coined by Schrödinger way back in 1935 in response to the famous EPR paper, but nothing much happened regarding this area for almost 50 years. And then in 1985, Wu in Australia performed the first, Margaret Reid, the group led by Margaret Reid in Australia, performed the first experiment of verification of EPR steering. And since then, steering has really come into vogue. And I must mention the pioneering work by the group led by Weismann. And they actually proposed a formal definition of quantum steering in an information theoretic sense. And now quantum steering fits in nicely in a very one-directional or nice hierarchy between entanglements and Bell non-locality. So if you can talk of quantum correlations, entanglement is the first and foremost correlations. And out of that, there are certain states which are steerable. So these form a subset of all entangled states. And out of all steerable states, there are certain states which violate Bell's inequalities, and these are called Bell non-local states. So steering fits in very nicely in this domain of quantum non-locality. And so steering is extremely appropriate for our proof of this one-sided device-independent self-testing that I will come to. And after giving you the theoretical formulation, we will discuss the first experimental implementation of this one-sided BIST scheme that was done in collaboration with the Chinese group, as I already said. And this experimental verification, of course, entails some very important concepts like robustness, no signaling, etc. So I will come to it. So this will be the first part or the maximum of my talk. And finally, towards the latter part of my talk, I will discuss self-testing in another way. And in that kind of self-testing, you do not require any entanglement. So if you are only interested in testing your devices, then you can do away with entanglement. So all of you know that entanglement is a costly as well as a fragile resource. So if you just want to test or certify your devices, how can you do it? So you can, of course, do it without entanglement. And in this domain, in this area, the concept of temporal correlations that I discussed is extremely important. So I will come to that in due course. Okay. So let me begin by giving a formal definition of self-testing. So what is self-testing? So it is verification of quantum states and measurements without direct access to the quantum systems. And this last part is, of course, very important. And this sets self-testing apart from the usual tomography. Well, those of you are aware, in quantum tomography, you also certify and verify quantum states and quantum processes. But then in quantum tomography, you have direct access to the quantum systems, or in other words, you actually trust the quantum systems given to you. But suppose you cannot trust these quantum systems that are given to you, then what is the protocol? So this is called a self-testing, that is verification of quantum states and also quantum measurements. So as I said, to repeat once again, the self-testing has to do with certification of quantum entanglement and also quantum devices without access to quantum devices or the trust of quantum devices. So this in a nutshell is self-testing. By the way, I would like to request all of you that if there are any questions from anybody and students, then please feel free to interrupt me and ask them, because the point is not to cover all that I want to cover, but to make myself actually, understandable to as many people as possible. So I hope if you have any questions, you will feel free to ask. Okay. So then we go on to the general, the paradigm of self-testing. So what we take here is the device-independent sense of self-testing. So suppose there are two parties, A and B, who are spatially separated, and by some means they actually share a quantum state. So it can be, to begin with, a very simple form of a bipartite two-qubit, which they share. And this state is actually produced by somebody else. They don't know and they don't trust. So now the question is, how will these two parties be able to verify that the state they share is indeed a shared quantum state that they have been promised by some manufacturer or by some sender? Okay. So they will have to go through a protocol with the help of a third party. And what is the job of the third party? Well, the third party is C, and the third party, as you see from this figure, from this cartoon, has no direct access either to the quantum state or to the devices which A and B produce. Okay. But what the third party can do is to ask some questions to both A and B, and depending on these questions, A and B can align their measurement settings in certain directions and perform measurements on their part, their respective part of the shared state, and then they can get some outcomes. So these questions, for example, that C asks A is called as X, and X is nothing but, let's say, the setting of the measurement device. For example, if A is performing Pauli measurements, then he actually aligns the Stern-Gall log along the X direction, right? So this is one way. Okay. And then if he gets the outcome, so in this case, the outcome, very simple, can be dichotomic, either upspin or downspin. Suppose they share a 2-qubit state. And then whatever the outcome is, if A is dichotomic 0 and 1, A communicates this outcome back to C. And similarly, C can ask the similar question of B, that is Y, and B can perform the measurement based on C's questions, and the outcome is B, which B again communicates to C. Okay. Now, the self-testing to be done is that C, based on his questions and answers, will actually compute a certain mathematical quantity, and based on the results of that mathematical quantity, C will be able to verify that the shared state between A and B is indeed the entangled state that they want to share in the beginning, or they have been promised by some manufacturer. And not only that, in addition, C will also be able to verify that A and B are making sort of quote unquote perfect qubit measurements. They are not making any other measurement. So that is the beauty of the task of self-testing. Okay. So how is it achieved? So this is the general setup, general problem. So then there is a given strategy by Alice and Bob, which determines a collection of conditional probability distributions of answers to the given questions. As I said, there are given questions, say X and Y, and depending on these questions, there are measurements, and then depending on the measurement, there are conditional outcome probabilities, that is the outcomes of A and B. So these are labeled as sets of these PAB given XY. And one can refer to such a collection as a correlation. Why a correlation? Because after all, depending on the particular questions, both A and B are performing measurements. They are spatially separated, but the outcomes of these measurements will be correlated because they are supposed to share some correlation at the beginning. And indeed, in a perfect sense, they share a maximally entangled state. Okay. And now such a correlation can be called quantum if that correlation is obtained by some quantum strategy. If it cannot be obtained by any classical means, classical protocols, then that correlation is indeed quantum. And then we come to how can we verify it as a quantum. And so let's consider a quantum strategy which is specified by what? It has to be specified by, first of all, a joint state psi, and let us take to begin with some projective measurements on both sides. That is pi on the side of Alice and pi on the side of Bob, respectively. So in general, these can be any measurements, any POBMs, but to begin with, to make our argument simple, let us take them as projective measurements. So now you can see exactly that indeed this joint probability PAB given XY is the expectation value of these projectors on the state psi, and then we can denote the set of quantum correlation that I've just written here by CQMNRS, where all these samples can have different sizes. Of course, let us not go into the technical issue of sizes, but let us say that Alice and Bob perform enough number of measurements, so they have enough number of samples, and they can faithfully actually get these probabilities. Okay, so this is the task, and now. What is device-independent self-testing? Now remember that the observer Charlie had no access to the devices of Alice and Bob, and Charlie has to certify the behavior of the quantum system based only on the above observed correlations. Okay, and there are certain minimal assumptions which go into this strategy. First of all, we have to take that Alice and Bob obey quantum mechanics, because quantum mechanics is the only true theory of nature. So we take this assumption, and also we require that there is no signaling between Alice and Bob. That is, Alice and Bob cannot cheat. One of the parties cannot cheat and doing some measurement. Say Alice cannot communicate to Bob that I see I have done this measurement and you also do such and such. So that they cannot do so because their devices are spatially separated and they obey a no signaling constraint. Okay. So now we come to the first formal definition of self-testing. So we have the correlation as we defined above in the previous slide, and such a correlation we say self-test state, which is called psi target, if it, that is psi target, can be uniquely achieved where Alice and Bob make local measurements on psi up to local isometries. So just pay half a minute of attention what we are saying here. So what we are saying is that Alice and Bob make some local measurements. They communicate their results to Charlie, C, and depending on their correlation, if Charlie can uniquely achieve or uniquely know what the state target is, then we say that this psi target is self-tested. Okay, but remember that in actuality we want to have the state psi target, but in reality Alice and Bob have actually this state only psi. Okay, one part of each of the state psi, right? Because this state psi is given to them by some manufacturer and we don't trust that manufacturer. Okay. So now let us do a typical situation now. Let us consider only a two qubit state and dichotomic measurements, spin up and down. So you can see that X and Y can take only dichotomic values 0 and 1. And similarly, the answers A and B can also be spin -1 and spin 1. So in this case, we can consider, depending on these correlations, the violation of the CHSH Bell non-locality. And indeed, we know that if we take a state and consider this CHSH correlator, which again all of you know by now, A0 B0 plus B1 plus A1 B0 minus B1, and take an expectation value in the state, the maximum value, that is the maximum violation of the CHSH, is given by 2√2. So now we say that the correlations in this quantum set, that is the set of all probabilities that are formed due to the measurements of Alice and Bob, the correlation that achieves this maximum violation self-test the maximally entangled pair of qubits. Okay, right. So what have we said in other words? So suppose Alice and Bob perform measurements and they give these outcomes answers to Charlie, and Charlie computes this CHSH correlator and gets 2√2. So what can Charlie conclude? Charlie can conclude that indeed the state that Alice and Bob shared is nothing but a maximally entangled state. That is one of the four possible Bell states. And not only that, Charlie can also conclude that the measurements performed by Alice and Bob are qubit measurements, okay, quantum qubit measurements, nothing else. Okay, so this indeed is an example of a fully device independent self-testing for a maximally entangled pure state. Okay, so you can say that suppose instead of a maximally entangled state, you have a non-maximally entangled state, and the hallmark of a non-maximally entangled state, pure state, is that you introduce another parameter. Of course, this has to be normalized. So instead of 1 by √2 0 0 plus 1 1, you have cos theta 0 0 plus sin theta 1. Now, in order to self-test this non-maximally entangled state, Achin et al. Proposed in 2012 that instead of using the CHSH inequality, you can use a tilted CHSH inequality. And what is the difference? Basically, you have a tilt factor alpha over here, and you can see that if you take an expectation value. So normally, if you apply your local realistic argument, local realism arguments, then you see that this correlator has to be less than equal to 2 plus alpha. So alpha is an extra. So if you know that if alpha goes to 0, this should be less than equal to 2. That is your standard Bell CHS inequality. Now, the maximum quantum violation of this inequality is given by L of alpha, that is square root of 8 plus 2 alpha square. So now again, using our previous argument, we can see that if your correlation violates this tilted CHSH inequality maximally, then you can confirm that the state indeed that was shared by Alice and Bob is this psi theta. That is cos theta 0, 0 plus sin theta 1. Okay, and alpha, as you can see, is easily related to theta in this way. So this is fully device-independent self-testing. And since the first proposal was given for maximally entangled states by Mayers and Yao in 2004, the literature is built on. So people have considered the next question that is very important is that suppose in any realistic situation, you can hardly ever obtain the maximal violation 2 to root 2 because there will naturally be experimental errors, experimental impurities, imperfections of devices. So suppose you do not observe 2 root 2, but say you observe 2 root 2 minus some epsilon. So can you say something about self-testing? The answer is indeed yes. So you can formulate a robustness protocol that given a certain bound which is less than what you can expect maximally, if you can still confirm that the state that is shared is indeed maximally entangled within that error. Okay, so this was done by the group of Scarani et al. 2012. Then the proof for all pure entangled state device independent came from Bams and Pironi 2015. And then they moved on to, instead of qubits, to qubits. This was done in 2016. So then instead of just 2 singlets, they can consider n singlets in 2015, and all pure bipartite entangled states again by the group of Scarani in 2017. So this is a very nice, interesting program of device-independent self-testing, and it involves, of course, certain level of mathematical rigor, as we will give you a glimpse as we move on. But a lot of progress has indeed been achieved in the domain of device-independent self-testing. Okay, and some of you may ask, what are the applications of self-testing? So there are many applications. For example, if you want to test your Hilbert space dimensions, you do not really know the state that you have, what Hilbert space they reside in. So you can use it using self-testing. Okay. Then device-independent quantum key distribution, another beautiful application using self-testing. Randomness generation. Okay, so if you want to generate randomness in a quantum mechanical way, okay, remember that classically you can never generate perfect randomness. But if you want to generate randomness in a quantum mechanical way, and you want to confirm that the randomness you generated is indeed quantum mechanical in origin, there is no other way other than self-testing. Delegated computation, so on and so forth. In fact, it should be clear to everybody that if you in your laboratory, you do any experiment which requires pure state entanglement, then there is no way out other than self-testing. Unless you can perfectly trust your devices, you will indeed have to perform self-testing first on the state that you access and also on your devices. So any experiment which is using pure state entanglement requires self-testing, and that is an application of self-testing. Okay. So now we move on to the heart of this talk. This was a general introduction. So we come to, so far we were talking of fully device independent self-testing. So now I'll come to what we call semi-device independent self-testing. So now what is the motivation? Well, the first and foremost motivation is that DI self-testing is extremely hard to implement in practical situations, right? Because why is it hard? Because we have to perform full bell tests, and full bell tests requires, those of you are aware, very high detector efficiency and preservation of entanglement up to a very high level. So it is extremely hard to perform. Again, those of you who actually listened to the first talk yesterday will get an idea where the speaker was talking of sharing of Bell non-local correlations, and he mentioned at least several times in his talk that after the first set of observers, it is extremely hard for the subsequent set of observers to again come and access this Bell non-locality. So this is extremely fragile. So that is one of the motivations why we can say move beyond fully DI self-testing. And also there is another kind of motivation which comes from practical considerations. And as I said earlier at the beginning of my talk, that in certain cases, partial knowledge of the systems is indeed available. Okay, or in other words, you actually, in realistic situations, you can trust partially your devices. In fact, if you have 2 devices, as I gave the example at the beginning of the talk, if you trust one of them and you don't trust the other, then instead of implementing full DI self-testing, you can indeed implement semi-device independent self-testing. And what is the advantage here? That in full mathematical rigor that you require for DI self-testing, of course, you also require full mathematical rigor for semi-DI self-testing, but there are some very stringent conditions which you can relax for semi-device independent protocols. And in this case also, realistic protocols which can be constructed, as we will show, and these are also robust against imperfections and noise. Okay. So these are the motivations, and one of the classes of semi-device independent self-testing is one-sided device independence. So again, to repeat, in many realistic situations, one of the parties can be trusted while the other is completely untrusted. So you have a typical server-client relation, and this is an area for upcoming quantum technology of networks, where you want to secure your, say, for example, financial transaction of banks. So banks can trust their servers, but they may not trust their client servers. Okay. So in the similar way, there are manufacturers of quantum devices whom you cannot trust, but once one of the devices comes to you, you can actually verify and trust it. Okay. And entangled states can be produced by third parties, so on and so forth. So what are the advantages of one-sided device independent self-testing over fully DIST? First of all, as I said earlier, here we want to implement a protocol based on quantum steering instead of a protocol based on Bell non-locality, and this certainly requires less resources. And quantum steering is less sensitive to decoherence, and it has better error tolerance. And as I said, indeed, this is a very quantifiable and quantified result. So if you want to implement quantum steering, you require 50% efficiency of the detectors. Whereas if you want to implement Bell violation, you require 83% efficiency for the detectors in order to close the typical detection loopholes like no signaling loopholes, etc. And also there are many technical advantages. So for example, if you want to go beyond two parties to multipartite scenarios, then you have to establish a tensor product structure in the joint Hilbert space if you want to do it in the Bell non-local scenario, which is dispensable if you want to do it in the sense of quantum state. Okay. So then these are advantages. Of course, this very, very quickly, what is quantum steering for those of you who are not aware? So this is indeed an asymmetric protocol. So suppose there is a source of an entangled state, and this source produces two particles. One of the particles goes to Alice, another goes to Bob. Let us very simply take it to be a pair of qubits. And Alice's measurement is sort of a black box. We do not know what Alice measures. We do not trust Alice. Whereas, on the other hand, we completely trust Bob. Okay, so we know that Bob performs quantum operations. So in this sense, then Alice will perform a measurement on whatever she got on her particle, and she will communicate her results to Bob, and Bob will perform his own measurements. And then again, in the sense, depending upon their joint outcomes, they will prepare some probabilities, conditional probabilities, given outcomes AB, given the measurement choices X and Y. Now, if such a conditional probability cannot be expressed as a sum, and this sum is over all, say, probability distributions over some variables lambda, and these are individual probabilities on each side, A given X lambda, B given Y rho lambda. If this probability cannot be expressed in this way, then we say that Alice has steered the state of Bob. In other words, by performing measurement on her subsystem, Alice has been able to steer Bob's subsystem, which is spatially located far away from her. Okay. So in generally, this problem can be, constructed or represented using not only projective measurements, but general measurements or POVMs, whose collections can be labeled as MA given X. These are set of all for all A and X. And these are positive, so this is greater than 0. And these are also normalized. So if you sum over all A, this is equal to 1. Now, depending upon the measurement operations performed by Alice, we say that an assemblage is produced on Bob's side. So what is an assemblage? It is basically nothing but a conditional state on Bob's side, which is let us take it to be an unnormalized conditional state. So which we label by sigma A given X, which is given in terms of the probability A given X times the conditional state rho, which is there on Bob's side. Why rho here? Because Alice has already performed a measurement X and got an outcome A. So this is a conditional state conditioned on Alice's measurement on Bob's side. And if you take a collection of all such conditional unnormalized states, then you have an assemblage here. And this is very simple mathematics. So in terms of this P of M, this assemblage can be written now as sigma A given X is trace over A, A of X, tensor product identity rho AB, okay, for all sigma A, any member of this assemblage. Now, this condition that I wrote, this theory condition that I wrote in terms of probabilities can also be expressed in terms of assemblages. That is, if this assemblage sigma A given X cannot be written as a sum over all P lambdas, P A X given lambda rho lambda, then this we say that the state which is shared by Alice and Bob is steerable, or in other words, there is no local hidden state model for Bob's assemblage. So you see there, by this probability, that is probability on Bob's side, if you assume there is a quantum state or a quantum hidden state there, then you can always express your probability like this. If this cannot be expressed, then there is no local hidden state model for Bob's assemblage. Okay, so then Alice is successful in her task of steering. Okay, so this is a very quantitative definition, of course, but we also need to actually specify certain measures of steering. For example, if you have Bell non-locality, you know that if the Bell correlator exceeds 2, then you can actually quantify by what amount the Bell violation has taken place, okay, up to a maximum of 2. Now, in this case also, you can define certain quantifiers of steering, which are called steering monotones. For example, one of the first proposal was this steerability weight by Skripsik in 2014. And what did they do here? They took this steering, this assemblage, that I defined here, okay, unnormalized assemblage, sigma A given X, and they broke it up into 2 parts, okay. So first part is called the steerable assemblage, which I denote by the SS superscript with some weight PS. And the second part is this unsteerable assemblage, which I denote by sigma US. Okay. So any given assemblage, a part of it can be useful for steering and another part is not useful for steering. So you can break it up into 2 parts. Of course, this P has to be less than 0 equal to 1. And then this is the steerable, this is the unsteerable assemblage. And so what is the steerability weight? It is simply given by minimizing this number PS over all possible decompositions. Now remember, by no means this is a unique decomposition. You can decompose in many possible ways. And if you find all possible ways and you minimize your PS, then you get a quantity which is called as SW or steerable. And some years later, our group also proposed another monotone for a measure of steering. And in this case, we thought that after all, these assemblages are unconditional; they are not directly observable. So why not actually formulate a measure based on some observable probabilities? So we took these joint observable probabilities, and actually we took the same approach, broke up these probabilities in terms of the steerable part and the unsteerable part, and there can be a large number of decompositions, many possible decompositions. And if you take all such decompositions that take the minimum of PS, then indeed you get a steering monotone, which is the minimization of all PS. So we call this as the steering cost. Okay. So why I'm talking? Because this argument, we will take one of these measures, and this will be important in our demonstration of one-sided DIST. Okay. So by the way, so this one-sided device-independent self-testing was first proposed by these people, Subi, Kopan, etc., and also independently by Georgiou in these 2 papers, and they considered only the maximally entangled pure state. Okay. So in order to certify such a pure state, which we call a target state, which is given by psi tilde lambda, which is a bipartite state, it belongs to the product of these two Hilbert spaces. And so what do? They actually consider the steerable assemblage which arises from this state. Okay, and upon using of these measurement operators which Alice performs, as I just said in one of my previous slides. Okay, so the conditions for self-testing are the follows as per the definition of self-testing. So Alice is allowed to do any operation on her side which leaves the physical assemblage on Bob's side unaffected. Because after all, we have to realize that Alice is in a black box. We do not know what operations Alice is performing. So she can do any possible operation which does not impact the physical assemblage on Bob's side. So for example, she can take her part of the subsystem and embed it in another Hilbert space. Okay, so in a sense, she can actually take a junk state which in another Hilbert space, say H of A, and actually couple her subsystem with this junk state. Okay. She can also perform any kinds of operations on her part of the subsystem, which is just labeled by this, by the way. So this is called isometry by Alice. And so we have to realize, because Alice is allowed to do such operations, so self-testing is possible only up to local isometries. So given a maximally entangled state, you can say that you have self-tested it only up to local isometry. So this is completely indispensable in any self-testing protocol. Okay. So now, they perform this self-testing argument for pure entangled, maximally entangled state, and then about 3 years ago, so we thought that let us try to extend this argument for any non-maximally entangled state as well. So we proposed the first proof of one-sided device independent self-testing for any pure 2-qubit state. So as I said, I take a parameter cos theta in the form of one of the possible Bell states. Now I can take any possible Bell state, because as I said, from the argument of local isometry, I can transform one possible Bell state into another. So this is up to local unitary transformation. Okay. So now what we do, we have two parties, Alice and Bob, and Alice is untrusted, but Bob is trusted. So let us say that Bob performs quantum measurements in mutually unbiased basis, and let us say we choose the basis of in these two forms. So these are two measurements. B0 is 0, 0, minus 1, 1, and B1 is the orthogonal basis, that is plus, plus, minus, minus, minus. Okay. Now, Alice's measurements are, of course, in a black box. So we can assume that she can perform anything. To begin with, let us take a test measurement for Alice, that is given by A0 equal to 0, 0, minus 1, 1, and A1 equal to cos theta 0, 0, minus 1, 1, plus sin theta plus, plus, minus, minus, minus. Now, conditioned on the fact that Alice and Bob do such measurements and they collect the statistics of these measurements, then we have to see whether steering is implemented by them or not. So this is a one-sided device independent scenario. We trust Bob, we do not trust Alice. And how do we check whether steering is implemented? We check it by the help of a steering inequality, which is called a fine-grained steering inequality, which was proposed by our group some years ago, about seven years ago. So we proposed a fine-grained steering inequality. And what is the fine-grained steering inequality? Which we just test steering. So suppose steering is not possible, then you have a bound, okay, local hidden state bound, given that the sum of these two probabilities have to be less than equal to 1 by root 2. So what are these probabilities? Suppose A performs a measurement on this operator A0, and conditioned on that, Bob performs a measurement in this direction B0. So this is one probability. Similarly, you have another term where A performs a measurement along direction A1, and conditioned on that, Bob performs a measurement on the condition state and direction B1. So we collect these probabilities and we check whether this fine-grained steering inequality is violated or not. And the maximum violation is, this is possible, that is, this becomes 2, is only possible for the above measurement, nothing else, up to local unity. So this is essentially, I have given for you the statement of self-testing, that if you make these measurements, collect these probabilities, and get an outcome 2 for the left-hand side, that is the sum of these two probabilities, if you get 2, then you can sanguinely certify that indeed Alice and Bob share this state, non-maximally entangled state, as well as Alice performed this measurement that we already know. But not only that, Bob performed this measurement that we already know. But not only that, Alice in principle can perform any measurement, but unless and until she performs only this particular set of measurements, she can never, both of them can never get a violation of 2. So this is our statement of self-testing. And of course, the proof is somewhat technical, and I think I do not have too much time to go through the proof. So let me just skip the proof. Those of you who are interested, I can relate it to, I can discuss with you later. So this is a proof. Again, it uses the concept of steering monotones that we have here. So let me skip it. And so this is finally the proof. So what we just focus on the last line of the slide, that is the maximal violation of the fine-grained steering inequality implies that Alice's measurements are nothing but A0 and A1, nothing else. Okay, so this is a continuity of the proof of isometry. Again, let me skip it, and let me just come to one more interesting question, of course. So now I say that this state has been self-tested. I have verified without having access to the state and the device that indeed the two parties, Alice and Bob, share this state. But there is a parameter theta here. Can I ask a further question, that which particular state is self-tested? Note that I'm going slightly beyond the usual self-testing protocol here. I'm asking a further question, that whether one can not only ask this question, that which particular state, and in the process, I can also ask how much entanglement is there. How much entanglement is certified. Because as soon as you know theta, you can know the concurrence of the state, which is given by C2 theta. So indeed, we can also answer this question within the steering framework. And for that, one has to consider another form of steering inequality. Remember, we considered one form which we proposed as the fine-grained steering inequality. But there is also a necessary and sufficient condition for 2-2-2 steering, which was given by Cavalcanti et al. Weinberg was also one of the co-authors, which is given by this inequality. And now if you compute this violation of this inequality, and on one hand, and also plot the concurrence on another hand, you see that both of them are monotonic functions of theta, right? So both of them, this is C equal to sine 2 theta concurrence, and this is also a monotonic function. So indeed, this violation, that is the steering sum and concurrence, are in one-to-one correspondence, and depending on the violation of this inequality that you obtain from your measurement correlation, you can immediately pinpoint the value of concurrence, and from the value of concurrence, you can immediately get the value of theta. So not only can you certify how much entanglement you have self-tested, you can certify the exact state. So this is beyond the standard ambit of the self-testing protocol. And this can be achieved from another way also, if you can define some correlators like this: P equal to 0, B equal to 0 given xy, plus B equal to 1, B equal to 1 given xy. You can define something which is called the predictability, okay, which is the minimum over these two correlations. And concurrence is also a function of this mutual predictability, C square equal to 2E minus 1. And as soon as you determine these probabilities, you can determine concurrence, and from that you can determine the state. Note that this is very interesting, because in order to determine these probabilities, you do not require the full set of measurement correlation, the complete set PABXY. Okay, so we can also prove that the scheme is robust, and again, due to lack of time, I'm not going into that. So suppose instead of these maximally entangled state, there is some impurity, and instead of these qubit measurements, again, there is some dephasing. Then how do you test self-testing? You can do it through the method of operator inequalities, which was proposed by Kaniewski in 2016, and we indeed showed that this method is robust. And now this is the experimental scheme which was done by the Chinese group in partly in Beijing and Nanjing. And you see this is a linear optical setup. Alice is here, Bob is here, and then there is a laser which actually produces an entangled state, and then Alice and Bob perform certain measurements, and Alice communicates the result of a measurement to Bob, and then steering is achieved and self-testing is achieved. Okay, so this is the experimental protocol which we suggested is exactly goes according to our theoretical plan. So we take an initial state that we do not know, and of course we know Bob's measurement, so let us choose B0 sigma x and B1 sigma z, and let Alice choose anything, A1, A0, and A1. Now Alice and Bob perform measurements, they calculate these conditional probabilities, we calculate the sum of these probabilities, and suppose we do not get this equal to 2, then we go back here and Alice chooses a different set of measurements. She keeps on repeating until this value of this sum of these probabilities is equal to 2. And as soon as this is 2, then we compute these mutual predictabilities, as I showed in my last slide. And as soon as you compute these mutual predictabilities, you know the state parameters in terms of the concurrence. And as soon as you know the state parameters, you know what Alice's measurements are. So just from this protocol, you are able to verify not only that the state, for example, if it is 5 plus, again, up to some local isometry, but also what exact measurements that Alice has performed without doing any state tomography. So these are the experimental results. Again, I do not have time to explain much of the nitty-gritties. And also, as I said, that the state can be, to begin with, it can contain some impurities, and then we construct a fidelity. Check here that even if the purity is 0.95, the lowest fidelity, that is the target state that we have self-tested compared to the tomographically reconstructed state, is greater than this 0.95. So this says that we indeed have an operational robustness of this protocol. And of course, again, this robustness bound has been self-tested. And finally, as I said, that no signaling constraints can also be demonstrated in the scheme. And so in the last few minutes, 5 minutes or so, let me go beyond this protocol of self-testing. And now let me discuss, just give you a brief glimpse of a protocol of self-testing of measurement devices without entanglement. Okay, so this is a very recent work which has just come out, I think, last month. So again, this is a work of our group in collaboration with Jeba, who was an earlier postdoc, now is in Poland. So the motivation is the follows, that as I am saying again and again, entanglement is a costly resource, as well it is a fragile resource, it gets easily destroyed. Okay, and as again, you take most protocols in quantum information processing, qubit systems are the most widely used protocols. Okay, so and again, when you actually implement some quantum information processing protocols, you typically require at least binary measurements. Okay, you require two parties, one is called Alice, another called Bob. They have independent measurement devices. So this indeed motivates for construction of a self-testing protocol for binary Pauli measurement. So suppose you have these two devices, and these two devices can perform Pauli measurements, but you do not trust these devices. They are given to you by some manufacturer. Can you self-test such devices? Okay, and the most important question is that can you self-test without using the standard self-testing argument, which requires entanglement and which requires a lot of entanglement for the fully device independent protocol using Bell non-locality, and it's also required some entanglement for the semi-device independent protocols requiring steering, okay, based on steering. So now the question is, we will forget about entanglement. So suppose we will consider an input state, so this is a single party state which is prepared by some party and sent to Alice. Alice performs a measurement which is, say, given by capital AI, obtains an outcome small ai, and what she does is to pass this state, which is a single party, can be a single qubit, and she passes it on to Bob, who comes into the play after a certain time t and performs a measurement pj, gets an outcome small pj. So now again these probabilities, conditional probabilities, can be arranged, and these correlators Cij can be constructed out of these conditional probabilities. And having constructed these correlators, let us take them four of these. We can construct this algebraic sum, and we can apply the argument of classical realism that was done by Leggett and Gerg way back in 1985, and you get an inequality which signifies what? Which can be violated by temporal quantum correlation. So these are indeed temporal correlations, because Alice makes a measurement at some time t and Bob makes a measurement at some time t2 later on. Okay, so the argument of macro-realism that was used by Leggett-Gerg in order to devise such an inequality from the joint assumptions of non-invasive measurement and also realism, but these can be refined slightly. In fact, in the modern parlance, we can derive such an inequality using the two argument of predictability, that is the joint statistics lie in this domain 0 and 1, and also no signaling in time, that is by the act of Alice's measurement, Bob's measurement outcome is not affected. So if we assume these two conditions, that is NSIT-based predictability, we can again derive the Leggett-Gerg inequality. Okay, and that is indeed what we have done in this paper. So we have considered this such inequality, and then we have considered just single qubit measurements performed both by Alice along A1, let's say general, and Bob along B1. And our self-testing argument is extremely simple, that the maximum quantum violation K4 of this four-term inequality, it can be 2√2. It can be achieved only if and only if A performs sigma Z and sigma X, whereas B performs these combinations, sigma X plus sigma Z, sigma X minus sigma Z. So this is a beautiful argument. Of course, the statement is simple, but the mathematics is again not extremely simple, because we have to construct a self-testing proof that we did for the earlier case also. And in fact, I cannot show it for you. So I will just show it for you what is the robustness bound. So we can indeed think that these measurements are not ideal, but there is some dephasing. So for example, the directions of Alice's measurements are altered by this parameter theta, and same for Bob. Okay. So now we again construct this fidelity. So up to what fidelity should we get the violation of this Leggett-Gerg inequality, so that I can indeed trust that my probabilities give me an argument of self-testing. So there, to check that, I actually plot. So this is the theoretical bound, and I plot the data upon putting actual values of this measurement operator. So you can see clearly that this blue curve, which is the data upon feeding the actual measurement operators, if they are dephased by this angle, this lies above the bound. So we can say that our protocol is robust up to experimental imperfectness. And finally, I have come almost to the end of my time. I will end by just giving you a glimpse of another improvement that we have done recently. So our earlier protocol had to perform, or had to assume in the proof, at least 2x2 block diagonal measurement. So this lemma is part of a proof of self-testing, where we needed to assume that if Alice and Bob share a general state, that is not a qubit, but general state in any dimensions, then such kind of block diagonal measurements are implemented at both their ends. Okay, so this is again, some people technically they regard this as kind of a restriction, because we do not know to begin with which state this experiment is trending. This can be a qubit, or this can be a state in any dimension. So if Alice and Bob indeed want to certify or verify that their measurement devices are perfect, they can do it if they get access to any state. So this lacuna remained in the proof, which was published here. So very recently we have posted another work where we do away with this kind of two device arrangement. We take a preparer who sends a state which is in any dimension, so T is arbitrary, and the preparer can send any state, in fact even a maximally mixed state, which remains unaffected by any further noise to this device, and Alice, who is here, only a single party in this device, now can perform 4 of any possible measurement. So A, 1, 2, 3, 4. And after performing 1, she again sends back to herself. So this loop goes on 4 times. And they again get 4-time correlator for this term. And now this correlator we actually write in terms of Fourier transform quantities, for not the conditional probabilities, but Fourier transform them. Then we perform a sum of square decomposition. And just to give you an idea, for the 2D case, this inequality looks like this. Okay, so this is another form of a temporal steering inequality, which is slightly different from the canonical Leggett curve form. And using this, we perform certification of quantum measurements, not only with the initial state is 2-dimensional, but the state is any dimensional. And finally, we perform the robust analysis as well. And for an icing on the cake, using this arrangement, we can also generate a secure randomness certification protocol. So for example, Alice performs these 4 measurements, and if you take only the first 2, and if you compute the Shannon entropy of these first 2 measurements, and if you plot it, say, for example, the dimensionality of the state, then you can see that if you go to higher and higher dimensions, the more and more randomness Alice and Bob will be able to certify in a quantum mechanical way. So this is genuinely quantum mechanical because this is a measure of quantum randomness. Okay, so self-testing protocol, as we said, as an application, and even self-testing protocol without entanglement that is based on temporal correlations also as an application, as we showed, and that is secure randomness generation. So finally, I think I have just overshot my time, and I conclude with the summary slide. So what we tried to discuss in this talk, in this protocol for semi-device independent self-testing. The first ones, they actually used entanglement. The idea there was not only to test the devices, but also to test the input entangled state. And the experiment was also performed, which actually guaranteed the robustness. And the final set of protocols is to do with self-testing of only measurements without entanglement. And there also we have proposed 2 protocols which have reduced any dimensional restriction and any requirement of entanglement. So thank you very much for your attention. Thank
you. Thank you, Professor Majumdar. So now the floor is open to question sessions. Since we are short of time, please.
Yeah, Usha actually also wrote something in the chat box.
This is about your fine-grain answer, that is inequality that you showed.
Yeah.
You have chosen Alice's measurements, which are theta dependent. How are they determined is one question that I wanted to ask.
Sure.
Alice's measurements A0 and A0 and A1. Bob's measurements were fixed to be sigma z and sigma x there, 0, 0, minus 1, 1.
Exactly, absolutely. So you are coming to this slide, I think. Yes. Yeah. So you see, so we are in an asymmetric situation because we want to implement steering, and our purpose is to perform self-testing using violation of some steering inequality, which we take it as the fine-grained steering inequality. So now, because Bob is trusted, we can take Bob's measurement to be perfectly in a mutually unbiased basis, right? But to begin with, a priori, we do not know what measurements Alice is performing, right? Because the whole idea is to actually say that Alice indeed has performed this measurement. So a priori, we do not know. So of course, but we have to propose a certain ansatz, and because theta is the only parameter available, so we propose this ansatz from Alice, and then we show the beauty of the argument is that if you take this inequality and construct these probabilities, compute these conditional probabilities, so you get true only if Alice performs this. Alice, if she performs any other type of measurement, they will not get this value 2 here. They will always get less than 2. So that is the argument. Of course, the proof
is some
not
kind
present.
of identification that you have.
Sorry?
Have an identification. You have your own identification for what
Yes.
measurements analysts should do. So why
Yeah,
I
yeah.
ask this question is Horodesky's results on CHSH inequality, their measurements, that is what is the bound, depends on what measurements you take. In CHSH inequality, for any mixed state, there is a measurement which is prescribed so that you do have an appropriate bound there. So I wondered.
Sorry. I think we are talking two things very differently. So are you talking of self-testing protocols or Bell non-locality violation?
I am linking it with that so that why it was not used here is my question. CHSH inequality for maximal bound, there are some prescriptions. Such prescriptions do not exist here is what I wanted to ask you that question.
Yeah.
That
You see this.
Measurements are something here.
Yeah. You see, so first of all, if you're just talking of Bell non-locality violation, then Bell non-locality violation can be done with any mixed state also, right? So there is no problem.
Right.
But if you're talking of self-testing, there is no till date rigorous protocol for mixed state. So only you have to consider pure state because the protocol is constructed in such a way it doesn't work. But you can do with non-maximally entangled pure states, even for Bell violation. And for Bell violation, you can do with non-maximally entangled pure state, as I showed in one of the examples. In fact, you can do it in using this tilted CHSH inequality. Okay,
Right.
These people proposed in 2012, right? And
Mhm.
now so I've not given you the details. So of course, they will also give you some measurements. And in this case, what you will have is that the measurement which turns out to be the measurement direction, which turns out to be a function of the theta or alpha, exactly in a similar way. And here what will be true for our steering case is that, again, the measurement which maximally violates this fine-grained steering inequality has to be along exactly in this form. So now one part of the question. So now if we come to the identification problem, up to there, we have identified the state and the measurement only up to some local unitary theta. So now if you want to ask me what exactly this theta is, then in addition to the fine-grained steering inequality, I take the help of another, the original CFFW inequality, which you know, which is given by this. Now the simplicity of the argument is, I'm sorry, that this violation of this steering sum as well as the concurrence are in one-to-one correspondence. So immediately from this violation, I know what is the value of concurrence. And because my state is parameterized like this, where concurrence is sine 2 theta, I know exactly what is the state. So which takes me beyond the standard self-testing paradigm. In this case, I have not only identified the states and measurements up to some local unitaries, isometry, but I've also identified exactly what is the state that is given by some experiment. I hope this is clear.
Okay, I will think about it later.
Okay.
Thank you.
Thank you.
One more comment, just
sure.
a comment, is that in any commercial quantum, that is key distribution, one takes only device independent setup, not semi-device independent. I always wondered why they don't use semi-device independent. Is it just that they have it, so they use device independent? Because semi-device independent is practically feasible, is what I understand.
Yeah.
Commercial
No, so that's
things always use device.
Yeah. So it's a good question. I think it's more to do with the trend, because after all, device independent follows the Bell non-locality approach, which is the traditional approach. So many people, in fact, people who are outside the quantum foundations domain these days, have also heard about Bell non-locality violation. But steering has actually just picked up in the last several years. So not all people, even within the community, are very familiar with steering. So that is why, although that is extremely more challenging to implement the full DI protocols, people are still, focused on fully DI protocols. Whereas it should be definitely easier, less resource consuming to implement semi-DI protocols. But nowadays, I think more and more people will take up these semi-DI protocols.
Hope so. Thank you.
Yeah.
Thank you
Thank
for
you.
your.
Thank you. Thank you.
Okay. Yeah, if there are no more questions, let us thank
There
Professor
are questions in the
Majumdar.
chat. So there are questions in the chat.
Okay, we are actually running short of time.
So
Because
chat, let me
to
see
again
where is the chat.
for
So
the
can
next,
somebody read it out? Okay, I'll just, okay. I'll come from the top. Okay, please write in the chat box.
Okay.
So are both Alice and Bob making measurements on the same state temporarily separated? If so, doesn't the state collapse? Okay. So that is a good question. Okay. So the point is, if you are talking of the temporal correlation scenario, then certainly Alice and Bob are making measurements on the same state. But and of course, when Alice makes a measurement, the state collapses to the eigenstate of Alice's measurement operator. But then the state again evolves. It is re-evolution and goes to Bob. So Bob can make a measurement on that state. And more generally, Alice can make a POVM, and she need not make a projective measurement. So then there is no problem. So I hope, Alice, this question is answered. And the next question is how to get no signaling constraints experimentally if there are spatial correlations. Okay, fine. So you see that spatial correlations is something, but using such spatial correlations, you cannot signal violating your laws of relativity. So that is being proved long ago. So even if you have Bell non-locality, that is violation of Bell CHS inequality, you cannot signal violating the special theory of relativity. So what has to be ensured in these experiments is that Alice and Bob are spatially separated, and they indeed share some correlations which are weaker than Bell violating, but which indeed contain entanglement. We call them as steerable correlations. So these are spatial correlations. But however, we have to ensure that, see, Alice performs the measurement independently and Bob performs the measurement independently. We have to ensure that there is no signaling between Alice and Bob, so which can be completely ensured experimentally. So there is no contradiction here, right? So I could only see these two questions.
I just, yeah. Okay, thank you very much. So we conclude this first talk today. We are already overshooted the scheduled time. So we come back after the lunch at 2. Yeah, so thank you once again to the speaker, Professor Arjun. Thank you.
Hello. Hello.
Hello.
Am I audible, sir?
Yeah, I am back.
Okay.
Yes, good afternoon.
Yeah, good afternoon.
Yes, so thanks for your invitation. Nice to be here with you. Can I try to share the screen?
Yeah, you can try now. No problem.
Okay, let's see. It looks like I do not have such a privilege, so I try to share and it doesn't allow me yet.
Okay, I will request the volunteers to do the needful. Just 1 second. Yeah.
Yes, sir. All right. One second, one second. Take it.
Yes, now it works. Just a second.
Yeah, we can
Can you
see
see the
your
full
slides.
screen
Yeah.
now?
Yes,
Yes, and you
yes.
see the full screen as it should be. Great.
Yeah, it is full screen. Yeah.
Okay. Okay. So everything is fine. Yes, you can hear me, you can see me and my slides.
Yeah.
Good, good. So look, in India, we will start in, let's say, 8 minutes. Yes.
Yes.
Great. And I have something like 55 minutes, less than 1 hour.
Yeah. Less than 1 hour. You take 1 hour, no problem. Yeah.
Okay. Okay. And one more question. Is it so that all of you are watching online, or some of you are gathered in the institute on site? It's only online?
It's only online.
Okay, okay, good, good. Yes, so thank you very much. I will come back in a second.
Hi. Can I also ask the organizer to get access to share my screen? I'm the second speaker in the session.
Okay, we just give me a minute.
Maybe we can use like this time to do the testing before so that everything goes smoothly.
So do you wish me to stop sharing?
If you want, you can keep it. I think it should be fine. But
So, Dr. Buka, we'll let you test right now, and then we'll make.
okay,
we
so
have
you
enough
want to
time,
test?
so I can stop sharing.
Okay.
So look, I stopped sharing. So
Okay.
now please try, Marine, please try your.
Thanks, Carol. Okay, so now the button is enabled and I can share the screen, and I hope you guys can see now the slides, right?
Yes, we do.
Yes,
They're
yes.
changing, right?
Yes.
Okay, excellent. Okay, so then
So if you could
how
stop
do I
sharing,
stop
then.
sharing now? Here. Excellent. Thank you.
Okay.
Please give me back the privileges to share the screen.
Yes,
I
got
will
it.
try to put it again.
Oh, so only one person can share at a time. I see.
Makes
Yeah,
sense.
yeah, only one
Yeah.
person can share at a time. Yeah.
Okay. That's why the privilege is not there. Okay, cool. Thanks, guys.
Okay. Yes, can you see now back entire screen?
Yeah, full screen. Yes, I can see. Yeah.
Good, good. Okay, so I'm more or less ready. Yes, we have still a few minutes to start.
Yeah.
Okay.
We have 5 minutes left.
Good. I'm coming back soon.
Right.
Yes, so I'm back and I'm ready to go as you wish.
So hello and a warm welcome once again to QFA 2021. We will begin the post-lunch session shortly. So Dr. Narayanan, if you can take over as the moderator.
Yeah, we have 2 minutes. Yeah. So welcome to speakers and all the participants at QFA 2021. We are beginning our post-lunch session. The first talk by Professor Karol Zurkowski. He is a senior professor at Jagiellon University, Poland. He is also with the Polish Academy of Sciences at Warsaw. He is also serving as the director of Quantum Information Center at Gdańsk. He has obtained his PhD degree from the same university, and he is a visiting professor at the Perimeter Institute, Canada, and also serving in various capacity at Academia Europea, and also he is a recipient of Master 7 grant. Professor Karol Zurkowski has a research interest in the domain of quantum information, quantum measurement, entropy, quantum chaos, geometry of quantum states, random matrices, nonlinear dynamics, and fractals. Interest in the game theory and financial mathematics. So I warmly welcome Professor Karol Zurkowski, and his talk is a plenary talk of today's session. So the mic is over to Professor Karol. Thank you.
Thank you very much. Can you hear me?
Yeah, sure, we can hear you.
Yes. So it's my great pleasure to be in India. Unfortunately, I cannot visit you right now on site, but I'm very, very pleased to be with you online. And it's my great pleasure to be in India again. I visited your country several times, but I've never been yet to Jodhpur. And today I have a pleasure to make a longer introduction to this subject, which is related to some special designs. Eventually, I will mention mutually unbiased bases and some structures in Hilbert space, which will be used or are important for both foundations of quantum theory and the theory of quantum information. Let me first mention my collaborators, Jakub Czartowski, here from Krakow. I had a very nice collaboration with Dardo Goszeneche from Chile. He worked in Krakow, now is in Antofagasta in Chile, and Markus Grassl from Germany works now in Gdańsk, in Poland. Well, you could ask, what is this talk about? In general, well, we'll discuss combinatorial designs. What are they? There are some strange structures, let's say mathematical structures, usually combinatorial designs. You can think, there are some finite sets arranged with balance and symmetry. For instance, maybe you have seen such a magic square. You see a square of 9 numbers, and some in each row. Each column is here, in this case, 15. By the way, it's a special magic square, very magic, because also along both diagonal, the sum is the same. Well, another simple example is so-called Latin square. Now you see 4 times 4 grid. There are only 4 symbols. And as you can easily see, in each column, each row, there is only 1 symbol. No 2 symbols can repeat. So there are many, many other examples, and mathematicians, especially people working in combinatorics, study them for a long, long time. Here I will mention only Fano plane. This is a nice constellation of 7 dots ordered in such a way that 3 points belong to a single line. Of course, this circle is also considered as a line. And then any 3 lines crossing a single point. The special, as you see, design. And here I will mention Greco-Latin square. We have again 4 times 4 square. Now each box you have 2 letters, 1 capital Latin letter, 2nd Greek letter. Therefore the name Greco-Latin square. As you can see, not only in each column, each row, there's only 1 Latin, 1 Greek letter, but then there are 16 boxes, and the pair of 2 letters, 1 Greek, 1 Latin, will never be repeated. In other language, this is called or Greco-Latin square, or a pair of 2 mutually orthogonal Latin squares. So one is produced by Latin numbers, second by Greek numbers. So here are examples of classical objects known and studied for many, many years. Why we care about them? Okay, we'll switch the gears. We'll not discuss classical objects, but quantum. So instead of such letters, we'll consider quantum states. And we'll, in fact, discuss constellations of states, so some discrete structures in the finite Hilbert space. We assume that the size of Hilbert space is given. It's finite, like 2, 3, 4, 5. And we discuss different constellations of quantum states. For instance, we'll discuss mutually unbiased bases, I will provide the definition later on. Usually we refer to them as MUPs. Then generalized measurements, which are called symmetric, informationally complete generalized quantum measurements or positive operational value measures, so SIC or SIC POVMs. Then quantum orthogonal Latin squares or orthogonal arrays or quantum orthogonal arrays or complex projective T designs, which will be formed of pure quantum states in a special way, and several generalizations like mixed states T designs. Well, you could ask why we care, why we do it. On one hand, because we do not fully understand the structure of quantum theory. For instance, several basic questions concerning such constellations are open. We are not sure in a given dimension which structures do exist. Then such structures are usually related to some schemes of generalized measurements, so they can be used in principle in laboratory, but definitely in the theory of quantum information. And also we are wishing to design techniques of averaging over the set of all pure states. So like pure states for 1 qubit correspond to the Bloch sphere, which is only hollow empty sphere. So we average over set of pure states, like taking the standard measure, uniform measure at the sphere, or sometimes it's important to discuss also mixed states, density matrices. In the case of 1 qubit, they correspond to the full Bloch ball, so the sphere and everything inside, and then we average over 3-dimensional full ball. By the way, if something is not clear, you want to ask a quick question or wish to have some explanation, I think we have enough of time, so you can just interrupt me and ask question. I will also be pleased if this chair from time to time will also say something to, so I could be sure that you are there, because it's a strange feeling to talking only to the screen. I'm not sure whether you have already you are sleeping or not. So are you there? Is somebody listening to me?
Yes, we can hear you. I wanted to ask
hello,
you about
hello, yes.
hello.
Yes. So thanks. We met last week.
Constellation.
Thanks for being with us. Yes. Hello, Usha, David. Yes. Good. Thanks.
Majorana constellation. That is, Majorana had also given a constellation of stars, points.
Exactly. Exactly. So this is another point. Good point. I also like them very much. We also call them stellar representation of a given state. It is very much related. So going back to the story, I think I should start with the so-called Mermin-Perez magic square. Why? I believe it is one of the first combinatorial quantum combinatorial designs. So again, you see design, it was a like square of some numbers or objects arranged in a special way. Here, this special magic square of Mermin and Perez is a square of operators. So it's very simple. They are matrices, in fact, of size 4, because here we have 2 qubit operators. So this means like 1 tensor product sigma z. So you have 9 such operators. What is magic here? The magic is that operators in each column and each row do commute. They are form so-called compatible measurements. So even though, of course, all those operators mutually do not commute, they are ordered in such a special way that in each column, each row, they do commute. So in some sense, well, it is a special constellation of matrices, of operators with some special properties, with simple applications in quantum theory, because they give us, you see, 1, 2, 3, 4, 5, 6 different measurements, 6 different compatible measurements, in fact, 2 triples of measurements. So technically, the situation is simple. Instead of like objects like this, where we have numbers or letters, we exchange them into states or operators and ask about special constellations of such quantum objects. Here I will mention a nice definition of quantum Latin squares, which is not very old. I refer to the paper by Vicari and Musto from 2016. So the idea is very, very simple. Instead of a definition, I will show you an example of all the n equal 4, we have again a configuration of 16, but now not numbers, but quantum states. All those states belong to the Hilbert space of size 4, and definition is very simple. We call it quantum Latin squares if each column or each row forms an orthogonal basis, as simple as that. So you see, here are classical states like 0, 1, 2, 3. They form a computational basis. So of course, they are classically different. Quantum mechanically, they form a basis. So you have first basis, then now you have permuted basis. But here, in the quantum scenario, you allow entanglement. So for instance, those states, high plus minus, are famous Bell states. We have here entanglement in the subspace 1, 2, and another pair of states like psi plus and minus, they're also entangled, in fact not maximally entangled, in the complementary subspace 0 and 3. Therefore, it's easy to see that those two rows form also orthogonal bases, but also vertically, all columns form orthogonal bases. So it is again a nice constellation of quantum states. In this case, we have, look here, here are 4 and 4, so 8 states, which form altogether, so vertically 4, horizontally 4, so 8 bases, 8 orthogonal bases. In more general words, in standard combinatorics, we take care about individual objects, like letters, symbols, and we use the group of permutations. We are allowed to exchange them. So the permutation group is also discrete. It's a group of permutation matrices, which is finite. And in the generalized, like quantum combinatorics, instead of discrete set of symbols, we work with the set of quantum states, which is now continuous. And in a sense, we embed this discrete permutation group in much larger space of unitary matrices. We discuss now unitary group, continuous unitary group, which allows to transform any pure state into any other state. So this is the main idea and main generalization. So I will only mention that there are many other designs like orthogonal arrays. Okay, I mentioned Latin squares, Latin cubes, and so on. And if you wish, so here are some letters. So there are Latin squares, mutually orthogonal Latin squares, or Latin cubes, or orthogonal arrays. And now, basically, for all those classical definitions, you can find corresponding quantum definitions. Like QOA will be quantum orthogonal arrays. Here, quantum Latin squares, quantum Latin cubes, and so on. I will not discuss today all of those. However, the idea is very simple. You take a classical object, combinatorial object, and you exchange the discrete numbers to be replaced by quantum states, and you possibly allow for superpositions of states or quantum entanglement, and then you can play with quantum analogs, which of course is much larger. So if this green small set is the classical set of some objects like orthogonal arrays, the blue set of quantum contains all those classical objects, and it's much larger. Here I will mention another paper with Dardo Goyeneche, Zahra, Raisi, and Sara Di Martino, published, well, 3 years ago. Now, going a little bit back to physics, I already mentioned the name of mutually unbiased basis. Let me recall the definition. In the simplest case, look, you take the red basis in R2, standard basis, and now you rotate the basis, take the blue one. So you rotate it a little bit, and now you want to be the blue basis as far away from the red as possible. So if you slightly start to rotate, of course, you have to stop at some point, because otherwise the blue line will go to be too close to the red one. So of course you can guess that the best solution is to stay here at the angle of 45 degrees. So then those two bases are in a sense as far apart as possible, what you can quantify by computing the scalar products. So phi I are the states of the first basis, psi j of the second, and you require that the squared overlap is the same. It's the same, so it has to be 1 over n, where n is the size of the Hilbert space. In this case, of course, the size of the space is 2, so then this overlap squared is 1/2. This is easy to see that the blue vector you can decompose in the red bases will have the same components, horizontal and vertical, so the scalar product is the same. Why it is important? This configuration is important because it allows us to provide, in some sense, optimal quantum measurements. Let's assume red basis corresponds to one measurement, then you want to perform another measurement. And of course, it will be pointless to perform the measurement in the same basis. You want to have the basis to be, in a sense, as far as possible from the first, to extract as much information as possible. And now simple reasoning tells you that just this blue basis will be optimal. And then such a scheme gives us an optimal scheme of quantum measurements. It is possible to show that for a complex Hilbert space of size n, there are not more than n+1 such bases. So if n is equal to, we get n+1 is 3. And then, of course, you can guess there are 3 well-known bases. They are just eigenbases of 3 Pauli matrices, 3 Pauli operators, sigma x, sigma y. Here is a misprint to check if you are sleeping. It should be, of course, what here? What is missing? What is wrong?
Sigma z. Sigma
Yes,
z.
thank you very much. Very well. So I see that some of you are, yes, alive. I managed to notice my misprint. Of course, here should be sigma z, so sigma z. So there are 3 bases corresponding to 3 different directions in the standard block ball. And now it's also interesting to see that mathematics starts to play an important role here, in the sense that this full set of n+1 mupes is known if the dimension is prime, p is a prime number, or if it's a power of prime, like 2 to the power 2 is 4. Such a full set of 5 bases is known for dimension of size 4. However, n equals 6 is, in a sense, first exceptional case. 6 is, as you know, 2 times 3. So it is neither a prime number nor a power of prime. 2 and 3 are different factors. And strangely enough, we know that there are not more than 7 mupes. 7 is 6 plus 1. But up till now, only 3 bases are known. And the question arises, what is the number or maximal number of mutually unbiased bases in dimension 6? So even in such a simple, relatively not so huge dimension, we deal with matrices of size 6, and nobody knows the answer for such a seemingly innocent question. Well, if you want to go from one basis, then determined by the vectors phi, to another determined by psi j, so you look for such a matrix such that all squared elements or scalar products are the same, so they have the same modulus. And such a matrix is a simple generalization of the Hadamard matrix. They are called complex Hadamard matrices. So standard Hadamard is like 1, 1, 1, minus 1. So it has all entries only +1 or -1, of course, of the same modulus. And here we allow the phases to be arbitrary. So the definition is simple. It's a matrix which is unitary and has unimodular entries. So all of them, in mathematics, you say that they are equal to 1. In physics, we rescale them by n just to have the matrix to be unitary. So definition is very simple. And here, again, a strange situation occurs with the numbers, because for n equal 2, 3, 4, 5, we have full classification of all those complex Hadamard matrices. So the case n equal 2 is the standard Hadamard matrix we use very often. The case n equal 4 is just the tensor product of 2 real Hadamard matrices or Fourier matrices. For size 3 and 5, there of course exist Fourier matrices, which also belong to this class. However, for n equals 6, this is the first case. Maybe this is not an accident. Then this classification is still not done. So there are many different cases of those complex Hadamard matrices of size 6. But nobody knows whether a new species may exist. We run such a catalog of complex Hadamard matrices. If you are interested, you can visit our website here. And especially if you find a new complex Hadamard matrix of a small size, like 6 up to 20, please let us know. To summarize this part, this is not an accident, then up till n equal 5, the situation is more or less well understood, both for mutually unbiased bases and those Hadamard matrices, complex Hadamard matrices, which are useful to describe one basis in the other one. But for n equals 6, this classification is still missing.
Carol here.
Yes.
Hi. So
Hello. Is there any Arul? Is there any question?
yes. How does this n+1 result translate to the case of the complex Hadamard matrices? Precisely. I see the word classification, but can you be more precise on that?
Yes, so thanks for the question. It is not like this that one problem solves another one. However, to check whether, let's say, 4 MUPs exist, mutually unbiased basis, you can always first choose the first basis as computational basis, identity, and then you need only 3 Hadamard matrices. Each Hadamard matrix complex will produce a new basis. This is simple. However, what is not simple, you don't only need, like in this case, 3 other Hadamard matrices, but they have to be unbiased with respect to themselves. So it means that H1 times H2 dagger is also a Hadamard, and this is difficult to satisfy. So if we knew all complex Hadamard matrices, it would be in a sense easier to say, we are sure that there is no more than 4 or 3 mutually unbiased bases of size 6, because basically you can say, we scanned all possibilities. But this is still not the case. So as you see, the search for mutually unbiased bases is performed in a sense in the space of complex Hadamard matrices. So knowing this space, it would be easier to find the question about the existence.
Okay, thank you.
Thank you very much.
Thanks.
Now we go to a concrete case of 2-qubit. So a 2-qubit system where dimension n is 2 times 2 is 4. So this is simple. We have 2-qubit systems, like you have two steps, physically 2 systems, but we can split them into 1 qubit and another qubit. And of course, we allow not only separable product states, but also entangled states. Now, this simple bound n+1, in this case 4 + 1 is 5, and of course, for like 20 years, there are known sets of 5 mutually unbiased bases in dimension 4. If you assume that the structure 2 times 2 is given, so physically you say, we split the entire system into 2 parts, and mathematically we introduce the tensor product structure, then it happens that the standard solution, 5 bases, can be split into 2 parts, 3 separable bases and 2 maximally entangled bases. This is the standard solution in H4. Look, in H4, it is not so easy for me to show you the picture of the states 4-dimensional, but what is much easier to discuss reduced states. So reduced states, we take now partial trace over 1 qubit, like say rho B, and look at the state in the first qubit, rho A. So now look, if you have separable bases, then after partial trace, these states are pure. And it's not a great miracle, mystery, that what you get from those 3 separable bases, you get 6 pure states, and they form just 6 points which form a regular octahedron inscribed in the block sphere. So here at this picture, you see the block ball, and there are 6 points at the sphere, and they are just form those triple of bases of operator sigma x here, sigma y here, and vertically sigma z here. And both those points at the sphere, after partial trace, they are doubly degenerated. So those 6 separable bases produced by partial trace pure states, then there are also 2 maximally entangled bases. But so they contain only of maximally entangled bases like states of Bell, psi plus minus, phi plus minus. And of course, partial trace of them, since they are maximally entangled, partial trace will be maximally mixed states here in the very center of the block ball. So there are two such bases. So 2 times 4 is 8. And then it means that this point here in the center is 8-fold degenerated. So in a sense, in short, this constellation, the standard set of 2-qubit mutually unbiased bases of size 4, after a partial trace, reduces to 8 points in the center of the ball and 6 doubly degenerated points at the surface, which form regular octahedron. And this was known, let's say, for, I would say, 20 years at least. So here, I think I should mention the paper of Wouters, who discussed mutually unbiased bases already in 80s. So maybe, no, maybe it's more than 20 years, or maybe already 30 or 40. Another constellation I'm going to discuss, it is symmetric informationally complete general measurement, so SIC. Here we look for n-square vectors in Hn such that they form a simplex. What it means that the scalar products for all I and j are the same. This is a normalization constant. Anyway, for n equal 2, it's easy to see you need 4 states, and they have to have the same overlap, so they will form a regular tetrahedron inside the block sphere. So this notion goes back to the paper of Zauner from 1999 and later by Rennes and others from 2003. Why this is important notion? Because if you have such a measurement, it's informationally complete. In this case, you have 4, in general, n-square vectors. So after such a measurement, you get exactly n square minus 1 because of normalization numbers enough to infer full information about the measured state. Therefore, they are called informationally complete, because you can get full information from any state by such a measurement. And of course, they are symmetric because those overlaps are the same. In mathematics, they are called equiangular structures in the Hilbert space. And interestingly, those constructions are known for many, many, many cases. In the first paper, they were known analytically for dimensions n from 2 to 24. Then many researchers found many cases up till, let's say, 400, later 800. Now there was a new discovery of such a constellation of dimension more than 2000. However, there is still an open question whether such SIC, POVMs, generalized symmetric measurements, exist for any n, for arbitrary dimension. This is still an open problem. Even simpler problem is open. Can you construct an infinite family of such configurations? So not to discuss it for every n, but find at least one infinite family going to infinity. It is still unknown. So here again, you see this simplest structure for n equal 2, when you have very nice pattern, regular tetrahedron. Moreover, there is a nice relation to group theory. Basically, it's enough to find one single state, so-called fiducial state, and take some group, in this case, it's kind of rotation group, which will, knowing this state, will transform this state into other states. So in the ball, this is relatively simple, but in higher dimensions, the space of all states is not a ball anymore, and therefore those rotations have to be chosen in a clever way. Now, another notion. In the title, I use the word T-designs. So what is a design? Again, it's a discrete set of numbers, points, in our case, pure states. And it's such a specially chosen ensemble of pure states, such that if you take any reasonable function, like polynomial function of the degree at most t, so this is this function, and compute the average value of this function among all m points which form this design, then this average value is exactly equal to the average value of the function integrated over entire set of pure states. In this case, this is so-called complex projective space of site n-1. So look at this example expression again. So DFS means the Fubini study. This is just standard measure you integrate over the space of pure states. And basically it means that this set is such well chosen that the average value, discrete number, average over discrete numbers of points gives us exact result for the integral. So this is the idea. So in a sense, it's like well-chosen set of points to compute the average. So this is known, for instance, for the sphere, they are called spherical designs. For pure states, they are called pure states designs. And then two designs are a simple case that it means that if you take a linear function or a polynomial of order 2, then, this average is equal to the integral. And here it happens, okay, again, it's not an accident, that those examples I discussed before, mutually unbiased basis and 6, they are just example of two designs. So those designs, in a sense, they are sets of points which are cover the space in some sense uniformly. Well, like here you see there are 4 points which cover uniformly entire sphere as uniformly as possible for 4 points, and then the average value of such a function will be equal to the integral. So the idea under design is a set of well spaced points which are occupying entire allowed space in a sense optimal way. They are not clustered together because then it guarantees that the averages function is equal to the integral, and then the larger t, the more points you need, the larger t, then you want to approximate higher order functions, and then basically the number of points m has to be larger, but in general it is not clear what will be the minimal number of n to reach the design of order t. Here, maybe I will emphasize it again. The larger t, the better a design approximates the entire set. And then for more functions, this condition holds. So let me now make a short pause and ask you, is this concept, is a very important concept, now used in many, many applications? Is it clear to you? I will have a sip of tea, so please let me know, is it clear enough? Are there any questions concerning design and T design? T is just number. By the way, you can ask, well, I told you about two design. What about one design? One design is too simple. Any basis, any orthogonal basis forms a one design, which is also good. So computation basis 1, 2, 3, 4, 5 up to n, it's already one design. So going back to this case, if you have 2 points, here state 0, here 1, it's already one design, which makes sense. You have 1 point at the sphere and second antipodal point, it's already one design. Now if you take 4 points, you have a 2 design. So you could think that maybe 8 points is enough for a 3 design, which is also correct. It's enough to have a cube. But then later it becomes more complicated. But in a sense, the larger T, you need the more points to make a design, but the price is, or the reward is that this equation holds for a larger class of functions T. So, are there any questions?
So, Carol, for t equals 2, is n squared the minimum number that is required?
So, for n equal to, several well-known constellations like mutually unbiased basis and SIG belong to those classes, but there are also other designs. So you can find many other designs which exist, but I'm not sure whether it is known for general dimension n, what is the minimal size of such a 2 design. So of course for qubits and qubits this is known, but for higher dimensions I'm not sure. And you would like to have as small number of points as possible to guarantee, let's say, 2, 3, or 5 design. This is the goal.
Okay.
Just for curiosity,
Yes?
I'm asking this. So the Pauli matrices, they form a Clifford algebra of 3 elements. Higher dimensional Clifford algebra with many elements. Like how you showed complex Hadamard as a generalization from 2, 2, 3, 4, etc. Like that,
Yeah.
Pauli matrices give you a MUB, And then Clifford algebra, has it been investigated for MUBs or any other designs? For example, a 4x4 Dirac matrices, gamma 1, gamma 2, gamma 3, gamma 4, gamma 5 in that language, they form a Clifford algebra. You showed 5 bases for that. So I was just wondering, do you have any answer for this?
Okay, nice question. So, okay, again, I would say that in smaller dimensions, a lot is known. A lot things become unclear for higher dimensions, especially those products of Pauli matrices. Indeed, they work for 2, 3, 4 qubit system for dimensionality 2 to power k, let's say. But of course, it will not solve the problem for n equals 6 or for, let's say, n equals 7. So for other dimensions, yes? But today, indeed, I will now discuss the simplest case, 2 qubits, for which everything basically is as simple as possible, but still you can find nice questions and nice answers for them. So here I will mention the following fact, that exactly one of those functions you can take in a sense like purity of partial trace, and then by the condition that we have a 2 design, then look what is here. Here is a pure state of, let's say, 2 qubits. Now we take partial trace, so it's a mixed state, and then take the trace of this square. So this is a squared function, which basically tells us about linear entropy of entanglement of this initial state. And now look, it's easy to compute this quantity, which is a function of n. So what it means, that for entire constellation of states which form the design, the average entanglement is fixed. So you can have some separable bases, some entangled, but as average entanglement is fixed, it's a clear argument. You cannot have mubes, 5 mubes in dimension 4 only composed of separable states, because then the entanglement would be 0. Neither you cannot have them construct for all only from entangled states. So here this situation, 3 entangled to 3 separable 2 entangled gives us the average entanglement, which gives the result according to this expression. Now I will mention a paper by Zhou and Englert from Singapore. They found a very interesting constellation of exactly 16 states forming a SIC, so the symmetrically informationally complete measurement for 2 qubit system, such that, look, entanglement of all such states is constant, as should it be. So this is exactly this number 4/5. So all those states have the same degree of entanglement, and they can be obtained from a first, let's call it fiducial state, by local operations, because they share the same entanglement. So this is the main advantage of such a scheme. It's enough to construct one fiducial state and then get all others of the same degree of entanglement by local operations. So this was a nice result by Zhou and Englert concerning SIC. And then one can pose a simple, similar question for mubes. So the question we started is there a similar configuration for the full set of 5 iso-entangled mubes or for 2 qubits? So standard mube solution I showed you for n equal 4 consists of 3 separable bases and 2 maximally entangled. And we ask if it's possible to find solution with 5 bases of the exactly same degree of entanglement. Is this question clear? Now, again, why we care? Well, in some cases, it would be nice to have this one fiducial vector and all other vectors. So together we will have 5 times 4, 20 vectors of the same degree of entanglement. And here it is. The answer is positive. And we are very pleased and proud that we managed to find this answer in a relatively simple form. So look, here is, okay, it's not too complicated, not too simple. I don't ask you to memorize the formula, but somehow to appreciate that it's given in simple numbers. So you see, this is a simple state of 4 qubits. You have 0, 0, 0, 1, 1, 0, 1, 1. And the expression is relatively simple. So you have some i's, square root of 5, and so on. By the way, Arul, you see the square root of 5 1 plus minus square root of 5. You know this number.
Yeah, and you have the golden mean there too. Looks like.
Yes, yes, yes. But somehow we didn't emphasize it so much. But as you see this number, of course, Aaron knows well. We also know that number 1 plus square root of 5 over 2 is golden mean. So, well, it's a very, very special number which appears here and there since Greek times, since, let's say, Plato, yes. And in short, if you take one such a state, now you can explicitly write down those local unitaries, and all other 20 states can be obtained from this one by local operations. So eventually you get 20 pure states, which are locally equivalent, which form 5 bases, and they share the same degree of entanglement. What it means that if you take partial trace, so this is partial trace, you get states of the same degree of entanglement, which means that after partial trace, they will be, of course, inside the block ball, but they will belong to a sphere inside the block ball because they will have the same radius. So this result was presented in the paper with Jakub, Dardo, and Marcus a year ago. And look, here it is. So what is here? Mathematically, you could say this is compound of 5 tetrahedrons. Now look. All those tetrahedrons are regular, of different color. They intersect in a very special way, in such a way that the angles are equal. You can see here, for instance, you have a structure of 1, 2, 3, 4, 5 colors. And if you take those 5 points and join them together, you get a regular pentagon. And then the convex hull of this figure, you can guess what it is? Who knows? Of course, it belongs to Platon in a sense. What you get? What is the convex hull of this? Simple question, but I forgot I gave you the answer here. Of course, the famous regular dodecahedron, yes, because we will have only all sides, faces are pentagons. However, what is most interesting here, that each color represents a given tetrahedron, which represents a basis. So it represents 4 states which were orthogonal before partial trace in H4. So each color represents a given basis, and this convex hull of this forms a regular dodecahedron. By the way, there are different dodecahedrons known in quantum theory. There's a famous one by Penrose, other by Zimba, but this is not exactly the same. So of course, dodecahedron is the same because there's one of Platon, but the somehow motivation and formulas are different. So you see, the fact that those all bases are iso-entangled or equi-entangled means that after partial trace, all those points are equally distant from the center. So it means that they belong to a single sphere. And again, you see what means a design. Design means that all those points are, in a sense, equally distributed over the sphere. So here is my main author, Jakub, who really produced this, you see. So he really was careful enough to produce this object. So it's not so easy as you can guess because they intersect in a strange fashion, and he produced such a figure. And if I were in India, I would take it with me to show it on the site. Maybe next time I will take it. You can put it into the box, and somehow, strangely enough, it is still stable enough, this nice object. And now we go to mixed states T designs as a last part of the talk. So in quantum theory, we use projective designs formed by pure states. There are also unitary designs formed by unitary matrices. Definition is simple. You take unitary, you extend it by 1, and you act on the pure state, and you can get another design in a sense. There are also spherical designs. There are other notions. I will mention conical designs by Graydon and Appleby, mixed designs by Brandsendal, Arno, and Shimusiak. And in fact, all those cases are special cases of very general mathematical construction of averaging. Here, I think the most important paper is by Seymour and Zaslavsky from '84. So the formula is very simple, but now the setup is much more general. You take any measurable set omega, a reasonable measure mu, and you say that integral of a given function ft, let's say of some order t, has to be equal to the average with respect to m points which are placed in an appropriate way in the set omega. So this is the general idea of t-design. But look, it means nothing else as approximating of an integral with average value. So maybe, you know, for 200 years, we had like different rules of integration, approximate rules like of Gauss, D'Alembert, Laplace, and others. And in a sense, you can ask, is it possible that those approximate, here you have approximation of an integral, those approximations are exact. So you ask for such functions and such choice of points for which those simple approximate formulae known for 200 years are exact. So now we go to the new idea of mixed states designs. So we will apply this idea for the set of all mixed states. So omega n is now, for me, a subset of L to power n squared minus 1, which denotes the set of all mixed states of size n. And now we assume there exists this flat Hilbert-Schmidt measure, d rho, which is related, like if you have a n equal to, you have a block ball, so it corresponds to the standard flat measure dx, dy, dz inside the ball. So now the definition is, well, very simple. So we take now a set of m density matrices, and they will be called mixed states t-design. If for any polynomial I change now to g, so g is this function of order t, which acts on density matrices, the average value over the set of m points, our design, is equal to the average over the entire set of mixed states with respect to the Hilbert-Schmidt, so flat measure. As simple as that. So the idea is, again, the same. You want to find such set of points that the average value of a function g is equal to the integral over a full set of all states. As simple as that. Why we care about it? This could be a good tool to compute averages without integration. So you want to have kind of, instead of integration, you want to exchange sometimes complicated integration into a summation which has only finite number of terms, and it's much simpler. Well, so now some results. Very simple. Look, let's assume we have a complex projective design of order S. Now I change the letter. In the complex Hilbert space of size n times n. Now I take partial trace. I take partial trace and I get the set from each pure state of size n squared. I get a mixed state of size n. So the theorem says that if you start with complex projective S design in dimension S squared, so take partial traces, they will produce a mixed states T design where T is at least equal to S, can be larger. And of course, the same property holds if you take partial trace over not A but B, because this is a symmetric case. And then, okay, I will not go too much into details, but how to prove this fact, but it's somehow it's related to the fact that if you have the Pubini study measure of the set of pure states, so this is how unitary invariant measure, and perform partial trace, this induces the flat Hilbert-Schmidt measure in size in the set of mixed states. So if you take pure states of size 4, perform partial trace, if the states, pure states are random, you get uniform distribution inside block ball, inside the standard block ball of size, well, 3-dimensional ball for dimension 2. This is a very simple and nice fact, and we use it in the proof. So now, observation is simple. If you take a standard measurement, then they perform partial trace. This induces a one design, which is rather simple. So by center of those points coincides with maximally mixed states. So the center of the ball. Now, you can ask, well, if you have the set of M states, how to check if it's really a design? So here we have a constructive result. We use so-called Welsh bound from the classical combinatorial theory adopted by Scott in 2006 to quantum mechanics. And in a sense, it's enough to compute some integrals. But here now I take raw power. Look, it's a tensor power of order T of rho. And then I have to check whether some inequality is saturated, but basically this is a constructive way. If I have obtained the set of from U of M states, I can check whether such a inequality is saturated. If it is so, I know that this set is really a design. So to show you some examples, if I take a standard constellation, let's say of sig pure VM, formed of 16 pure states of size 4, I take partial trace. On one side, I will get a nice cube. So again, 8 points inside the block sphere, but they belong to a sphere. And they also form a design inside the block ball. Here is if you take another partial trace, you get another object. As you see, it is not as symmetric. So basically, this is obtained from those results obtained by Zhu and Englert. Okay, there's a nice example of Hogarth, but I think I have to skip it, and I will return to our construction. So we had this construction of 20 pure states of two-qubit system, which form our iso-entangled mu. Now we take partial trace. We take partial trace, and we get 20 points inside the block ball. So since this mu was a 2 design in the space of pure states of size 4, our theorem says that immediately we know that this constellation of 20 points inside the block ball forms a mixed H2 design. However, we can prove it is not only 2 design. You remember the theorem says that S can be larger than T. Here, in this case, sorry, T can be larger than S. In this case, we can show that this object is already a 3 design, so it has a better averaging properties. Well, I will only show you now, go back to a much simpler example. If you take an interval from 0 to 1. So here is a basic of integration. You want to have integral from such a function, let's say polynomial, with respect to the, let's say, flat measure, and you want to choose m points such that this equality holds. So the average value is equal to the integral. So you can look for such constellations of points for which this holds for a given number of t. And here it is. So you have an integral from 0 to 1. So to have 1 design, you put 1 point at the center. To take 2 design, you have to put 2 points here. To have 3 design, you have to put 1 in the center to here, and those positions here are exactly known. So here it's easy to find. It's a very nice structure, constellations of endpoints on the interval, which provide t design from 0 at the simplest possible question at the interval from 0 to 1. Okay, you can also do it for other measure, but I will, I think, skip this point. Okay, and now I want to show a relation to the classical heroes of mathematics. So you know there's this standard integration rule of Simpson along the interval, where you have to give the weights like 1, 4, and 1. Or there is a Gauss-Legendre rule where you have 2 points with the same weights. So what is the relation to quantum physics and geometry of quantum states? Well, if we take now our design, which corresponds to points at the inside the block ball, now we can ask what happens after decoherence. Decoherence, well, it means that you project the sphere on the axis. So from those 4 points at the corners of the octahedron, you will get after decoherence 4 points here. So in the center, which you can now plot here, and you get 2 points which do not decohere, they are already classical. So the weights 1, 4, 1, corresponding to the Simpson rule, correspond just to our 2 design represented by octahedron inside the Bloch sphere after decoherence. However, of course, the same design you can orient in a different way. If you now orient it in such a way, you have 2 faces with 3 points here, After decoherence, they will make 1 point, blue point here. The same happens with 3 points spanning the second phase. So you have triple degeneration here, triple degeneration there. So you have the same weights. And now those positions of those points correspond exactly to the famous Gauss-Legendre integration rule. So therefore, it means that the quantum designs after decoherence, where we go back to the classical states represented by an interval from 0 to 1, correspond to well-known integration formula, integration patterns, and our designs can be seen to be as special cases of integration rules. So sorry, I see some question, but let me finish now because time. I will look at the question later on. Okay, I think I have to. Well, so just a simple statement that if you have a pure design and in Hilbert space and allow for decoherence, you will get the design in the simplex of eigenvalues. Yes, and I think I will skip the last issue concerning single-sided distinguishability. Well, so you have a following question. You have composite system, and you want to find such a basis that after partial trace, all partial trace you can distinguish as much as possible. For instance, they form a design because they form a simplex. The Hilbert-Schmidt or better trace distance is as large as possible, and this is so here is a solution related to so-called elegant joint measurement problem of Giselle. So here are 4 states of 2 qubits that after partial trace give us again a nice tetrahedron which is as large as possible, provided those pure states of 2 qubits were orthogonal. So here is the same constellation for n equal 9 states for 3 times 3 system, but I think I should, and this is related to the paper of Giselle, but I think I should conclude. So first I would ask you to study a little bit of classical combinatorics, and then I suggest that all your knowledge you can learn, you could invest and you could use for quantum case. So instead of combinatorial designs obtained from classical numbers or digits, you replace them by quantum states or by operators. And if you put them in nice constellations, they have some direct physical applications because they form some nice measurements. I want to convince you that we found a nice configuration of 20 pure states of 2-qubit systems, which form the full set of isoentangled groups. And after partial trace, they form a dodecahedron, 20 points, inside the Bloch ball, which forms a special configuration. They form the mixed states to design. So design in general is a configuration of points with special properties, that the average value of some functions is equal to the integral. Usually you have states and integrate over pure states. Here we introduce mixed states designs and show how to obtain them. And we found a relation between designs in the space of mixed states, pure states, and after decoherence, designs in the probability simplex. And I will finish with a simple statement that even though for the last, let's say, 20, 30 years, people worked a lot about those problems, there are still many interesting questions. For instance, you can ask for what dimensions seq is known, and you can ask is maybe another question of those elegant joint measurements I mentioned at the very end. Now we found analytical form which bases on the construction of seq. So for those dimensions for which seq is known, our construction works, but in general, this question is slow. Thank you very much. Thank you for your attention.
Thank you, Professor Karol. So we have only a few minutes left. So one or two quick questions, panelist or the attendee.
Yes, but there was a question in the chat. There was a question somewhere, but I missed it. So maybe, I think there was Tamoy who wrote a question. Maybe you can read it for me because I skipped it.
Okay, yeah, I can read it for you. The minimum size
Yes.
for a 2 design, one could perhaps use a lower bound using a unitary 2 design. And he continued to say that in the case of unitary, he continued to say, in the case of unitary T design, there are notions of asymptotic approximate designs concept. You start with an ensemble of unitaries, randomize over the time. I mean, k infinity limit. You could get a perfect unitary design. Is any such notion possible for the positive designs, projective designs, or a mixed state design, or other types of design?
Very nice question. So to be short, my answer is very simple. I don't know. So okay, again, something could be known for very small dimensions, but in general, already for, let's say, dimensions of order 3, 4, 5, and t larger than 3, not much is known. And I think it's another good question, good problem to work on. But thanks for the question. I appreciate it. And strangely enough, it may happen that for asymptotically something is known, but some asymptotic properties. But somehow in the mean, there's a lot of open questions.
Okay. If there are no more questions, maybe
I can ask one.
Yeah, sure.
One more quick question. So thanks, Carol, for the very interesting talk. I really like the analogy that you did, like the geometric analogy to the Platonic solids. And I was wondering, so you showed us basically situations where we were able to obtain, when we projected everything onto the Bloch sphere or the Bloch ball, we were able to obtain like a tetrahedra, we were able to obtain a dodecahedra. But I know that there's only 5 Platonic solids. Right.
Yes.
And so the largest one is the icosahedron. And so does this impose any constraints on the structure of quantum states in higher dimensional Hilbert spaces?
Very
and in particular,
yes, please. No, but in a sense, maybe not imposes constraints, but in other words, it's easier to find some solutions, let's say for some dimensions which fit to the Platon solution.
Right. Exactly.
It only shows that if you have, let's say, 23 or 27 dimension, somehow the things will be more and more complicated, and therefore, because there are only 5 of them, you easily see why those problems stated for arbitrary dimension are so complicated. But this is related to the famous mathematical problem. If you have a sphere and want to place k points in a, let's say, equally, like it's called spherical design. And again, for some special magic numbers, solutions are known, and for some not.
I see. Okay. Yeah. Thanks.
Thank you. Thank you, Marine. So I think I will thank you again, and I have to unshare the screen. Just a second. I forgot how to do it, but maybe yes. Stop sharing. Yes. Thanks again.
Yeah. Thank you, Professor Karol. Yeah. Okay. So we move to the second talk of the post-lunch session. I request the volunteer. Okay, it is already shared. Okay. So the next speaker is Marine Bukov. He is from with Sophia. Marine got his PhD from Boston University, USA, and he was a postdoc before moving to Sophia at University of California, Berkeley campus. His interest includes quantum condensed matter physics, quantum simulation, quantum optics, machine learning, and computational physics. I request Professor Marine to begin his lecture. Yeah.
Thanks a lot for the nice introduction, and thanks also for giving me the opportunity to present some of the results that we recently obtained here at this nice virtual conference. The organizers asked me to present some of our research on machine learning and quantum technologies, and so I thought that a nice work to show here would be this collaboration with Jiahao Yao, who's a graduate student at UC Berkeley, and Professor Lin Lin, who's also at UC Berkeley. So we have like a series of papers on that, and I'm mostly going to focus here on the red one. But you should feel free to check also the others if you find this interesting, and then I'd be happy to answer any related questions that you might have. Okay. So today I'll talk about reinforcement learning for many-body ground state preparation, which is based on counter-diabatic driving. And I am aware that a lot of these words are not familiar to everyone in this audience, and so I'll try to introduce things one by one as we go forward. Okay, so this talk is going to be about quantum simulations. As I'm sure you know, quantum simulation is one of the 4 pillars of modern quantum technologies. Modern or present-day quantum simulators, they are closed, isolated, highly controllable AMO platforms. And here I've shown you a few examples of such platforms. So these could be ultra-cold atoms or photonic insulators or maybe superconducting qubits. And one interesting common feature of these systems is that they all contain many degrees of freedom. So in the case of ultra-cold atoms, there's this optical lattice, and in the optical lattice, we have multiple interacting degrees of freedom. In the case of photonic insulators, you can see the waveguides, and in every waveguide, you can shine photons. And then, of course, due to evanescent coupling, the photons in between different waveguides talk to each other. And also, you know, the superconducting qubits, they form the basis of quantum computing. And of course, we know that one of the major challenges there is to understand and to harness quantum entanglement, which is also due to interactions between particles. But one common feature of all these platforms is that they present non-equilibrium systems, in the sense that whenever we want to probe or measure some quantities there, we typically have to do this using non-equilibrium protocols. And this actually makes them harder to study, because we need to figure out ways to manipulate and control systems taken away from equilibrium. And this is not necessarily an easy task. In fact, it's actually quite a difficult problem. And here I've listed only 3 just very simple reasons for this. You know, if you just put non-equilibrium aside and you only think about equilibrium systems, when they are many-body systems, then typically there's no closed form expressions for the eigenstates and eigenenergies. What this means is that we have no analytical control over the behavior of these systems, unless, you know, there's some extra conservation laws, symmetries, etc. But for generic systems, this is, as we know, not the case. Now, when we take systems away from equilibrium, even if they're not many-body, even if they consist of a single qubit or 2 qubits, then we are faced with another problem, namely that there's no solution to the time-dependent Schrödinger equation. And it is the time-dependent Schrödinger equation that describes quantum systems away from equilibrium, at least closed quantum systems away from equilibrium. And then, of course, you know, talking about how to manipulate these systems, then a natural question would be how to do this in an optimal way, in a best way, in the fastest way, for instance, etc. And so there's a fine interplay between the control and the physical degrees of freedom in the system that also has to be understood in order to do that. So there's many challenges, and today I'd like to focus on one of them, namely how to prepare ground states of many-body spin chains. So here's, for instance, a spin chain upon which I can shine some laser light in order to control it. And so my goal would be, for instance, to start from some easy to prepare product state, and then try to transfer the population of my system into the ground state of this Hamiltonian, because in a quantum simulator, I would actually like to study the properties of that state. Okay. And the way we're going to do this is we're going to use quantum or variational quantum eigensolver based on reinforcement learning. So this is something that I will introduce in the talk. I will briefly explain the policy gradient algorithm and the deep autoregressive neural network structure that we use in order to do this state preparation. I will also mention an extension of the quantum alternating operator ansatz, which incorporates the adiabatic gauge potentials. So these are control terms that will allow us to easily and in an optimal way prepare the state in many body systems. So I'll explain how this works. And then in the end, I'm also going to show you very concrete examples. For instance, how to compare, the algorithm that we'll obtain against simple QAOA or against other variational counter-diabatic techniques using a quantum spin chain. So, for instance, Heisenberg and Ising models. Okay, so if I'm going too fast or if there's anything you'd like to ask right away, please feel free to just jump in and ask a question. Okay, so to begin with, let me just set up the stage by telling you what the ground state preparation problem is in terms of a very simple system. So let me just get rid of the complicated many-body character and just consider a single qubit. As we know, the state of a single qubit can be described on a Bloch sphere. Now, the Hamiltonian of my system is given here, and it will have some time-independent term and some time-dependent term, where the time-dependent, say, magnetic field along the x-axis is given by this unknown function h of t. So now suppose that I can prepare the system in my initial state, which here is shown as a green arrow on the Bloch sphere. And the goal of my system is then to find a function h of t, an optimal protocol, such that after some fixed amount of time, capital T, I can transfer the population from the initial state into a target state, shown here in red. And the target state can, for instance, be the ground state of some Hamiltonian, in that case, you know, a Hamiltonian where the external field has a specific value of +2. So as I said, you know, the task here is to find out of, you know, a variety of different protocols to find that one that does the job in the fastest possible way. And so if you gave me two protocols and I need to tell you which one of them is better, then one quantity that I can look at in order to do this is, for instance, the energy expectation value of my evolved state in my target Hamiltonian H star. So notice I take an initial state, I evolve it following this Hamiltonian for a fixed protocol, right? And then I can measure how far away am I from the ground state. But I can, of course, change the protocol, and then I'm going to get a different number. Now, what we know is that there's no state in the Hilbert space that lies lower in energy than the ground state. And so therefore, I can use this energy function as an optimization cost function, where I try to change my fields in such a way as to get closer and closer to my target state. Okay. And of course, you know, I'm showing you this using a simple description of a two-level system. The whole thing, of course, applies to more complicated systems, as we'll see later on. So now the question is, okay, so there's many ways to choose this external magnetic field, or this external control function, control parameter. One very useful way of doing this that was established over the last decade is the quantum alternating operator ansatz. So suppose that you can decompose your Hamiltonian in two non-commuting terms, H0 and H1. For instance, H0 can be the kinetic energy, H1 can be the interaction energy, etc. Now, the QAOA ansatz for the control protocol is such that at any given point in time, only one of the two Hamiltonians, H0 and H1, can be turned on. So for instance, here, only H0 can be turned on, then only H1, then only H0, then we go back to H0, H1, etc. So in particular, we do this in an alternating fashion where we flip or switch between H0 and H1 at every step. What we don't know, however, is how long we should be applying these Hamiltonians for in order to prepare our state. And so this ansatz results in a generic unitary operator, which is parameterized by these variational angles, alpha and beta, which you can think of as angles in your gates, or you can think of as time or whatever you want. And because we're dealing with a many-body system where H0 and H1 are extensive in the number of particles, I would like to impose the constraint that the total time, if you wish, for my operation is also fixed, and I will use this parameter to study that system. Okay, and so, you know, once we have, you know, fixed our kind of protocol, then we can also now compute the energy, and the energy becomes now a function of these variational parameters. And so in QAOA, what one tries to do is optimize the energy for these parameters. So we're basically trying to minimize this quantity here as a function of alpha j and beta j under the given constraint. And this gives us the unitary process that we need in order to get as close as we can to the ground state of our system. Okay, now this is all nice, but as you know, you might have already noticed, you know, in QAOA we only have two unitary gates. So these could be, you know, H0 and H1. And if you have two unitary gates, then the sequence that you can apply them in is always fixed. So either we start from U1 and then we do U0 and then we go, you know, in an alternating fashion, or you can start with U0 and then you do U1, etc. So there's only two sequences. But the question that you can ask is, whether potentially you can do better by choosing the sequence of gates as well. So consider now a system where you had like 3 unitaries, right? And each of them can come up with its own degree of freedom, alpha, beta, and gamma. You can ask the question, can I order them in a way that produces a better result than if I only had 2 unitaries, right? And as you can see here, this is an optimization problem that contains 2 parts. The first one is the continuous optimization problem relating to the angles alpha, beta, and gamma of the unitaries. You can think of the time durations as I showed on the previous slide. But now, in addition, we also need to find the optimal gate sequence, whether it's going to be U0, U1, U2, or U0, U2, U1, etc. And of course, we can repeat these guys up to some fixed length Q. So there's like these 2 problems. There's the continuous optimization problem that was essentially solved like with QAOA. And now, in addition, however, I would like to impose a new problem, a discrete optimization problem. And it turns out that when you have like a discrete optimization problem, then a well-suited class or framework of algorithms to help you understand its structure and how well it can be solved is reinforcement learning. So this is how I make the connection for why reinforcement learning can be useful in that specific setup for quantum control. So, okay, let me try to explain to you briefly what reinforcement learning is. So in reinforcement learning, we have an agent, and this agent is supposed to learn how to perform a specific task by interactions with its environment. So for instance, this task can be a manipulation task or a control task. Now, in reinforcement learning, works in a feedback loop. At any given step, the agent is supposed to take an action from a set of some available actions, right? And this action is going to change the state of the environment. As the environment changes state, there will be some feedback signal. In this case, we call this a reward that will be given back to the agent. And so the next time the agent has to choose an action, then it will look up, like its rewards, and it will say, okay, it's better for me if I took that action because then I can, get a better and better reward. So the goal in reinforcement learning is to maximize the expected reward. The interesting thing about this class of algorithms is that they assume no model about the physical system, so you don't need the notion of a Schrodinger equation, etc. So the optimization happens in an independent way from the actual dynamics of the system. So let me dive a little bit more into the details. So in order to formalize this, in reinforcement learning, we need an action space. Here's one application that you can think of. For instance, you want to teach your computer agent to play a game. This was done by Google, I think, almost 10 years ago, maybe 8. So suppose that you want to play this game of breakout where you have a pad and then you have a ball and then there's bricks, and what you want to do is you want to break all the bricks, and this brings you score. So how do we frame this in terms of reinforcement learning? So there's an action space, and the action space can be to move left, to move right, or to leave the paddle where it is. Then there's going to be a state space because the environment is in a certain state. And this state space in this case can be just the pixelized image of the screen, but it could be like a quantum state, for instance, as we'll see, etc. And then there's the reward space, and the reward space in this example is just the score. And now, what reinforcement learning is, it's essentially a Markov decision process. So we all know what Markov processes are. If you have a chain of states and you're given a transition probability where you can go from state S to state ST to state ST plus 1, then this happens according to this dynamics rule. But now a decision process is a process where this transition probability can also depend on an action that you've chosen. And moreover, you're choosing this action with another, or according to another probability called the policy or the strategy of your agent pi. So while the transition probabilities are basically set, by the world that we want, by the environment essentially, by the world that we live in, and they're fixed, they cannot be changed. The policy or the strategy is something that we have control over. And so, for instance, you can ask the question, what is the optimal way of playing this game, or what is the optimal way of preparing quantum states? So whenever we have that, whenever we have such a transition from state S to state ST to state ST plus 1, we're also given, as I said on the previous slide, a reward for this transition. And then the objective in reinforcement learning is to maximize the total expected return, or the sum of the rewards, following some policy pi. Okay, so how can we do this maximization? So this is the definition of the quantity that we want to maximize. It contains this expectation value, and this is expectation value over such trajectories. Now, as we know from statistical physics, whenever we have a lot of possibilities, a lot of combinations, then evaluating this expectation value is similar to evaluating a partition function. So we can't really do this in interesting cases exactly, but what we can do is we can sample it. So you can imagine that, I start from some initial state, and then following the policy, I basically draw these transitions, right? And then I obtain a trajectory, which is a sequence of these states and actions. And so if I do this procedure many, many times, I can obtain various trajectories, and I can get the rewards over various trajectories. And this average Monte Carlo sampling, if you wish, will give me an estimate, which, if I do this often enough, will essentially converge to the quantity that I would like to do. So this is now how we evaluate the objective. But the question is now, how do we actually improve the policy, right? So how do we make sure that this pi becomes better, that gives us a higher objective? And one thing one can do first is one can parameterize the policy pi using some variational parameters, theta. And these variational parameters allow us now to compute the gradient of this quantity j, right? Now it becomes dependent on the parameters theta with respect to these parameters. And it turns out that there's a nice expression which allows us to also use our samples of trajectories in order to directly evaluate the gradient of the policy with respect to the parameters theta. But now that I have a gradient, then it's very easy to do gradient descent or gradient ascent in that case, and update the parameters of the policy. So this structure here allows me to now also improve my policy, so become better and better at preparing my quantum states as I run this feedback loop. Okay. So now let's get back to this picture, and now let me tell you how one can actually frame the quantum control problem, or one way of framing the quantum control problem in the reinforcement learning setup. So once again, here we have an agent. We know how the agent should learn in terms of this policy gradient. Now, the agent is supposed to take actions, and the actions, in my case, are going to be these discrete unitaries, U0, U1, and U2. So these are like discrete actions, right? But every unitary comes up with its, with its own duration angle that, as we know, in QAOA has to be determined. So the agent first has to choose a unitary to apply to the environment, and the environment is given by the quantum system. Okay. So now, so these are the actions. Now, in the reinforcement learning, I said I also need to define the states. And here comes the problem for us, because if we want to have absolute control over the system, we actually need to use the quantum states. But quantum states are physically not measurable objects, right? So quantum states are very important and useful mathematical constructs to understand quantum mechanics, but you can, unless you do full tomography, and we know for many body systems this is not so easy, you can't really have access to the quantum states. And so what you can have access to, however, is the sequence of actions that you apply. And so for this reason, in our setup, we choose to label the reinforcement learning states with the sequence of actions. So for instance, the state at time step 0 is just the first action, the state at time step 1 is the first action and the second action, etc., as we go forward. And finally now, the reward function is just the negative energy density, the quantity that I want to maximize, right? So I would like to minimize the energy, I want to maximize the reward, therefore there's a negative sign here. Notice that I cannot measure my quantum state arbitrarily, because every measurement, I imagine destructive projective measurements, every measurement is destructive, and this would mean that I would have to restart my my cycle, optimization cycle from the very beginning. Therefore, I'm going to impose the constraint that I can only measure this reward in the end. And so what this means for me, or for my agent, is that the agent will be constructing these sequences, optimal sequences, one unitary at a time. But at the end, the sequence is there, but what we don't know is what the angles the optimal angles for the sequence are going to be. However, QFA tells us that if we have, this continuous optimization problem, we can use some solver or something else to find these continuous angles. And then once we found the continuous angles, then we have everything we need to know about our protocol, and then we can actually do the measurement and obtain the negative energy density, which is the reward of the agent. And so then the agent starts again from the beginning and does another feedback loop, et cetera, et cetera. So that's how we frame reinforcement learning, quantum control in terms of reinforcement learning for this talk. So now I've told you everything except what this policy actually is, and that's the final part that I need here. So as I mentioned, we can parameterize the policy using some variational parameters theta, and this can in principle be any function. As long as this is a probability distribution, right? This was one of the constraints that the policy is the probability to take the action A if you're in the state S. So, in light of recent developments in deep learning, you can also try and use a more complicated variational function approximator for theta, which could consist, for instance, of some deep neural network. And then, depending on the problem of interest, you can try and make this ansatz as suitable to your problem as it can get. Now, in our problem here, when it comes to quantum control, one feature that we would like our policy to be able to do is we would like to have causality. And this is important because, as we said, the agent will be constructing these sequences one step at a time. But of course, the optimal unitary that I apply at step 5 will depend on the unitaries that I chose before. And therefore, there will be some causal relation. So the question here that we have to answer is how can we build in this causality? How can we build this causality into our model? And luckily, computer scientists have prepared a class of variational ansatzes for this, which go under the name of autoregressive models. So this is what I'd like to explain here. So at the first time step, we start with some neural network parameters, let's say some training parameters, some nonlinearity, etc. And then we would like the output of this neural network to be a probability distribution for picking up for picking up the first action A1. So each of those cells, you can think of the probability, for instance, for picking A1, picking A2, A3, A4, etc. So we have a discrete action space. So this is a discrete probability distribution. Now, if this is a probability distribution, then I can draw my first action from this state. Okay, and this is now A1. Now, in order to build in causality, I'm going to use this action A1, which is now a concrete, very concrete action chosen, in order to select the second action A2. And to do this, I'm going to put this into a similar layer of the neural network. And this layer, notice, will know about what happened in the first, about the parameters of my first layer. And so at this stage, at the second stage, I have a probability to pick the action A2 conditioned on the action A1 that I picked in my first time step. And if I have this probability, then I can also draw an action A2 according to it. And now you can imagine, in the next time step, now I take A2 and A1, and then I put them in there. And so I design a probability that depends on A1, A2, and which would give me the action A3. And so I can pick up A3 and so on and so forth up to, say, the maximum length of my sequence that I allow. Now at this stage, I have chosen a sequence of unitaries to apply to my state, but I haven't determined yet the optimal angles. So now I can use, for instance, a solver, which allows me to find this, perform this continuous optimization, and which in the end, I can use in order to construct the sequence. And having the sequence, I can obtain also the reward. Oops, sorry about that. And as I said, once you have the reward, then you can use the policy gradient algorithm in order to update the parameters of your neural network, again in some closed loop fashion. So that's essentially the procedure. It might look a little bit more complicated, but it really is not. Again, these neural network layers, etc. I can tell you more about the details, but this is really not so important here. What is important to take home from this slide is this causal structure, which is important, as I said, when constructing sequences. Okay, so at this stage, we basically, I basically told you, roughly what reinforcement learning is and how it could be applied for quantum control by using this generalized or extended QAOA ansatz. But what I have not told you is, where are we actually going to get more unitaries to control our physical system? Because typically in Hamiltonians, one finds a kinetic energy term and an interaction energy term, but there's not necessarily any more terms, and it's not quite clear where we could get like extra unitaries. Now, in the era of quantum computing, you can always say, oh, I can take my universal gate set and these could be my unitaries. And yes, you're totally right. So you can definitely do that. But it turns out that if you make this approach in quantum simulation to prepare ground state of quantum many-body systems, then this is actually an approach that won't get you too far, just because there's many different combinations that you can do. And these combinations grow exponentially with increasing the number of quantum degrees of freedom in your system. And so what we'd like to have here is an alternative approach to do that. And ideally an approach which is motivated by the physics of these underlying systems. So I'd like to do like a physics-informed machine learning in some way, such that I can maximize the fidelities, or if you wish, minimize the energies that my agent can get. And so one way of doing this can be stolen or taken from the shortcuts to adiabaticity community, or the so-called counter-adiabatic driving. So I'd like to very briefly explain to you the basic idea. So suppose that you're a waiter and you would like to serve a glass of water, right? Now, of course, you want to do this without spilling the water, because if you spill the water, then your client, your customer is not going to be happy. And so one way of doing this is, to move the tray with the water very, very slowly, and that would correspond, we know, to the adiabatic transfer of the quantum state. In our case, from one state to another, of the population from one state to another. But sometimes, moving so slowly is not really going to do the job, because you also want to, to serve your customers like as quickly or guests as quickly as possible, because this is going to allow you, to serve as many customers as possible, and that way you can maximize your own profit, right? For instance, getting like better tips, etc. But there is a problem. If you move too fast, you're going to actually spill the water, right? And that's a problem. However, if you're an experienced waiter, you know that there's a cheap trick you can use. Namely, what you can do is you can tilt your tray, and if you tilt your tray appropriately, then you can actually move much faster without creating excitations in your physical system. And this tilting the tray has been formalized under this concept of counter-adiabatic driving. So what essentially this means is that you have to apply a counter force in such a way that in this moving frame now, your system will look static, right? And in this specific example here, it's actually easy to get to compute what the counter force should be. In some single particle systems, it's also easy. It turns out that when you have a many-body system, where, for instance, again, you have a Hamiltonian H0 and a Hamiltonian H1, and then you're trying to, slowly turn on H1, or maybe not so slowly now. In order to facilitate your process, you can add an extra term to your Hamiltonian, the so-called adiabatic gauge potential term, that you can compute, for your physical system is going to be some sum of nested commutators, essentially. So if now we go back to our spin chains, then we can, so let's say that, we have our spin chain. We want to prepare the ground state, as I showed you in the beginning, using QAOA, where, the first thing would be to define two unitaries, U0, which is relating to H0, and then U1, which is related to H1. And these H0 and H1, for instance, can be, any combination, for instance, of nearest neighbor interactions and then external fields, or only external fields, etc., depending on the model that you have, right? But now what you have is you can also compute these gauge potential terms that are going to provide these counter forces that to allow us to do the state preparation in a faster than adiabatic way, in a counter diabatic fashion. And one way to think about these gauge potentials, which is I find very useful, is to think of them as some sort of generalized currents, right? And so currents means that you have to have, something imaginary in your Hamiltonian. So therefore, you would have to either have like a sigma y or an odd number of sigma y matrices in your interaction terms. So for instance, this could be just an external field along the y direction, or it could be, an on-site interaction between x and y, or a nearest neighbor interaction between x and y, or even something more complicated. But you can basically list these terms for your system. And now here's, we'll come back to the title of this slide. This is now a way to find extra control degrees of freedom that are especially suitable for your control problem, for your many-body system, and that now allow you to extend the space and ask the question of, what is now the proper way of constructing sequences if I have, for instance, 5 unitaries instead of only 2, right? So that's essentially motivation for this. And I want to say that, this has also been applied to a quantum computer, the same, to state preparation on a quantum computer, the same procedure for a small number of qubits. So this idea of finding the physically relevant control degrees of freedom seems to be something that is currently being recognized as important to study in the field, not only by us, but also by colleagues. So this was like a long, introduction, if you wish. Well, not quite introduction, but a long way to come to the point where I can finally show you some very concrete results and go from abstract description to something more down to earth. So suppose now in my first example that I have a spin 1 Ising chain. So you can imagine here the spins. These are not spin-and-a-half particles, so these are not qubits, but these are qubits. There's a technical reason for this, which I can tell you about later. But the Hamiltonian now here is the mixed field Ising model. So there's a nearest neighbor interactions between the qubits along the z direction. Then there's an external field, fixed strength along the x-axis, and another external fixed field along the z-axis, right? And then these are like some parameters that I've chosen. One important property of this system is that this is a non-integrable system, meaning that I have no closed form expressions for the eigenstates and the eigenenergies. So it's actually very hard to do any analytical treatments of this. It turns out that the exact adiabatic gauge potential, for the same reasons, is actually not a local object. It cannot be computed in terms of local Hamiltonians. And so all of this makes the problem very much complicated. And it makes it like a perfect example to test in our model agnostic reinforcement learning based algorithm. So as I said, in ground state preparation, we would like to first start with some initial state, and the initial state is going to be the polarized down state. So this is a product state, a simple to prepare state to start with. And then the question is, can we actually target the ground state of this Hamiltonian and this specific set of fixed parameters? Okay, so if you had QAOA, then what you would do is you would alternate between the Hamiltonians H1 and H2, right? This is what QAOA does, right? But now, in CD QAOA, which is the algorithm with continuous discrete control based on reinforcement learning, then apart from the two QAOA terms, as I said, we can put in this generalized current. So for instance, a Y field, an XY current, a YZ current, and then this could be nearest neighbor, but this could also be next nearest neighbor, right? So we can put like more terms, and we can ask our agent to construct an optimal sequence for that. So now remember that every sequence comes with a fixed total time duration. So this is a constraint that I impose for practical reasons. And what I'm showing you here on the left now is the best energy that the algorithm was able to get as a function of that time duration, of that protocol duration. Now, obviously, if my protocol is too short, then it's just going to be physically impossible, to get from one part of Hilbert space to another part of Hilbert space. This has nothing to do with quantum physics. It's just, the fact that, you're constrained by what you can do and by the resources that you have available to move from one place to another. But of course, if the time becomes longer and longer, we expect to be able to do that using these extra controls. So let's first, okay, on the graph here, I'm showing you 4 different curves. Now, the first thing you can wonder, is, okay, so I have this problem and I know that I probably can do this process adiabatically. So how well does the adiabatic preparation do? And that's given here by this purple curve, right? And so you see that even, after a significant duration like 24, this is in units of these couplings that is set to 1, even up to significantly long durations, I can't really get close enough to my target state. So this is the energy axis. Sorry, I should have explained. It's normalized by the ground state energy, which means that if this quantity here becomes 1, then we've reached the ground state, we've prepared the ground state. And the further it is from 1, then the further we are from the ground state itself. And so what the adiabatic curve shows us is that we can't really reach the ground state in any of these fixed durations. Now you can wonder, okay, what if I just do QAOA, which is the blue curve here? If you only did QAOA, then of course you do better than the adiabatic one, right? It's a quantum alternating ansatz. It doesn't have to be adiabatic, right? And so we see basically the blue curve. If you would only do a counter-diabatic driving, right, this variational counter-diabatic driving that I explained on the previous slide with these extra gauge potential terms, then you can do that, and then you beat QAOA because you have better controls than QAOA, right? But of course, if you combine the QAOA ansatz with counter-diabatic driving, which is the CD QAOA, with for which we actually need reinforcement learning in order to determine the sequence in which these unitaries occur, then what we find is the red curve, which is by far the optimal one. And just to tell you, here the sequences have length of 20, so 20 gates per sequence, which means that in total, there's 10 to the 15 different sequences, possibly one of which is going to be the optimal one, right? And obviously you need like an algorithm, a sufficiently sophisticated algorithm to do this optimization. And this is done, this is what we use reinforcement learning for. And the whole simulation is done on a system of 8, but now notice not qubits, but qtrits. So the Hilbert space dimension is actually larger. We use some symmetries to reduce it. Because we don't want, we need to basically, save some computational power in order to be able to trade the agent. I should say that we also did that for 10 qtrits, where the Hilbert space dimension is, I think, about 3,000. So it's, you can push it to as big as it can get. Now, of course, this is how close you get to the ground state, but there's another quantity you can look at to measure this, which is the fidelity, which is essentially the overlap between your target state, the ground state that you want to prepare, and the evolved state. And this is a little bit more sensitive than the energy. So what you see here, again, these are the same curves, right? Is that by far the counter-diabatic driving, the CDQAOA algorithm does the better, and then after, say, durations of size 24, we can actually reach pretty close to the target state, and neither of the other algorithms that we used as a motivation to cook up CDQAOA can get us that close. Okay, so this was like one system, the spin-one Ising chain. Now let's see whether we can do like another one. So here's one that's a little bit more interesting from the perspective of quantum simulation. So this is the spin-one anisotropic Heisenberg model, Heisenberg chain. And so here again, the Hamiltonian is decomposed in H1 plus H2. H1 is now the XY term, so we have nearest neighbor XX plus YY interactions. And then H2 it contains nearest neighbor ZZ interactions with some anisotropy parameter delta. So the interesting fact about this system, spin-one system again, is that it has a very rich ground state phase diagram. Especially if you, and this is as a function of delta, the anisotropy parameter. So if the anisotropy is very large, right, let's say infinitely large, then this term dominates the Hamiltonian, and if delta is positive, then your state is going to be an antiferromagnet. And contrary, if this delta is large and negative, then the state of the system will be ferromagnet. Now, as you decrease delta from the positive side, you're going to enter a so-called Haldane phase, where it turns out that the ground state of the system has topological properties. If you do that on the opposite side, right, so here in this blue regime, then the ground state of the system has this low energy XY type order, right? So what I'm trying to show you here is that there's a variety of different ground states that you can now ask your agent to prepare. And so what we decided to do is to start, from the state of infinite anisotropy, where we have a very simple product state, right? So that's an easy to prepare state to start from. And then what we want is we want to prepare either the Haldane state or the XY state or the ferromagnetic state in a fixed amount of time using our algorithm. Okay, so and once again, now that the system is a little bit different, right? Then also the gauge potential terms that we use are also slightly different. But again, you can compute those. So that's not a problem. What I also want to say is that the way we define the algorithm, we don't really need to only put gauge potential terms in H1 and H2 terms. We can also put in your favorite Z term or XX term, nearest neighbor interaction, etc., etc. So you can just have these controls that are available to you in your, for instance, experimental platform, quantum simulation platform. Okay, so once again, here in this plot, I'm showing you the energy, normalized energy versus the protocol duration. In this case, the sequences have length of 18. There's a total of 10 to the 16 different sequences. The Hilbert space dimension is the same. Now there's two types of curves here. So it's actually three colors that correspond to preparing the Haldane state. This is the green one. Then there's the XY, which is the blue, which is shown in blue, and then there's the ferromagnetic, which is shown in red. And these two curves come in two flavors: solid lines and dashed lines. So the solid lines are the CD QFA algorithm, including the gauge potential terms, whereas the dashed lines are just QAOA, which is what we want to compare to. And the take-home message from this curve is that if you're trying to prepare the XY state or the ferromagnetic state starting from the antiferromagnet, right? Then if you're only doing QAOA, which means that you can only flip between these two terms, H1 and H2, then it's actually not possible to even reach your state, right? So the available controls here are not sufficient, are not enough to grant you access to that state using unitary time evolution, Schrödinger time evolution. This is possible for the Haldane state, interestingly. But of course, even for the Haldane state, you cannot do as well as what you would be able to do if you have these extra counterdiabatic control terms, right? Take-home message from this curve is that having extra controls is actually advantageous. It allows you to prepare your state in much shorter time. And notice, much shorter time is a great advantage these days, because we know that our quantum computing devices, for instance, are quite noisy, right? And then being able to do the process in a short amount of time is actually going to buy you quite a lot in that case. But I'm mentioning quantum computers, but I should say this is also equally applicable to systems of, say, cold atoms or trapped ions, etc., right? So this is, a completely generic setup because you can put in any fixed drift Hamiltonians that you might have during the evolution in your set of unitaries, set of operators. The last example I would like to show you very quickly is a spin-a-half spin chain. So this is also a non-integrable system, a little bit simpler than the one before. So in this case, the really interesting thing that we find is that if you only use QAOA, then again, within short amount of duration that we give the agent, it's actually not even possible to get to the agent, irrespective of how large I make my sequence, right? But if I use CD QAOA, then I can get almost its fidelity within the precision of the algorithm with only 3 steps. And this is something that is actually quite neat. If you try to do some system size scaling, right, so you can wonder, okay, these are now qubits, right? So I can go all the way up to 18 qubits, so a large Hilbert space dimension, and you wonder, how dependent is this process on scaling of the system size? And this is something that was truly surprising to me. It looks like, it's completely independent of the system size. So all we see here are so these values for the energy at this fixed amount of time, they are all fixed by the constraints in our physical system. So we have a nice scaling collapse. Okay, so with that, I'd like to move over to the summary. So I've shown you that it's possible to define a generalized continuous discrete quantum alternating operator ansatz, and that there's a very natural application of reinforcement learning in it, where it's used to fix or to solve the discrete optimization problem. Now, I should say that one can also use reinforcement learning to solve also the continuous optimization problem. And one of the things that we did here, especially in this second paper, more recent one, was to actually eliminate the continuous solver and to use reinforcement learning for both the discrete and the continuous solver. And this also seems to work nicely. And it's also robust to all kind of external noise, etc. But I've also shown you that it's non-trivial to pick up the terms, the control terms in our physical system, especially when it comes to quantum many-body systems that have strongly correlated ground states. And one natural way of doing this is to use insight from counter-adiabatic driving, right? But of course, this is not the only way of doing this. As I mentioned, you can add some drift terms. So these are Hamiltonian terms that you cannot turn off during the time evolution because your experiment is set up in such a way. Fine, you can't turn it off. You just add it to the set of gates in this way, in the way you have it. It's still going to work. Or if you're more into quantum computing, you can try just a universal gate set and see what this is going to give you. The CDQA algorithm gives us much shorter circuits or protocols. So as I mentioned, there will be smaller error accumulation. And then they also, interestingly, provide superior performance compared to just counter-adiabatic driving or just QAOA, right? And this is maybe not so surprising because in some sense, this ansatz is generalizing, as I said, these two. And so, last but not least, I've also shown you like a nice synergy between machine learning and quantum control. So hopefully, I've convinced you that, reinforcement learning is useful for this task, but this is not the only task that it can be used for in quantum technology. In particular, it also has been used for quantum error correction, for quantum optics setups, or even in classical systems to navigate turbulent flows, finding optimal strategies, how to move through turbulent flows, or to explore even the landscape of string theories, or even for some statistical mechanics problems. And so I really think that, we're in a position where we have understood how these methods work, and now we can ask the question, can we actually get like some new physics out of all of this? And with that, I would like to thank you for the attention. And I would like to mention that all the simulations done here have been performed with the QSpin package, which is a open source library, Python library that we've developed with Phil Weinberg and Marcus Schmidt that allows you to actually simulate these many-body systems. And if you're interested, check out the documentation website. Yes. And so, yeah, with that, I'd like to conclude. Thanks a lot, guys, for the attention.
Thank you, Professor Marin. So now the session is open for question and answers. So anyone interested or anyone have a query, you can ask. There are, of course, few in the chat box, so I will read out after this. Yeah.
Can I ask Professor Narayan?
Yeah, sure.
Yeah. Thank you for an interesting talk, Marin. I have a question about, do you have some insight into why QA worked for qubits, but didn't seem to work for a similar Hamiltonian for qubits?
Yes, so sorry, I'm trying to go back. So notice that, okay, so there's a few different things here to answer this question. So when I say it didn't work, the important number to look at is here, the number on the x-axis. So it didn't work in these short times, right? In these short durations.
Yeah.
But of course, the durations that we used, for instance, for the Heisenberg model are on the same order of magnitude, right? So whether your algorithm works or not is essentially determined by the underlying physics, right, of your system. So if you're trying to move from one initial state to your target state, which is in a sense very far away in a huge Hilbert space, then it's not always clear that it would be a possible process to do, given the the unitaries that you have, right? So notice that the unitaries that I'm choosing here have a physical constraint that they have to be local operators that can be implemented in the lab. These are not necessarily all possible rotations in Hilbert space, and therefore I cannot guarantee that I can always get from one state to the other. So, the long story short is that whether you can or you cannot make it depends on the model, right? And also on your control space.
Yeah, okay, thanks. But I was actually comparing the Qtrit case. So I think there you went longer, right? You went to maybe 20.
Yeah, here I also went longer, exactly. Yeah.
Yeah, there we went.
And again, this is once more, this is a different system, right? This is a different Ising model, right? Even though they are all spin-1 models, I'm not claiming that I can prepare any ground state of any spin-1 model, right? This would be ideal to have, but we don't have it. But instead, what we do is we realize the model in the lab, and then we ask ourselves, how can we actually get to this ground state? Because, for instance, if you don't get to the ground state, you can't study these phases, right? So that's essentially the motivation behind it.
Just quickly, you said that these are non-integrable models. So how would you? How does it compare if you did have integrable models or the integrable cases in these models?
So we did actually. This is something that I didn't put in the on the slides, but we did study one integrable system. The advantage of having an integrable system, maybe this is a good slide. The advantage of having an integrable system is that you can use many more degrees of freedom. So you can go, for instance, to 500, maybe thousands of spins, right? Yeah. But the effective Hilbert space dimensions that we can do are actually quite similar, right? So there's no free lunch here, right? You're just redistributing the parameters in your Hamiltonian. So the reason why I did not explicitly discuss integrable systems is that for some integrable systems, their dynamics essentially is constrained by an extensive number of conservation laws, right? And so it's not that they can access all states in Hilbert space, right? Whereas the non-integrable systems that I'm alluding to here are essentially less constrained, and as such are more difficult. If you want to be more precise, they can exhibit quantum chaos, etc. So they're more interesting target Hamiltonians. But long story short, to answer your question, this method can be applied to integrable systems. We have done this. There's one example of the LMG model in the paper. You can check it out. And there's no problem of applying, setting any, for instance, parameter here to 0, and you can still get an integrable system.
It's easier in the case of integrable models to.
Not necessarily. It could be. It doesn't have to be.
Oh, thank you.
What's easier in integrable systems is to actually compute something analytically, right? And compare.
Thanks.
Can I ask a quick question?
Yeah, sure.
Hi,
we
thank
have a
you,
couple of minutes.
Yeah, I'll be very quick about it. Thank you, Marin, for the very good talk. It was a very nice talk. So just one technical question and then one kind of more broad scope question. So TQSL depends on the path. No, it actually depends on the control Hamiltonian that you use, because you have to evaluate the TQSL on the Beerers on the paths that you're using. So how are you,
yes.
When you say TQSL, are you using an upper bound on the Hamiltonian or something like that to evaluate TQSL? This is question number one.
No, okay, so let me just explain for the audience. So the question relates to this TQSL here. That's the time for the quantum speed limit. The quantum speed limit is defined as the minimum time required to prepare a system. The minimum time required to get unit fidelity in your process, and strictly speaking, unit fidelity, right? Okay, and so now your question was, how do I know that the quantum speed limit is going to be here? Is that the question, or can you repeat it once again?
Margolis-Levitin and Mandel-Stam-Tam for time-dependent Hamiltonians both have these integrals inside them. They have these slightly kooky formulas that you have
right.
to
The problem is that the estimates by Mandelstam and Tam, etc., and then there's like a few more, they actually impose no constraint on the locality of the generators of time evolution, right? So they just assume that you can do any rotation in Hilbert space, but any rotation in Hilbert space is not necessarily generated by a physical Hamiltonian, right? And that's really the connection or the distinction that probably I should have emphasized a little bit more. So here I'm really trying to think about, or within the constraints of present day in quantum simulators. So what it means is that I only have such nearest neighbor terms in my system, at my disposal. So this quantum speed limit will depend on the constraints that I have in my control problem, in particular on which terms I put here in the space of available control unitaries. And in general, my quantum speed limit will be larger than the ones predicted by Mandelstam and Tam, just because I have more constraints on the system. But I believe it's going to be, in a sense, more experimentally accessible and more relevant, more down to earth.
I see. And one last very quick question, man. In this counter-adiabatic, the whole kind of derivation, basically, it actually generates, potentially an infinite number of terms, right? And essentially the problem is the termination. And so you've stopped at 3. And does the infidelities that you get somehow related to 3? I mean, can it be traced back to the fact that you stopped at 3 operators?
Right. So as I said, however, the performance of what you get in the end will depend, of course, on which terms you put here. You're also right to say that there's infinitely many terms in this series, and this is what I alluded to when I mentioned that in these complicated many-body systems, the gauge potential is a non-local object. In fact, the non-locality arises from these nested commutators that you see here. But non-local objects are unphysical. Like, for instance, if you think about, let's say, a trapped ion system or a cold atomic system, I can barely imagine that I can have like next nearest neighbor interactions, for instance, right? Just because they're exponentially suppressed in nature. Or if I have, for instance, 3 body terms, right? Which is also something that you would get if you go to the high order term, right? So the reason, so the place where I stopped the expansion here is dictated by locality and by, essentially by locality, and by the number of operators that show up. So that's my physical constraint that I put. In principle, you can go to higher order. It doesn't mean that you're going to do something useful, right? You're going to get better, but again, if you take them all, you're probably going to get to Mandelstam, back to Mandelstam and Tam.
Sure, I understand. Yeah, thanks a lot.
Okay. A very short, quick question. Last one.
Yes.
So, mine.
Yeah. Okay,
if you consider, for instance, 2-qubit gates, there is classified 3-parameter family of gates with respect to non-local properties. So in a sense, of course, to have something interesting, you have to have non-local gates. So the question is, to what extent is it true that the more non-local gates, the better from your perspective or not? Or is it 3-parameter parameterization of 2-qubit gates? Are there any special distinguished gates from your perspective?
Right. So from this perspective, it's hidden in this equation here, right?
Yes.
So even though you are constructing your overall unitary, your process, this is the total process that, for instance, rotates the initial state to the target state, right?
Yes.
But you're decomposing this process into a product of exponentials, right?
Yes.
And every exponential is generated by a local operator. However, when you combine everything, you can actually effectively get a highly non-local unitary. Right. So in a sense, even though you have a local Hamiltonian instantaneously, you can access these gates. So that's the mechanism how this works here. And I believe that it's the same mechanism that if you're using 2-qubit gate, right, then you can generate a non-local unitary if your circuit depth is large enough.
Okay. Okay.
I don't know. Did I answer your question?
Well, to some extent, yes. Yeah. Okay. Thank you.
Yeah. Thanks.
Thank you. Thank you for some nice talk. Yes.
Yeah. Thank you, Professor Marin, for the nice talk. So there are a few questions in the chat box, so we will mail it to you, and then the volunteers will do the needful, and you can respond to that. Since we are running short of time, we will proceed to the next talk. I request you can.
Thanks a lot.
Yeah, thank you. So thank you for accepting. I thank both the speakers, Professor Carol and as well as Professor Marin, for accepting our invitation and giving the talk. So now we go to the third talk in the session. The speaker is Professor Debashish Sarkar. He is at University of Calcutta, and he is in the Department of Applied Mathematics. His primary area of research includes quantum information theory and quantum foundations. The title of the talk is Quantum Correlations in Quantum Network Scenario, a case of more complex network. I request Professor Sarkar to begin the talk. Yeah.
Thanks, Nayan. Is my slide visible?
Yeah, sure. Yeah, yes, sir. We can see your slides. Yeah. It's a full screen.
Thanks also,
we are all...
Subhashish, for arranging this nice conference in this pandemic situation. Thanks to Narayan also. My topic is quantum correlations in quantum network scenario. Today I also spend some time on more complex network lastly. This topic I am doing research with my students who already did their PhD for last 5 or 6 years. This work is obviously based on two recent works. One is published in last year by Physical Review A, and another is in preparation. The collaborators are my students Amit, Mostaq, and Indrani. Now, our lecture is based on basically what I have said, two works: maximal qubit violation of n local inequalities in quantum network, basically chain and star network shape, and another what is in preparation, violation of this inequality in more complex network. Basically, I choose the triangle network configuration. Okay. Now, before going to our main things, I have to do some basic matters to go to these network things, because this is one of the important part of quantum foundations, understanding correlation. This is one of the possibly most important term in modern physics. Now, naturally, one may ask, what do you mean by correlation? However, the answer is not quite obvious. Rather, our sole intention is to understand the word correlation. The term correlation generally appears when we perform a measurement on a physical system or subsystem of a composite system repeatedly and want to observe the outcomes of that measurement. In other words, we basically interested to learn about the correlation between the results of the outcomes. Consider a system of n particles or parties assumed to be separated in space-time, say at different laboratories. Each of the parties perform a measurement on their subsystems and observe their outcomes. Alternately, suppose to each of the parties a question is provided from a set of questions, and the answers are provided by the parties according to their measurement results. The answers are assumed to be many for a given question. In mathematical terms, each party has provided with an input xi, capital Xi, called measurement settings with values small xi, and output is small a. Our interest is then to understand the nature of the joint probability distribution. This is how the correlation appears in any statistical scenario. Now, in quantum theory, one could ask that from where we can start. Usually, the starting point to understand correlation is associated with the view that quantum theory is non-local, in the sense that quantum correlations cannot be described by a local hidden variable theory. Real inequalities serve the purpose of distinguishing between classical correlations and quantum correlations. Now, what do you mean by, in short, by hidden variable theory? By hidden variable, we mean the different system measured in the experiment are considered to be all in the initial joint hidden state lambda, say, where lambda is arbitrary. The outcomes of the measurement of any particular system can depend on the global state lambda and on the type of measurement performed, but not depend upon the measurements performed on the distant or separated systems. This assumption usually known as Bell's locality assumption. Mathematically, this locality assumption means that this joint probability distribution could be written in the product form of the individual parties, where rho lambda is the probability distribution over the set of all possible joint hidden state, and integration over rho lambda d lambda is equal to 1. This is required for the probability distribution, and we have assumed implicitly that measurement choices x1, x2, etc. are independent of lambda. Now, all the correlations that comes from such a joint conditional probability distribution are known as classical correlations. These are called local or classical correlations. We call correlations are quantum if the joint conditional probability distribution have the following mathematical form, where this joint probability conditional probability distribution you trace over some state sigma and the positive operators p x1 a1 x2 x2, where a signature pxi ai denotes the positive operator representing the measurement outcomes at the ith site, and sum over all these positive operator should be equal to identity, and sigma is the state of the corresponding joint quantum system where each party in general is associated with a separate Hilbert space. Okay, so by this unique formula we can find the conditional probability in quantum regime. Now I am going to the tripartite non-local case because we essentially use tripartite or more than tripartite things. So I begin with some tripartite scenario. Let rho ABC denote a given tripartite quantum state shared between three parties, Alice, Bob, and Charlie. The correlations arising due to measurement of the parties on their respective subsystem are local if those can be decomposed in the form this. If you write down in that form this conditional probability, then it is called local. The correlations which lack such a decomposition are said to be non-local, and the which lacks obviously, and the tripartite state rho ABC is said to be a non-local state. The non-local correlations are capable of violating tripartite Bell inequality. Now, for such tripartite scenario, there are many things where each of the three parties can perform any one of the two binary inputs. Bell local polytope having 46 facets was defined by Silva. Then the 46 inequalities is defining a facet of the local polytope serve as a necessary and sufficient criteria to detect non-locality of tripartite correlations generated by local measurements by each of Alice, Bob, and Charlie, say, on their respective subsystems. This in turn guarantees that the tripartite state rho ABC shared between them is non-local in the specified in any specific Bell scenario, 2 input, 2 output scenario, 1 input, 4 output scenario, many things. Let there be a referee who wants to check whether the correlation shared between the three parties are steerable. This steering is also very interrelated things. However, he trusts the measurement separators of only one party, say Bob, but does not trust that of Alice and Charlie. He will be convinced about the steerability of the tripartite correlations from Alice and Charlie to Bob if those correlations are inexplicable in the form. That cannot be written in this form, where lambda denotes the hidden variable, xz AC denotes local inputs and outputs of Alice and Charlie respectively. This pi b conditioned by y denotes the projection operator corresponding to observable characterized by Bob's setting y such that this is associated with the eigenvalue v. Rho b lambda parameterized by the hidden variable lambda stands for some pure state of Bob systems. If the tripartite correlations are steerable, that is, cannot be decomposed in the above form, then the corresponding tripartite state is considered to be a steerable from Alice and Charlie to Bob. Cavalcanti et al., they have provided a Bell-type inequality under some specific measurement settings, von Neumann equatorial measurements, of all parties with referee trusting only one party was given to detect steerability of rho. Violation of this inequality is only sufficient to detect steerability of rho ABC from 2 to 1 party. So no definite conclusion can be given if it is satisfied. Now, some points to note. So far, we have not mentioned about the sources by which a composite system is shared between many particles or parties, as if there is only a single source by which the system is shared. This is the general scenario we generally consider. However, we can consider a situation where there are a number of independent sources and each produces some system that is shared between a number of parties or particles. This situation is new to all, and it is actually provided by Nicholas Gissin's group 10 years back. In the language of hidden variable, instead of considering a single hidden variable, we consider there are many independent hidden variables. A typical example of such scenario is the bilocal correlations. I will explain this bilocal correlation. Consider a simple situation of three parties, say Alice, Bob, and Charlie, share two quantum states, rho 1 and rho 2, produced by two independent sources, S1 and S2, where rho 1 is shared between Alice and Bob, produced by S1, and rho 2 is shared between Bob and Charlie, produced by S2. Alternately, the system between Alice and Bob, produced by the source S1, is characterized by hidden variable lambda 1, and similarly between Bob and Charlie by another hidden variable lambda 2. And this is a pictorial diagram where you show that xi is the input or ai is the output of Alice, S1 is the source where this lambda 1 is shared between Alice and Bob, S2, lambda 2 and Charlie. And this is a simple picture of a tripartite. Now, what is new in this scenario? Instead of considering a single tripartite state shared between three parties or particles, here we have considered a series of bipartite entangled sets that are initially independent and uncorrelated with each other. In other words, analog to hidden state lambda in a local model, there is no initial joint state which is responsible for the observed correlation. Instead, we have correlations created by smaller systems through joint measurements. When we call a correlation bilocal, the correlation which can be described by the results of the measurements of two independent hidden state lambda 2 each produced by one of the two sources. Otherwise, then we call it as a bilocal correlation. Otherwise, we call it non-bilocal. I will explain a little more. Mathematically, if the joint probability distribution is of this form, where you would find that this rho 1 depends upon two hidden variables, lambda 1, lambda 2, and the integration overall lambda 1 and lambda 2. And for Alice, this probability, marginal probability is x, which depends on lambda 1, but for Bob, it depends on both lambda 1 and lambda 2, and for Charlie, it is on lambda 2. Or that this joint distribution would be factorized as the sources are independent, it will be factorized by separate hidden variables. Okay, and they will satisfy the normalization condition. It is clear that this is the form of really bilocal correlation, and you can observe that this bilocal correlation is local by construction. Thus, the set of all bilocal correlations is a proper subset of local correlations. We know that the set of local correlations is has a convex structure, but the set of bilocal correlation is not a convex, as the mixture of bilocal correlations need not be a bilocal in general. So this is a mathematical difficulty. Also, the bilocal set is connected, but this set is connected and is restriction to subspaces where the marginal probability distribution of Alice or Charlie is fixed is star convex. However, star convexity does not hold for the full bilocal set. All deterministic local or bilocal as they are the extreme points of the are bilocal as they are the extreme points of the local set, and also the convex hull of bilocal set is the local set. How to determine a correlation is bilocal? One can look for some well inequalities such that it is satisfied by all bilocal correlation. Then violation of these inequalities or constraints imply that correlation is non-bilocal. However, we find some nonlinear type bilocal inequality rather than linear constant found in the usual case of local correlation. What is the form of this? All entangled swapping, an entangled swapping network is a particular case of this scenario. The correlations are bilocal if they satisfy the inequality bold B is less than equal to 1, where this B has a form square root of modulus I plus square root of some other quantity modulus J, where modulus I and modulus J are simply the expectation values of the observables of Alice, Bob, Charlie. I has that form, J has that form, and this correlation is the usual things, where X, B, Y, C, Z are observables for the binary inputs X, Y, Z of Alice, Bob, and Charlie respectively, and ABC have the values 0 or 1, denote the corresponding outputs. You can check now. Okay, this is the bilocal. Now you can move to this bilocal to trilocal scenario. A pictorial diagram of this. There is 3 sources. There are minimum. There are 5 parties. Alice, Bob, Charlie, Dick, and Tom. And there are 3 hidden variables from S1, lambda 1 with Alice, Bob, and Charlie. S2, lambda 2 hidden variable, Bob, Charlie, and Dick. And S3, Tom, Bob, and Charlie. And their input outputs are Xi, Ai, Bi, Yi, Ci, Zi, Wi, Di, Ui, Ei is. It is a network of 5 parties, what I've said. They share independent sources, S1, S2, S3, characterized by the hidden variables lambda 1, lambda 2, lambda 3, with independent probability distribution, rho 1, lambda 1, rho 2, lambda 2, rho 3, lambda respectively. And this case, rho 1, lambda 1, lambda 2, lambda 3 should be factorized this, and all the normalization condition should be satisfied. Now let X, Y, Z, W, U, they belongs to 0, 1. This is the simplest situation, denote the binary inputs, and ABCD also 0, 1, denotes the outputs of Charlie D. Each party performs measurements on its respective particles. Each of Bob and Charlie receives 3 particles, one from each source. SI, Bob, Charlie are named as intermediate parties. Each of the remaining 3 parties, Alice, Dick, and Tom, receives only 1 particle and are termed as extreme parties. No communication is allowed between the parties. We call the correlation is trilocal if the joint probability distribution satisfies this equality, where you find that the marginal distribution of Alice depends on lambda 1, Bob lambda 1, lambda 2, lambda 3, Charlie also lambda 1, lambda 2, lambda 3, and Dick and N lambda 2 and lambda 3, Tom respectively, together with the constant given the above equation. Under source independent restriction, correlations which cannot be decomposed as above are said to be non-trilocal in nature. Now, by construction, again, set of trilocal correlations forms a proper subset of local correlations. However, the set of trilocal correlations is not convex, and due to the nonlinear constants. Now, if the non-trilocal correlations are generated in the network, when each of the 3 sources generates identical copy of a tripartite system, say S, then S is said to be non-trilocal, and this form of non-locality is said to be non-trilocality of S. To detect non-trilocality, we frame a set of sufficient criteria in the form of nonlinear type L-type inequalities. One theorem is any trilocal five-partite correlation necessarily satisfies this I, and where I depends upon two indices. I has this form. This is the expectation values of five parties, where I is this M is this X denotes the observables of inputs X of Alice, By, Cz, DWT, U are similarly defined. Each of these, there are 16 actual inequalities is tight in the sense that there exists correlation reaching the bound 1. In the context, one should note that the notion of tightness discussed here is different to be specific weaker compared to the standard notion of tightness in Bell's inequality, where usually tightness of a Bell inequality refers to a specific feature that the inequality is a facet of local property, but here this is not that case. Now, all these inequalities are necessary but not sufficient criteria of trilocality. That is, there may exist non-trilocal correlations that satisfy all these inequalities. However, violation of at least one of these inequalities guarantees non-trilocality of the correlations. Hence, violation of the above equation for at least one possible I1, I2, G1 is sufficient to detect non-trilocality of the correlations. Now, next, we put forward a set of Bell type which acts as sufficient criteria to capture non-locality of the correlation generated in the scenario. It is of the again of the form theorem, where this is less than equal to 1 local 5 satisfy. Just as in theorem 1, here also 16 inequality is tight in the sense that there exist correlations for which equality is obtained in each of the inequalities. This set of inequalities being only a set of necessary but not sufficient criteria for locality, no proper conclusion can be drawn about the nature of correlation satisfy the whole set of inequalities. However, violation of at least one of these inequalities from the set guarantees that the corresponding correlation generated in the network are non-local in nature. A comparison of the form of trilocal and local inequalities for every possible combination I1, I2, J1, J2 clearly indicates that the inclusion of set of trilocal correlations inside the set of local, as was already interpreted before, or from the decomposition of trilocal and local correlations. Now we can discuss throughout our discussion, we denote the set of 16 trilocal equal by tau, capital tau, and the set of capital L. After sketching the trilocal networks here, along with inequalities capturing nature of five-partite correlation terms characterizing the network, we now explore quantum network scenario compatible with our scenario. This is the pictorial form projection of the correlation space Ij plane, where I, J, J1, J2, J01, tau, and L denotes the set of trilocal and local correlation space. Clearly, tau forms a proper subset. This is the tau, and L is this box. Now we are going to the network situation. More general, consider a double entanglement swapping network with three independent sources S1, S2, S3, each producing a tripartite entangled state. Before we have the bipartite, but here we consider tripartite entangled state. S1 sends a tripartite state rho ABC to Alice, Bob, Charlie. S2 sends another tripartite state rho BCD to Bob, Charlie, Dick. S3 sends tripartite to Bob, Charlie, and Tom. Say the overall quantum. This is also the five-party scenario. The overall quantum state is nothing but the tensor product of the density operators. The correlation arising due to the measurement of rho ABCDT characterize the network. Each of the two intermediate parties, Bob and Charlie, performs partial GIZ basis measurement on the joint state of three system that each of them receives from their sources. For instance, Bob from partial GZ on his 3 qubits that he received from S1, S2, S3. That is corresponding to each of the two inputs. He can distinguish between any two non-overlapping groups from each 8 class of GZ basis, 8 state, sorry, not class, 8 states of GZ basis. Similarly, Charlie also performed partial GZ basis measurement on the joint state of the 3 particles that he receives from the sources. Our choice of partial GZ basis measurement against full GZ basis is not only compatible with the non-trilocal network scenario, but also justified from the experimental perspective, as the latter is impossible in non-idealistic situations. Resulting state rhoidity is shared between the extinct 3 parties, Alice, Dick, and Tom, who then perform arbitrary projective measurements on their respective particles, forming the tripartite state rhoidity. The 5-party correlators resulting due to the measurement by the 5 parties on their respective subsystem are non-trilocal if those can violate at least one of the 16 inequalities from the set tau, whereas these are non-local if they can violate at least one of the inequalities from the set L. If non-trilocal correlations are obtained when all 3 sources generate identical copy of a tripartite quantum state, say rho, then that guarantees the state is rho is non-trilocal. This form of non-locality of a tripartite state is referred to as non-trilocal. Analogous of non-local correlations are generated in the network due to use of 3 identical copies of rho, then rho is said to be non-local in the network scenario, apart from the standard Bell scenario. Now we are going to our main topic. We will discuss some recent result that is generated by some problem generated by Gissens and 2 groups, Androli et al. The main goal of this work, first work, is to get the maximal violation of the n local. So from trilocal, you can go generalize to n local. I will spend a little bit about n local correlations, n local inequalities for n local scenario using arbitrary qubit states shared between 2 parties from different sources, just like the bilocal inequalities given by Andreli et al. And Gissen et al. They actually individually they have given this bilocal scenario. Here we consider only 2 types of n local scenario, one for chain separate, that is linear chain, and another is the star separate case. Gissen et al. Showed that all pure entangled states violates bilocal inequality. This is showed recently. This also showed that for mixed state distributed over the 3 parties from the 2 different sources, there is a relation for bilocal inequality violation and CHS inequality violation. This is a connection between bilocal and CHS inequality for each sources. They provided the relation that S bilocal max is less than equal to square root of SAB and SBC, where these SAB and SBC are the CHS value, which proves the violation of bilocal inequality implies that either rho AB or rho BC or both must violate CHS inequality, where rho AB, rho BC are be 2 mixed states shared between Alice and Bob and Charlie respectively. They have the form, say this is the form of rho AB and this is the form of rho BC, 2 qubit states. Here MAMB represents block vector of Alice Bob's reduced state, and DMN is the correlation matrix similarly for rho BC. Maximizing S bilocal, they proved that the minimum criteria for bilocal violation, either rho AB or rho BC, should be non-local. This is not off or proving this statement. If Androli et al. Took a state 5 plus, this is a Bell state 0 0 plus 1 1 by root 2 between Alice and Bob, and a generic density matrix between Bob and Charlie, and showed that satisfying CH inequality by the genetic state rho BC violate by local inequality. Now we go to the n local scenario. The n local change scenario is depicted in this. This is the change scenario. N local, there are n sources between these lambda 1, lambda 2, lambda n are hidden variables. N sources and n plus 1 parties AI arranged in a linear way such that any two neighboring parties are share a common source. For each I, party AI can perform two dichotomic measurements xi k equal to 1 2 where xi k belongs to 0 or 1. On the system they have received and obtained outcomes AI j equal to 1 2 where AI is also 0 or 1. Accepting the extreme two parties, A1 and AN plus 1, each of the remaining n minus 1 parties would receive two subsystems. The measurement will be a joint measurement operating on both subsystems simultaneously. In this scenario, Bell locality takes the form, this joint probability distribution gives this form where this capital Pi is the product of these marginal things. Here lambda is the joint hidden state. For each party AI, the input xi and the corresponding output AI is determined the local distribution. The hidden state follows the distribution rho lambda with normalization condition, and the measurement choices of each party are independent of lambda. Now suppose each source Si be characterized by hidden state lambda I. Moreover, we assume that each I for 2 to n, the output party I depends on the states lambda I minus 1, lambda I, and its input xi, whereas for A1 and AN plus 1, the outputs depend on their corresponding inputs and also lambda 1, lambda n respectively. So we can write this joint distribution as this. This is a total probability distribution, lambda 1 to lambda n, and these are the marginal things. These two are separate, only depends on lambda 1, lambda n, and this is the all other intermediate things. Without any further assumption, this equation can jump to Bell local equation when all the different hidden state will be the same. Now, for in local assumption, the distribution of the hidden states with independent sources, we can factorize the distribution as this. The independent of sources and probability distribution together define the assumption of n locality. To study whether a given correlation is n local or not, there is a nonlinear inequality exactly same like bilocal inequality or trilocal inequality, which is referred as n local inequalities. Here we only consider the picture where two extreme parties have binary input and output, and with one input and four outputs for the remaining n minus 1 party, P1 port scenario. The other picture is party where two inputs, two outputs. Okay. We can see that for n equal to 2 makes the scenario exactly like bilocal, for which Giessen et al. Proved the inequality for the equation. Here we have tried to extend the process for this n local zero. What is the case for n local zero for P1 for case? Now the inequality to check n local correlation is this root over I root over j less than equal to 1, where I and j has this form for the n plus 1 parties. This is the expectation values. And this A0 and A1 be the joint measurement of the middle parties, denoting A0 is plus minus 1, A1 is plus also plus minus. So the inequality says that if the correlation satisfies the inequality, then we can say that the correlation is n local, and also it can be seen that the quantum correlations, the inequality get violated. Thus, for the n local scenario, we find the minimum number of sources which is CSH non-local that can easily violate the n local inequality. And later we extend this result to a star shape n locality where this there is a central node which connected to n number of parties individually. What is the in the we call those violation things. In the work of this network for bilocal network sharing two generic mixed states, say like rho AB, rho BC from two different sources, the maximum value is given by this quantity. Okay, of the left hand side of bilocal. While lambda 1, lambda 2, lambda 3 are the eigenvalues of the matrix. Rho AB, the correlation matrix is defined by this, where you are unitary matrix, and similarly for lambda 1, lambda 2, gamma 1, gamma 2, gamma 3, and for RBC. Now for maximal CHH value for rho AB, SAB max is, if you calculate, it is to these things, and similarly for rho BC, this thing. It directly follows that S bilocal max is less than equal to this squared in, which proves that the violation of bilocal engineering implies either rho AB or rho BC or both must violate. See, this is the result by Grissom et al. In the work Untitled et al., they showed that if Alice and Bob share a maximally entangled state, a well state, while Bob and Charlie share a generic quantum state, then bilocal inequality violation can be easily obtained without CHS violation of BC. Okay, they showed these things. Now making situation a little between we what we introduce one more party, Alice, Bob 1, Bob 2, Charlie, as in the figure 1, 3, 3 earlier. Here the number of sources is 3, and we call this situation 3 local scenario, a special of n local scenario. The middle party, that is Bob 1, Bob 2, again will do Bell state measurement with 1 input and 4 outputs denoted by this. The inequality for 3 local for ij is, and take rho AB and rho B2, then you find this is the pictorial things, this 5 plus 5, rho B1, B2. If we choose measurement choices, Alice, Charlie by any block vector, and middle party as this and this, then we determine the bilocal value for this tensor product of states for this measurement settings, maximizing the value. We get these 3 local things is root over lambda 1 plus root over lambda 1, lambda 2 are 2 maximum of the matrix, this matrix. So it can be easily seen that the violation of 3 local inequality, rho B1, B2 need not be non-local. Similarly, if we take rho AB1 is the 5 plus, rho B1, B2, rho B2, B is the generic form, we get the bilocal value, this where lambda 1, lambda 2 are 2 maximum eigenvalues of the matrix, and similarly gamma 1, gamma 2 for rho B2C. Now we take all the 3 states are in generic form and calculate the bilocal value for the arbitrary 2 measurement choices of Alice, Charlie. The quantity I can be expressed as this. This is the form of I, and similarly J can be expressed on this. As previously said, the correlation matrix can be given as the polar. Here we can denote the eigenvalues of the matrix are B1, B2 as beta 1, beta 2. Next, to fulfill our aim to maximize this with respect to the block vector, here this all the states are the generic form. Choose the vectors in this form, and we can easily find the maximum value by imposing these restrictions and get, this is the maximizing technique, and we get the S local maximum as this value. Consequently, the state rho AB1, rho B1, B2, and rho B2C can violate 3 local inequality if and only if this quantity is greater than 1. For this inequality, a criteria analogous to Herodic criteria can easily be get by applying Cauchy-Schwarz inequality, and we get this 3 local things is less than S AB1 maximal of CHH value, SB2, B1, B2, and B2. We get the extension of the result for n local scenario. We take the state like this tensor product of this n minus 1 states for the n local chain network captured in the earlier figure. And we have the, for this scenario, we we have the I is this form, J has this form, and concluding the value of S1, maximizing it, we find this is the form of the, sorry, this is the form of this, and all the eigenvalues come from the matrix R as previously discussed. Now, if we further generalize the situation from this chain to star, star means there is a middle party and there are say n number of other parties in the star separate things, and there are n sources, then we find in the case of chain, you find this is the summation thing, and if you and this is the product, and for the star network shape, you find this S is this product from what T1 and T2 are the two greater eigenvalues of the matrix, and this result is not this not follows from Gissin's or other. This is a thing we have found in our paper, and it is already published in Physical Review. Okay, this is how we showed that the violation of in local inequalities in chain shape and star shape network, generalizing the result by Gissin's and Androli et al. Okay. Now, next question arises that what can we do if we go more complicated networks? For that, we chose the triangle network situation. Thus, what is the motivation? Thus, in basic quantum networks, what we have showed, that is bilocal network, we have the result by Gissin, and that says if one of the two states violates CHS, then the bilocal integrity will be violated. Extending this result, we have violating condition for n local scenario with chain star separate network. For chain structure, we can say that for n local scenario, n minus 1 number of states should be well non-local to give n local violation. And for star network, we can say that only one well non-local state is enough to violate the bilocal new. So as in general extension, we have to check the existence of such condition for a network scenario for three parties with fixed input, say triangle network, also in for other complex network situation. The first situation is the triangle network. This is a closed structure. The important thing is this triangle network. This is a closed structure. For joint measurement, we have choose a we have base state measurement till Gissin et al. Proposed, and now till Gissin et al. Recently proposed a new one called elegant joint measurement. What actually in Carroll's lecture he also shared this elegant joint measurement by Gissin et al. For triangle network, Gissin et al. Showed that base state measurement will lead to a triangle local model for joint correlation probability ABC. So we need a different measurement setting other than base state measurement. The basic difference which made an effective result of our triangle network is replacing fully entangled state by partially entangled. This is the key things we have used. To understand these measurement settings, we should start with four vertices of a tetrahedron in a phi-k sphere, block sphere, you know, who is using cylindrical coordinate one obtain the natural correspondence with the qubit states in this form, considering the following two qubit bases constructed on antiparallel spin, just like Bell states. We have this is the partially entangled states. Now considering three independent singlets of the triangle configuration, assuming that Alice, Bob, and Charlie each perform the elegant joint measurement on their two qubits, and the resulting correlation is PTR ABC, where ABC are 1 to 3. By symmetry, PABC is fully characterized by three numbers corresponding to the case A equal to B equal to C, A equal to B not equal to C, A not equal to B not equal to C. By a not too complex computation, Gissin showed that this quantity is equal to 25 by 64. To check this probability distribution is three local or not, Gissin constructed a local model where this three local is given by probability is given by this value with probability Q. For a suitable value of Q, P3 local equal to B gives this value, confirms that is a non-3 local things. Next, using elegant joint measurement, Travacoli tailored a bilocal inequality for Alice, Bob, and Charlie, with Alice and Charlie have 3 inputs, 2 outputs, and Bob 1 fixed input, 4 outputs for elegant joint measurement. This is the result they have shown, where S is this expectation value, T is that expectation value, sum average over, and Z is this value, maximum of these expectation modulus of the expectation values. This inequality is checker for the bilocality with elegant joint measurement. And using noisy singlet, Warner states rho I is where psi, this psi is the singlet. They have showed S3 is equal to 0. Here theta equal to pi by 2 gives the Bell state measurement. Now, what we have tried to do, as we have a new tool for Bob in bilocal network, we have applied elegant joint measurement to find the bound for two shared Warner state, not the Bell state. This is the noisy state. Using the inequality of Branchia data of this, let the source between Alice and Bob distribute, say, Warner state with visibility V1, and a second Warner state between Bob and Charlie with visibility V2. This is the row 1 and row 2. These two, this psi minus is a singlet. The measurement choices of Alice and Charlie are simply this. These are not common, these are dot. No, this is Alice and Charlie. So, okay. This is the Alice and this is the Charlie, where A is this form, this is the spherical coordinate. Using all the measurement setting and states, we have a result this, where this quantity greater than 1 gives the violation of bilocal inequality. Theta is the deciding factor for the joint measurement from BSM to elegant joint measurement. And for theta equal to pi by 2, it is the Bell state measurement. And theta equal to 0 gives the general elegant joint measurement. By this result, we can get a better critical visibility, but the process is still under further observation. Instead of noisy Warner state, if we share entangled state and the generic quantum state between Alice, Bob, Charlie, respectively, we get nearly same result as provided by Gissin et al. That only one non-local source can violate bilocal inequality, but here the violation depends on the values of theta also. For more complex structure of network, where a party can receive more than 2 particles or more than 2 sources, we have a general joint measurement settings, and with general fully entangled state, that is GH state. Now we are working on these joint measurements with partially entangled state. For triangle network, we have 3 situations. One, the 3 states shared between Alice, Bob, Charlie, and are maximally entangled state. 2, the states between Alice, Bob, Charlie, are maximally entangled state, and the other one is the generic quantum state, and the third one is the 2 state will be generic, and other one is this is row B system. We have a result that only one maximally entangled state can produce a probability distribution which cannot be reproduced by any local module. But for the greater view, that is for any polygon structure, we are still striving to find analytical result. So for triangle things, we have some result, but for more complex network situation, we are trying to get the analytical results. Okay, we have completed. There are some references. This is the Gissin's latest work on elegant joint measurement. Thank you.
Thank you. So now the session is open for question and answers. So any questions from the panelists or the attendees? I hope I am audible.
Yes.
Am I audible?
Yes. Yes. Raman, you are audible.
Okay. Okay. No, because I'm not getting any response. So
Ah.
because today the network is also slightly bad in our building.
Yes, you are audible.
Okay.
So I am stopping sharing.
Yes, sir. Yeah. Okay, if there are no questions, so we thank Professor Debashis Sarkar for the wonderful talk. The next session will start at 5:30. So we are having Industry Academia meet from 5:30 onwards. You can see the panel members, which is on the display here. All those are also are welcome to join this industry panel discussion.
Can you hear me now? Can you hear me? You can hear me,
Yes.
right?
Yes.
Okay.
We can hear you. Yeah.
Okay. And
Yeah, we can hear you. Yeah. Okay. So we are having this industry meet from 5:30 to 7, and after that we have another talk where Professor Subhashish Ghosh will chair the session. So we conclude this post-lunch session, 3 lectures. I thank all the 3 speakers, Professor Sarkar, Professor Marine, and Professor Karol for the wonderful talk in this session. So those who are in this building at Jodhpur, we will be getting a hot tea, but unfortunately we can't teleport.
We are in our place. Okay.
Yeah.
Enjoy.
You can
enjoy
have the tea and give us the. You can have the tea and give us the bill.
Yes.
Or whenever we very soon we can have a meeting, and then
Yes.
of course in the physical mode, and we can have a tea together.
Yes. We hope so.
We hope so. Yeah.
Thank you.
Yeah. Thank you.
Hey, hi everyone.
Hello, can you hear me?
Yeah,
Yeah.
we can hear you. Yeah. Yeah, we will start in a minute or so. Yeah.
Yeah, that's fine.
Hello, I have joined.
Yeah. Thank you, sir. Yeah. Yes. Yeah.
Good afternoon, Narayan sir. Are you able to hear me properly?
Yeah, I'm able to hear. Yeah. Yes, sir. Yeah.
Thank you.
I think Vijay is also trying to join. Give 2 minutes for him to join. He doesn't.
Okay.
He's searching for the link.
Okay.
Okay, so good afternoon to all of you, panelists, industry discussion panelists, speakers, and all the participants. Welcome to the industry panel discussion of QFA-2021. We have Dr. Arvind, who is the Vice Chancellor of the Punjabi University, Patiala. So a few words about him before I hand the mic over to him. He did his PhD from IISc Bangalore, following which he joined the Department of Physics at Guru Nanak Dev University, Amritsar. Later, he moved on to IIT Madras, where he was head of Department of Physics Department, until in 2007, when he joined IISer Mohali. So he's obviously a very busy person. I don't want to take any more of his time, so sir, please, if you can take over. Dr. Hello.
Hello, am I? Is it? I couldn't hear the last part.
No, I was asking you to take over, sir. Am I?
Hello.
Hello.
Yeah. Okay. Maybe I'll just take few minutes and then. Yeah. Today's panel members. I am Narayanan. So this QFA 2021 is the conference day 2. We are having industry academia panel discussion. Professor Arvind, Vice Chancellor, Punjabi University, is the moderator. We will be shortly joined by Professor Shantanu Chaudhary, Director, IIT Jodhpur, Dr. Murli Mohan from DST, Mission Director, NM ICPS, DST, he has already joined. I think I'm also seeing Vijay Raghavan Varadarajan from Infosys has joined. Sardar, Director, DYSL, Quantum Technology. Yeah. Hello. Quantum Technology, Mumbai. Okay. Yeah. Welcome, sir. Yeah. Dr. Shantanu Sardar, Director, DYSL, Young Scientist Lab, Quantum Technology, Mumbai, has joined. I'm also seeing Dr. Jayakumar Shah, Infosys, has joined. We have sent an invitation to Dr. Manish Gupta, but I think he's unable to join. I'm also seeing Dr. Gagi Das Gupta Research is with us today. Dr. Sumanta Sarkar, formerly with TCS Hyderabad. I hope he is also there. So these are the panel members. We have already circulated or requested the kind of discussion. We would like to take it forward for in terms of quantum technologies, the academia and industry partnership. How it should proceed? So I request Professor with thoughts. We can start this discussion panel.
Hello, have you over to me?
Yes, sir. Yeah.
Yeah, okay. Yeah. So, first of all, it's a very nice effort that such a panel discussion is happening, and I'm very happy to participate in it. Let me put it in the following way that quantum technologies as an area started roughly at the time when I finished my PhD I finished my PhD in year 1997, and quantum technologies were just beginning at that time with theoretical developments which had taken place and some initial experiments that were happening. So in some sense, I have seen the field grow right being inside and also along. In India, we joined this area a bit late in terms of recognizing its importance. It took us a long time before we realized that this area is very important. However, I'm very happy that now the Indian scientific community and the policymakers have seen and recognized the importance of this area with two major initiatives, one being the QUST, Quantum Enabled Science and Technology initiative of DST, and the National Mission on Quantum Technologies, which is so it is very clear that the future technologies, the sophisticated technologies of the future will have a strong quantum component. And therefore, it's very important to develop these technologies all over the world, and particularly for every country like India, which aspires to be a world leader and a world power and is an independent state. There are so many different domains in which quantum technologies are coming up. It is computation, sensing, and even many other areas like quantum biology and so on, which is showing the way that there may be many more technologies in the future which will be quantum in nature. So this area is very exciting at the level of fundamental research and also at the level of applications and real time applications in terms of producing technologies and bringing them into market and working with like-minded partners in agency and industry. Now you see, if it is a question of technologies, there is academia alone cannot take it forward. So this particular culture of partnership between academia and industry is extremely important. And unfortunately, such things are not very common in our country. We have not, there are not too many areas in which we have successfully carried out such activities where we have participated and partnered in a big way. So therefore, as the Quest program is developing, as the national mission is developing, it's very important to develop ecosystem and environment of industry academia partnership towards quantum technologies. And this is again a very good time because there are hardly any industries at the moment. So we should motivate people to build small and medium-sized industries around quantum technologies. We should create an atmosphere where investors come forward and invest in this area in terms of business ventures. And all this will happen only if we make the industry and the investors aware of the potential which the quantum technologies hold. So with these words, I would say that we go on and listen to the panelists and see how things happen. It's very, very important here in some sense, in which we are launching the missions and looking forward to these collaborations. And this is a very key point that if unless industry comes forward, quantum technologies will not really become a reality within India. And all the work we do here in terms of fundamental research will get pumped into industries for the other countries, because at the end we'll end up publishing our work in journals. So it's very important that we hold some of our results and convert them into technologies right in this country. So maybe we can move on to panelists now and hear them.
Yeah. So I request each panelist to can switch on their mic and then put their thoughts. So let us begin.
Narendra, what is the format like? What is the format?
So we have said that the roadmap of for the quantum technologies, how the academia and industry should kind of come together and
What I mean to say. So what I mean to say is, are you giving 2-3 minutes to give the first type of thoughts, and then we'll go around
yes,
and
yes,
then come
yeah,
back.
Yeah. I think the first 2-3 minutes each say under what they foresee with their background and how the other places or whatever their inputs regarding the academia industry, how as Professor Arvind said, or you also spoke yesterday, in the both the domains, how we can participate. That they can say first 2-3 minutes opening remarks from each of the panelists, and then we can again take up another.
My suggestion will be that you invite specific panelists. So you say the name, that will become simpler.
Okay. I first invite Dr. Gargi Das Gupta, IBM head, IBM Research India.
Yeah, thank you. Can you hear me well?
Yeah, yes.
Yeah.
Okay. Yeah, so no, I think a very important topic, and as Professor said, very important year right now. The technology is, of course, growing and will continue to grow, but our government of India has expressed a keen and sincere interest in making sure that India is one of the technology giants in quantum. So a couple of things I wanted to say is about quantum related academia industrial partnerships. Before that, some general, I think most of you know here, but I also wanted to just reiterate what is the government mission, right? It was called out by Professor, but so there is a 5-year national mission on quantum technologies and applications. DST is of course responsible. MIT is a key player, and there has been a central technology innovation hub that has been created for quantum, right? So in the country today, as we talk, there is a TIH created for quantum, and ISER Pune is at the center of this hub, and it's going to be a hub and spoke model. So many other partnering institutes will build around this hub as spokes, and it's going to obviously do 3 things that are important for the nation. One is education and skilling. So develop resources both at undergraduate and graduate level. And there are a few universities that do quantum courses. I'm coming from IBM, so I of course have the IBM view, and I know that we are partnering on many of them with the institutes, with NPTEL for actually skilling. So skilling is a very important factor of getting this national mission to work, right? And skilling not only means courses, but having graduate, postgraduate students, integrated into the adoption through industry-led research, right from day one. So it's not that we do research for 5 years and then we do KT and technology transfer and it becomes harder. So it's day one, you have those graduate and postgraduate students integrated. The second is exactly this industry enablement that got talked about, right? Setting up of industry academia partnership. So which means that quantum machines, the real quantum machines are far and few, right? We as IBM, actually, we have these access to these machines through cloud. Creating this access in a much more ubiquitous way will help facilitate the skilling, will facilitate research and facilitate interest. And yes, theoretical research will continue to grow, but a lot of the industry-led applications, like let's say I want to use quantum for a very, very hard problem on logistics planning. I want to use quantum for getting out, doing molecular simulation so that I can have the best pollution-free fuel invented, right? All of these are applications and there's a whole stack that is needed, and getting access to quantum machines is probably the first one. And yes, we can do with simulators, but if people are building real quantum computers, then why not get access to them? So that's the second thing that we have to enable via this interest. And the third is, what are the long-term mission strategies, right? What as a nation can we imagine that quantum computer will help solve? How do we go towards it so there's new jobs created, economic growth, India becomes a leader in a global supplier of quantum devices, components, and all of that, right? So I think it's, so just to summarize, the partnership is critical, the timing is critical, the government is committed. So I think this is the right time for industry and academia to come together to partner on all these three things: education, industry enablement, setting up long-term missions and strategies. So I'll stop there and pass it on.
Yeah, since Dr. Dasgupta touched upon the ISER Pune, the TAH, I request Dr. Murli Mohan to touch upon some of the things in the context of academia industry partnership from the DST and the government point of view. If you can say a few words on that, it will be nice. Yeah. Over to Dr. Murli Mohan.
Thank you, Narayan. The intention of the government is proliferate the quantum technologies. That is, proven by launching, a small R&D project called Quest, and that is up and running. Now, also, if you look at, the translation aspect of this R&D into a type of tangible products, or if possible, the development of devices. So that is the mandate probably given to the Technology Innovation Hub at ISER Pune. And that is a type of an independent structure which has a Section 8 company, not for profit, and that a lot of industry people are board of directors. So given the freedom and flexibility to collaborate with the industry, the TAH has the mandate to go for translation and as well as product development. So that is the type of a platform for academia and industry to collaborate. Now, my fundamental issue is, though government intent is very clear, they are launching very soon National Mission on Quantum Technology, is rightly pointed out, another 5 years. And they are also stress upon the bringing these three helix together. But our experience as of now is not much encouraging. The industry is looking for something which we are not able to capture. We are looking at them as a co-partners and co-developers, and we are trying to create this type of platforms, not only in the quantum, in other areas, other technologies also. We have around 25 technology innovation hubs. Now, there is something, there is a gap what government intention and what is the plan, and then what industry requires. We expect them to partner with these as a code developers and code partnering with the product development. And I think there is some gap. And if somebody fills that gap, what exactly they are looking and how we can enable this, the 25, ecosystem that what we have created. I think in this panel that will be a nice, way of, points for me to take, back to my home. Actually, I look forward for the type of specific things that has to emanate from the industry. Yeah, I will come back with other things after the next round.
Okay.
It's a mix. Start right for you. You are frozen.
Okay. No, it is fine. It's fine. Okay, now I request Jaykumar Shah from Infosys to give the initial thoughts in this direction.
Thanks first to Dr. Gagi and Dr. Muli for walking us through all those things, because that kind of covers a lot of ground in terms of where we are headed and what what is it that we are looking at from the partnership perspective. Now, I have mostly been a part of the high-tech manufacturing group within Infosys over the last 16, 17 years. So my experience has been more with the industry side of high tech, right? So there are a few things that I see, and I like one of the core things, and that this earlier speaker kind of very well covered, was that we are at the cusp of so many different emerging technologies kind of merging as well as picking up at this point, and quantum being something which is very much at the nascent stage, right? Like which has not even hit the knee of the curve, so to say. So this is the time when you get all the excitement and creativity that you can bring to it, right? So the way we look at a particular application and then kind of think around how this technology can be applied to different industry problems, different social problems, different government problems is a unique spot to be in, right? So one of the things that I have seen from the customers that I work with, most of them are semiconductor industry, from semiconductor industry or OEMs or software providers, is the fact that most of the value chain works in some sort of clusters, right? So the whole idea of cluster competitiveness, I think, would becomes very important around quantum computing, right? And we being like geographically, as well as we being the pioneers and the hub for the software side of quantum computing, I think we are uniquely positioned for some of these some of these aspects, and kind of collaborating across the world with different partners, with different academic research institutes for doing these, right? Like whether it is around topics of quantum machine learning, or around metrology, or quantum finance, or even what we had discussed earlier around cryptography, right? Like there's a lot that we can bring up here, right? So that's, I mean, that's where I see us as of now. I'll add as we go along in the discussion. I hope I was audible.
Yeah, you were audible. Yeah. Okay. May I request Vijay Raghavan for the Rajan to speak from the industry point of view.
Thanks, Narayana. So, thanks to the speakers. They have put the point nicely. So first of all, I wanted to touch the point that Vijay, timing. So, why quantum?
There is a lot of echo,
especially now. So you can see.
Vijay, sorry to interrupt. I think the moment you started your video, your voice started lagging and breaking. So if you want to just be on voice, I think your voice will be clearer. Vijay?
Is it better now? Am I audible?
I think it's better, but yes, Vijay, much better.
Yeah,
Okay.
you are audible, yes.
Okay.
Yeah,
Thanks
please
for all the
continue.
panelists and IIT Jodhpur for organizing this. So I wanted to start the timing or why quantum now. So everyone knows that the quantum is getting hype, or every country and government is investing heavily onto this. So the reason may be the current situation. For example, we are looking for a better vaccine for solving the pandemic. It is taking much more time, but we have a quantum power, so we are able to solve it, do those things in parallel, and able to give a solution in short span of time. Or the threat for online security, or the climate change. So kind of all this problem is triggering or telling that what is the importance of a quantum now. Okay? So that's where everyone started looking onto the quantum. So not only on quantum, you can see any emerging technology, the origin of research or the starting points are from the universities. So I need not say that they are good at how good they are in doing the research. So that is the very starting point of all kind of emerging spaces. So obviously quantum also started from this university. Now, after doing a quality research, doing a publications or creating an awareness, you need someone to consume those things. So industrials are good at doing those parts. So I can see to this, the pedals of a bicycle, both the pedals, it's an academic as well as the industry. So we have to collaborate and see to this, create a quality research or enable them future talents or quantum resources. At the same time, we need to gauge that what is the requirement in the industry. So what kind of problems or what we are anticipating, the quantum has to solve that. That we need to feedback or put into this loop. So that's where I see to this, industry and academia has to go hands in hand and do those research. Okay. So in Infosys perspective, I am part of this ICETS, Infosys Center for Emerging Technology Solutions, where we are looking for a say, university collaboration or incubating startup wings or international, that is mentoring international and Indian talents in form of InStep and Portage internship. So these are all some of the activity we are doing to do a collaboration things. So maybe I can reserve my thoughts for the next round. So this is where I am seeing the importance of a quantum and essential thing where industry and academia need to collaborate and work together.
Thank you, Dr. Varadarajan. And now I would like to request Dr. Shantanu Sardar, Director, Young Scientist Lab on Quantum Technologies, to give the initial thoughts from the point of view of the difference.
Thank you, sir. I hope I am properly audible. So glad to be part of this discussion on this partnership, which is very important aspect and it need to be addressed as fast as possible. So during this process, I will share my few thoughts and we can discuss and debate on them. And as an introductory remark, I am from DRDO, and DRDO is already working on various aspects of quantum technologies and dedicated a laboratory to solely work on quantum technologies only. And we are very closely collaborating with many academias, IIT Jodhpur being one of them, and a few industries as well. So jointly working, what we feel is the key for faster progress, catch up with the global trend. Now, I will also highlight the role of government R&D organizations also, like DRDO, to achieve this objective of academia and industry collaboration, and how we also can contribute to the cause. DRDO also have some initiatives to promote academia and industry that I will be explaining later in subsequent discussions. And right now, this, as Murli sir clearly explained very briefly in the beginning, that academia-industry collaboration can be through a dedicated translational research center aimed at academia industry. They can jointly do R&D, publications, patents, product development, and etc. as per the scope of work. So we see that world is progressing very fast. And in India, a lot more industries, MSME startups need to come forward and leverage available funding. And strong bond among all the academia, industry, as well as the government R&D is very essential to catch up and retain the expert manpower in India to make a healthy ecosystem. So with these initial thoughts, let me conclude here, and thank you all. Sir, yeah, I will stop here, and in the subsequent discussions, I will detail more.
Yeah. I request Professor Alvin, based on this, can you guide us for the your suggestions for the next round? Okay, I think he's signaling. Professor. Yes, okay, may I request Professor Dasgupta about like when IBM have a partnership at various places, what is the role of academia, and what one expects from the academia, and what kind of collaborative things together one builds up? Maybe you can throw some light, that will be nice.
Yeah.
And including some of the past experiences. Okay, this is what we did, and you know, this is the kind of an outcome of that collaboration. Yeah.
Yeah. Yeah. So I guess what you're saying is that give examples from the past outside of quantum, and then say what we can do for quantum, right?
Yeah.
Yeah. So
yeah.
I mean, IBM research is big on university collaborations, right? The way we do our work, of course, we have to build our products that helps IBM innovate. But a lot of the N+1, N+2 innovations that maybe the business is not seeing today is done with the academia. And there are use cases of these partnerships with AI. I mean, AI, of course, is something that everyone wants to do, very popular in the last 2 decades. Right? And we have great AI partnerships with 2 leading institutes where, and I'll give you 2 examples of how we do this partnership and you know, how we take it out in the product. So the first one is around handling language and handling language variations in all the multilingual complexities that is there in India, right? Again, it's a very geo-specific problem. If we want AI to be, you know, infused in every business, every conversational AI, everything that we do, it is very important to understand the nuances of Indian languages. So we have a partnership with IIT Bombay where we work on technologies. The problem with some of these Indian languages is that there's not a ton of label data available, right? Which is not true for the Spanish and the English of the world. So while we can build global models on and very, very deep learning models on a ton of data for Hindi and for the local languages of India, that approach doesn't scale. So we work with IIT Bombay on these problems, and once they are mature, we also help contribute back to the product. And this is our natural language products, which is obviously Watson based. but it's been a very, very successful relationship because we do get to publish in the top computer science conferences and journals. And we do get back and try and create for our Indian banking customers solutions that are built out of this collaboration. So that works very well. The other type of product building is something that we do in the world of cloud, where we have a partnership with IISc, but there's no IP, there's no intellectual property that we're trying to save or protect, right? So it makes the collaboration very free flow. It's open source, which means IISc and IBM Research collaborates on open community projects. And yes, if IISc has 10 or 20 faculty and students working, IBM has 10 or 20 faculty, but there's rest of the world, it's all open source, right? And the developer community is very, very strong in India. So it's open to the rest of the world, it's open to students, it's open to faculty. Anyone who has an interest or something to say on that project can contribute code, can convert towards a community, right? So that's the different model. And we'll have to see for quantum which model works. But like you said, I mean, for everything in IBM, I think academia partnerships is very, very key. IBM believes in quantum networks, okay? So the quantum network is, of course, IBM, then industry partners and many other clients and collaborations. Today, we have over 100 clients and partners on our IBM quantum network, which itself tells you that, globally, there are about 100 such institutes or companies which believe that they have a use case for quantum, which believe that solving a particular problem is going to transform their industry. So we have about 100 such. In India, we actively collaborate, of course, with ISER, with ISIs, with IIT Madras, with IIT Kanpur. In fact, we have a list of 10 universities where we are collaborating with. And each of those collaborations are at a stage where it's not just IBM. So IBM does give access to its quantum computer. So that's stage 0 of the collaboration. So the faculty and the students in that university has access to quantum computers. But the stage 1 and 2 is really work out with an industry partner, like with a supply chain client, with a financial client. What is the problem area that is keeping you awake at night, right? Which when quantum computers come, is going to be imperative for you to solve. So it's always going to be this partnership model where IBM provides access, maybe research manpower, academia brings in most of the research skills, and then clients get the use cases, right? And this is the 3 in a box model that we've been trying. And it's early days, we'll see, but hopefully this gets us to the point where, we start building products that influence the client, helps the client on real quantum computers, looking forward to a day of quantum advantage in the next few years. Hope that answers your question.
Yeah, very much. I don't know, Professor Arvind, since he was traveling a few minutes ago, he's yet to join, looks like. Professor Arvind? Yeah. Okay, for the time being, I will continue.
Hello. Yeah.
Requesting the.
Yeah, no, I have been listening to all the comments.
Okay.
I think as a first round, we have had a very good set of points which have been made. We also have listened to people talk about the specific things that they are doing, specific collaborations that they have, and some others expressing certain broad people, of course, having a platform and a place and a translation hub is one thing, but specifically identifying areas and specific quantum technologies that are going to be incubated is very important. Because, it is not that we are going to come up with a multi-purpose quantum computer tomorrow in India, or we are going to come up with. So even these smaller initiatives, we should be very specific. And it is that specificity and detail which is needed for such partnerships. So that I, at the moment, feel that we don't have. And that is what we should, I think, focus. Even if it is 3 technologies, 5 technologies, 8 technologies, 8 specific industry academia collaborative projects, that would be very important. I know DRDO's main concern, of course, is quantum cryptography, and that would be more like a dedicated crypto system which DRDO can use for its applications. That is very specific and very welcome. However, we should actually do a brainstorming session maybe, where we consider, as all incubation centers do, say about 20 candidates, and then we form working groups, and working groups look at those 20 ideas, develop them, brainstorm them, shortlist, say about 10, and then bring it down to say 5, and those 5 are specifically developed and funded and taken out and in some sense rolled out. So that is the process I think we should follow, where we invite joint proposals, we even stimulate proposals, because such proposals are difficult to come given the small community. And we should also see where quantum plugins can be used for various purposes. I mean, if you talk about AI today, most of the AI is classical computing. Now, where exactly there can be a quantum advantage? Sensing, of course, we already know, and we should be very specific in terms of the projects. So I would say in the next round, as moderator, what I would float is the idea of coming up with specific ideas for the next session. Thank you.
Maybe based on the input, I would like to request Dr. Shantu Sadda to say a few words on what Professor Arvind rightly suggested.
Yes, thank you, sir. So, Sarah suggested very good input, information and suggestions. So accordingly, I will mainly cover 2 aspects. One is that where DRDO stands and how they can contribute to this cause. And another aspect is that how I think about the other methods and other suggestions that can be suggested right away, and we can debate on them. So first of all, as we see this a very brief idea, what we envision is that this technology development roadmap, this is basically comes from proof of concept development or demonstration. Then it goes to prototype, and then it goes to product. So now generally the proof of concept is being taken care by academia, prototype by different R&D organizations, and finally the product level maturity is achieved by industry. Now definitely this complete demarcation is little fuzzy, but this is the overall idea. Now in this direction, so what we see the role of DRDO, or for that matter any government R&D, is twofold. One is that to achieve prototype level maturity and offload to industry, and another is the hand-holding between them. So basically, we should improve the TRL level, what academia has done the proof of concept, or maybe gone to the prototype level. Whereas for the other part, DRDO have actually many solutions, both for academia as well as for industry separately. So like for the academia, we can fund different low TRL level research. For different methods are already well planned. That is, some CARS project is there. Some collaboration centers are already being worked out in different IITs and other academic institutions. Like One is already going on for more than 2 years or 2.5 years in IIT Delhi. Another research collaboration center is being established in IISc. Then in many other academic institutions, we are planning for the same to promote the research in this direction. And on the other hand, we have many process to encourage industry in these directions. Some of them being these development contracts or development come production partner, so that the industry can be involved with DRDO from the beginning itself when the prototype development is going on, so that later the TOT will be much more fruitful and much more easier to offload the technology. Another aspect which is mostly focused for MSMEs and startups, that is a technology development fund. So if DRDO has some technology, or it may not work in this direction also, but this idea, they will fund the industry itself to develop those technologies directly. And then the technology, when it is developed, and then DRDO can stop handholding or they can continue, and the technology industry can take up on their own. So these are some of the aspects where DRDO can be helpful for both academia and industry. And apart from that, there are some idea where academia can do right away. What I feel, that is, it can take some leading role in a project which is funded by, suppose, government R&Ds or any other users. And then it can offload some of the sub-projects of that project, which have, those sub-projects can have a higher TRL level, so those can be selected. And then those can be offloaded to industry with specific skill sets. Because suppose, just for example, for quantum computing, for quantum computer development, as for example. So there are some of the activities, those are very low TRL level, some of the activities that is very higher level. Just for example, the user interface development for a quantum computer. So those can be offloaded to an industry with specific skill sets. So that can be considered from academia side while taking up the project. So this basically will not only fast forward the overall progress, but the industry will be involved from the beginning itself, even if the overall TRL level of the complete activity is low. So that will boost the industry academia collaboration also. Another thing what we can think of is that we should mix the long-term and short-term application-oriented research. So this may be planned to attract more industry and especially these MSMEs or startups, because for MSME and the startup, one of the main target is immediate revenue generation as per user requirements. Because the fundings are less for MSMEs and startups, accordingly they can one of the major focus areas there. So that we can attract them by having some short-term applications or milestones. And in parallel, we should also be in touch with user, or maybe make them aware about the long-term potentials of various technologies, so that the funding comes up in that direction as well, and keep them in loop for long-term milestones. Then infrastructure, which are available both in industry, academia, and government R&Ds. So if we can share these infrastructures among all of us, I think that will boost the overall progress in a collaborative manner. And definitely the main, one of the main objective of academia is to develop expert manpower in these directions. So there academia has to take a role. And if this complete ecosystem of academia, government R&Ds and industry, if this ecosystem is healthy and flourishing, so that will not only develop new expert manpower, as well as we can minimize the brain drain also. Because after academia, if there are not much scope in India, then definitely the PhD students or MTech students, they will be going abroad. So if this ecosystem is healthy, they will be retained here. That is one of the major aspects. And one more point that I wanted to focus is that we should identify and accelerate some of the particular areas. Suppose the ecosystem, we feel that these are some of the areas where we need some more support to accelerate the overall progress. So that we should identify, and then we should help in those areas more in a more focused way, or in a more we should emphasis in this direction. Just for example, this supply chain, talent pipeline, then maybe those applications, whether those are being targeted for real world use cases or not. Definitely, this is a very vast topics, and not many of the applications won't be right now have real world use cases or cannot be implemented in this direction. So that's why I previously told about the long term, short term, but those things has to be taken into considerations. And last but very important aspect, what I feel that if we all the entities of India working on quantum technologies are able to map the potential quantum tech with users and keep updating this overall map, then I think it will be good for our collaborative progress. So with this, I will stop now, sir. Then maybe we will discuss and debate more on them, and I will get back.
I would like to request Jaykumar to give his thought on in continuation with Dr. Shanta Sardar.
Sure, sir. In fact, sorry, you were saying.
So there are few attendees also. So I wanted to ask after 5 minutes, maybe we can open up the chat box and then do that. So I request Jaykumar to speak.
Sure. So I have 3 or 4 observations that I wanted to kind of share at this point, right? Like one very important thing that everyone mentioned is that the government, the academia, and the industry needs to be collaborating very closely. But what Dr. Arvind rightly said, right? Like what would be important for us would be to identify those specific use cases that each of these collaborations can work towards, right? And I mean, I'm just referring to some of the things that I was looking for in terms of where else in the world is this collaboration between academia and industry working well at best of the universities, right? And if I look out, they have very focus areas in that sense. While I was looking at UC Berkeley, I saw that majority of the research were around deep neural networks and the machine learning space, right? Similarly, Oxford, I could see that a lot of their research was directed towards photonics or towards the hardware side of it. Waterloo was more towards computational part of the quantum computing, right? So they were talking about optimization and simulations and drug discovery or material design and things around computation, right? So focus area is one point that I wanted to mention. Another point I wanted to mention was around skill development, right? Now, one part of it, while there is this deep expertise that is required in the fundamental research on the hardware side, with the cloud computing and access that Dr. Dasgupta was earlier talking about in terms of having Watson on cloud or having many of the other so there are similar solutions which Microsoft or Google or Rigetti also has on cloud, right? So if we can bring that, and how is it that we can develop skills through maybe research opportunities, through courses, or through some sort of use case sponsorship, right? Which works more into crowdfunding and crowdsourcing perspective, which is not very academic in that sense, but which is more towards building it with everyone's input and crowdsourcing of ideas, right? So that skill development piece is the second thing that I wanted to talk about. And third is, of course, the use cases that we can build at this point, right? And it ranges from applications till fundamental research. Like there's a whole gamut of things we can do, right? But especially, so if we take some of the more mature topics around this, where we have certain examples or certain things around, let's say cryptography or machine learning that we can include, right? Then there are use cases which can be addressed, right? So maybe if we take banking and financial services optimization, that could be one good area around that, right? Or if we talk about healthcare, diagnosis is one. Or if we think about simulation designing of certain aspects, so those kind of application-based things can happen. The second layer could be around the algorithm or applied research, right, where we are talking about new sensors or new devices or new algorithms to apply for specific business problems. So maybe having that applied research in that layer. And then, of course, there is the more fundamental research side of things where we can think of a lot of components and hardware kind of development. So those things around use case development, I think having multiple brainstorming sessions around each of these topics might lead us to some good ideas where all of us can work together. So yeah, those are my thoughts. Over to you, Dr. Mohan.
If I could just add on, because I also have a hard stop to Jaykumar's thoughts, right? I think he made some really good points, and it comes across as things that we could actively do. Can I have 2 minutes?
So apologies to
I don't know if it's my line or.
We can hear you well, Dr. Dasgupta.
Okay, all right. So maybe I think I just want to echo that it's very important to understand that, sorry, can I have 2 minutes?
I think you can go ahead, please.
Yeah, okay. So I think the skilling part, I talked about it. Skilling is very important. It's just a small example of how much it can touch, right? We created an open, a free course on NPTEL, and instantly, in a matter of few days, I think 15,000 students signed up, right? And you think of scaling that up to 50,000, 100,000 students, right? These are, and the course material is something that we could partner on, but make it available. So that's an example. The other thing to realize is why are use cases so hard to get by is because quantum is not at the state of AI, right? That it can actually do a real thing. It can actually get to advantage much better than a traditional compute today, right? Hence, there's a lot of work getting done on hardware, on sensing and computing. But it's very important to understand that for something as big as quantum, it's not just one thing, right? It's not just the hardware. It's the hardware. It's of course the systems, right? And how do you push the boundaries to reduce quantum errors and reduce the qubit volumes. But there's also the runtime that sits on top of it, right? And think Python, Jupyter Notebook like AI. Is there an IDE that developers can today start using and creating their first quantum equivalent of the traveling salesman problem, right? So the runtime is very important, and we need research there. We have a Qiskit runtime, which is very popular with developers, but we need the community, and Jaykumar made this point, right? It's out there, but we need a lot of participation from academia, from community to contribute there, right? Build runtimes, build libraries, build models. So that's another core piece of research. Then there's the algorithms and the models. And yes, the models, we could say from India, we focus on finance, we focus on optimization problems, maybe machine learning, maybe natural sciences and molecular discovery, but we pick 3 or 4. And then that whole stack needs research, investment, development. And the community has to come forward, right? I mean, these 2-way, 3-way partnerships are great, but the more that we can do in the open, the more will be the accelerated path. So I wanted to echo, what Jaykumar said, and I think those are, so we pick a few areas, we figure out, yes, there's hardware, but there's also the runtime, there's also the algorithms, and then those are pivoted on certain use cases in certain industries. If we clean that up, I think we will make a lot more progress. Okay, I think that's all. I'll keep quiet.
Yeah, thank you, madam. Yeah, I would like to now request Sumanta Sarkar with the TCS formally to kindly say a few words in this regard.
Hi. First of all, thank you for this invitation to take part in this panel discussion. And secondly, I would like to say that earlier I was with TCS. Now I have moved to University of Warwick in the UK. I saw that it's not mentioned there. So for the record, I just wanted to say that. Anyways, so far I've been hearing from the experts about these quantum initiatives. It's very, I'm glad that India has taken up this initiative. I've heard from some people that India has been led to take this initiative, but I would say it's okay. I mean, it's not always possible to catch up with all the training technologies at the right time. Well, in the UK, I've seen they started this national quantum technology program like 10 years back, and where they formed a group of like hubs, and as in India, there are some hubs as well. So the main idea is that industry and universities, they come together and work together. So for Indian aspect, I can say that let's have some goals. So like in industry, we normally the research industry work in this way. They have some short-term goal and long-term goal. And this is very much appropriate for quantum technology because the technology itself evolving. So what we can do right now, let's do this. For example, QKD, quantum key distribution. I think it's quite possible for 100 kilometers of cities apart. Now we can do quantum key distribution. And obviously, I've seen hardware for generating a quantum key. So whatever we can have now, let's start doing this, and there should be another group who will be doing the research for the what is not possible yet. So we all now don't see that whether quantum computers will be realized 10 years later or 20 years later or 50 years later, but that at least we have seen that the progress. So so now with this progress, things are changing a lot, because I mean quantum technology at one side, it is revolutionizing the drug discovery and other computing technologies, but at the same time, it is becoming a threat to cryptography. So we have Shor's algorithm that can solve the factorization. So RSA cryptography, the RSA algorithms, they are not safe when the large-scale quantum computers will be available. So in this regard, we need to think something when quantum computers will be available, then how can we save cryptography? So there are some algorithms for which we still don't know the quantum algorithm, like some lattice problems, coding theory problems. They're quite hard that still we don't know how to solve with the quantum computers. So then we can use those hard problems to build some cryptographic schemes. In fact, those are available now. So they fall in the category of post-quantum cryptography. It means the cryptography which is still intractable by quantum computers. And NIST in the USA, they have taken the initiative to standardize post-quantum cryptographic algorithms. And they will be available, I think, end of 2022 or beginning of 2023. So, so I personally don't see too much of effort of the on the research on the post-quantum cryptography. Obviously, we need to do the research on quantum technologies, how we can use quantum technologies, quantum algorithms. At the same time, we must also protect the cryptography or the secure communication from the threat of the quantum computers. Because when quantum computers will be available, this will be available to the good guys and also the bad guys. So we must protect the communication from the bad guys, because if they have access to quantum computers, they can do a lot of harm if we continue to use modern cryptographic algorithms like RSA or discrete log problem-based cryptographic schemes. So I think one section in the quantum initiative should also include, like if I'm pretty sure that they have some initiative to do quantum cryptography. I think that quantum cryptography should have one part which is post-quantum cryptography. So second thing is that talking solely about quantum research, the major challenge in quantum research is that resources. So in case of classical research, I mean, we can have a good configuration laptop or high-end desktop, and well, we can at least start doing the research. But in quantum, if I have some we need to do some quantum algorithm, I need to simulate, or I need some resources that actually my quantum algorithm is working or my application is working really. So I need that environment. It's not, so that's not very easy. So I think that's the major problem that I mean, I don't see a lot of people are coming in this. So I think at that sector, we need the support from both the government and the industry. I personally, I like IBM's initiative, because they have opened this qubit 5-qubit Qiskit. I've seen students, they are also using this. At least that's giving us the hint how quantum computers work. So I believe that major industry players will also open up their facilities to the researchers within India, at least for the moment. And secondly is that quantum is such a complex thing, and we cannot do alone. So I think we must include international collaborations. Let's start with universities which are well known in quantum research. For example, Waterloo is very well known, and in Netherlands we have a strong group. So I think we can include them as a strategic partner, and then that expedite the whole process. Yeah, that's my thought. Thank you.
Hello. So I'm seeing Professor Chaudhary is online. I would like to request Professor Shantanu Chaudhary, Director IIT Jodhpur, to give his thoughts in this direction.
I'm not just prepared to give his thoughts. I joined to listen to the
any few initial
from
thoughts,
industry.
I think.
Yeah. So actually, what has been talked about, I think I have understood, and what I personally also feel, that academia, research organizations, and industry access has to be strengthened. This is very important. From our side, from academic institutions, we need to build strong programs to create manpower, which is a necessity. In fact, what Gargi has stated about this NPTEL course, I myself have seen, and there are lots of people registering and doing that course. But there has to be more such strong programs created inside the academic institutions in the country, and which are not just fundamentals of physics, but maybe more application oriented. And if we just order these areas, because I'm coming completely from engineering side, I would say that is post-quantum cryptography is something which is extremely important to look at from secured point of view, secured quantum computations, quantum machine learning, and quantum optimization. I think an institute should pick up some of these areas and try to focus on. And also from an industry point of view, which are also coming up in a very interesting way, is most likely more futuristic is one is quantum radar technology and quantum imaging technology. And in fact, that's something which I would like to add to the list of possible areas to go. So therefore, from an academic institution, my summary is we should build a strong academic research program, strong academic training program, and build a bridge with industry and research labs so that whatever is happening inside the IIT or in university system, find usage at the practical space. But today, I don't think universities are really geared to produce technologies which will go directly to the industry in the quantum field. These are my observations. Thank you.
Now I would like to request Dr. Murli Mohan to suggest, based on some of these and initial observations, what you said, anything is missing or whatever your thoughts will be nice.
Thanks, Professor Narayanan. Am I audible?
Yeah.
Confirm me. Yeah.
Yes, yeah, you are audible.
Okay. Thank you. How much time I will have? Because I'm going to take quite a time now.
I think Murli, you can take time. I think you can. I don't know what is the schedule. Schedule-wise.
Yeah, we are up to 7. The next talk is at 7:30 only. So this program is up to
Yeah. So I will not take not more than 10-15 minutes if possible.
Yeah, sure.
And in between, if you want to stop me, you can stop also. Absolutely, there is no problem. Okay. Now, see, very nice discussions. A lot of the analysis has come up. Somebody suggested about we need to have a specific technology-based specific collaborations, and somebody talked about case studies and international case studies and skill development, and then the collaborative models, what it can be done in India. Also, somebody talked about the international scenario, how those things are happening, and how probably we can learn from that. Now, if you look at the whole thing, the academic industry and the government collaboration is the need of the hour. Everybody recognized it. Okay. Now, government is very well aware about these collaborations, and academicians are gearing up, to the change in scenario, and industry is also keen to know what exactly happening in this field. Though they are not come forward very openly, but they are also very eagerly and interestingly looking at this particular model which is emerging from India. Now, why these academic industry and the government collaborations only confined to the what you call boardrooms or presentations or those type of things? A tangible model as of now we are not able to see, or a scaled up model which can be replicated across the country, somehow we are not able to see. There are certain silos or some institutions have very strong collaborations with industry, but it is very limited and very confined to the that institution or an individual. Now the issue is how these learnings can be taken up, and is it possible to generalize it and bring across a type of a national model where these collaborations could be proliferated. That is what the main question that we probably need to and some of the answers I got it from the panel discussions, and I would like to have that points to be made. Now, what is government vision? Now the government looking at return on investments. Gone are the days where proliferation of research or fostering research, of course, that is also still there, but the focus shifted to return on investments. Government is looking at, I'm not talking about industry. I need not talk about industry because they know it very well. Every activity, everything starts with the return on investments, either short term or mid term or long term. They need to have some type of a technology roadmap or what is the things that is getting out of it from me or for industry, and there is nothing wrong in that. Okay, and probably they are not charitable trust, and we cannot pinpoint on that. Now, but as Professor Shantanu Chaudhary rightly told, academics have certain limitations. They are very good researchers, very good innovations are happens, but the product development requires a different kind of skills, different kind of a packaging, different kind of a marketing, different kind of technologies or engineers involved. So those kind of things is available with industry. So now we are bringing two heterogeneous helix together, and we are asking them to work together to go for it. In the existing academic institutes, probably industry collaboration means a sponsored project from the industry to a particular researcher in an institution, or the institution working with some industry for a particular technology development and directs. It is mostly one-to-one. I am looking at the institutionalization of these mechanisms. When we say institutionalization, we need to have a platform where the industry could partner. The partnering could be either knowledge partner or as a capital investment partner or marketing partner or co-developer in those technologies. So we need to have a platform which can enable industry to come and invest either in the terms of knowledge, in terms of capital, or in terms of marketing, and we also call it as a monetization of their time and energy plus the technology that develop. Unless otherwise we have the type of platforms created and nurtured, and probably these three helix coming together, probably it will be a long term or maybe it remains as a dream. So therefore, my views are either quantum is one thing, it's emerging, but there are so many other technologies, which ICPS mission is pursuing. In quantum mission is also probably it will be in the same lines. But instead of looking at very specifics one way, another way is generalized model. I am looking at a generalized model. Now, what are the options for the industry? As I told, they can sponsor a project to an academic institute. It's not going to scale up. Or a CSR grant to an institution. Again, because they have certain conditions they have to be fulfilled, and CSR grant they will provide, and probably they contributed the CSR obligations. Is it enough? No. The technology platforms, what I am referring, probably that is where they know the industry should look forward, where they can partner, the co-develop, and co-deployment products. The another route for the industry is these innovation hubs or Section 8 companies, as I told, they can get into the fund of fund domain also. The fund of fund domain nurtures the startups and goes for that equity they will be taking from the industry. When industry will take equity from the startups because they are the co-investors in those startups. So one part goes to the R&D, the another part goes into the what you call the startup ecosystem. So the fund of fund is another structure or platform where industry can collaborate. The third aspect is not only Indian industry or some industries from abroad or anyone want to invest, they can take the FDA route. Because SEBI controls these, regulations, and there is a very clear path defined for incoming and exit also. This FDA is another option for the industry to participate in the Indian R&D ecosystem. Okay, so one is the specific projects to the individuals at the host institute level or academic institute level, or CSR grant to either the host institute or the technology or the structure which we are referring as the innovation hubs. And third is the fund of fund, and the fourth one is the FDA route. So once we have these entire structure created and nurtured, it becomes, independent of technology. Today we are talking about, quantum. Tomorrow we will talk about some other technology, or, there are another 25 or 100 technologies available. Every IIT is working on various plethora of technologies. For all these technologies, this technology platform should become a platform to translate and product development. For that, we need to aggregate the industry there in that particular level and give the partnerships, at the board level, and as well as at the membership level and the co-development and as well as co-partner level. So there is the ownership built in the hub for the industry. So therefore, they are the co-owners of these hubs. I think this type of structuring is essential, and then probably we are institutionalizing the entire ecosystem of the industry, academia, and government collaborations. Probably I have taken 10 minutes time. If I'm allowed, I will stop here. I will look for other panelists to comment on this. Thank you.
My first urgent to suggest a few thoughts on based on the previous speakers. Yeah.
Am I audible?
Yeah. You are audible.
Yeah. Thanks, Dr. Narayanan. I guess all our panelists has covered almost every point and given great thoughts. So I will conclude this, whatever a roadmap for India in quantum. So I'll just reiterate whatever they have given and adding with my views. So the first thing is on awareness. So one of the audience also asked in the chat window, how about the adoption of Indian industries? So in my experience, whenever we are going for international or global clients or some of the R&D institutes, they are readily accepting or working together, exploring what's happening, what's the future of quantum in this. But still there is a hesitation. Quantum is not a today's technology. So it is going to be a tomorrow's thing, why we need to invest today, or why we need to focus, or where to start. So kind of, I just see little hesitant, or even now it's getting better and growing fastly, but we need to create that awareness among those industries or the students community. So for that, what we have to create that. As some of the panelists said rightly, we have to target certain use cases. For example, the industry is shifting towards autonomous vehicle or electronic vehicle. So in those things, there needs some technology or some mechanism of powering those vehicles. So how fastly you can charge those battery. So quantum is come to handy. So what kind of material combination can be used for that? So, and climate change is the other example. And as I mentioned in the earlier, because of this pandemic, what kind of vaccination, how quickly you can bring into the practice. In telco sector, there are n number of problems ranging from security to fiber rollout. So kind of we have to create a pool of identified problems and prioritize those problems and make awareness among those, industry as well as the student community. So these are all the hard problems. So these are the things we need to take more struggle with this classical system or supercomputers where quantum comes into handy. And even there is another attack happening. So in stealthy mode, all the data are recorded. So whenever the quantum power is real, they will try to break that. Something like how ransomware is getting popular. So now they cannot able to break the encryption system with today's power, but still some of the attacks are happening. They are passively listening or recording those things to exploit that in future when quantum power is available. So the simple solution is you have to create an awareness and you have to work on post-quantum cryptography. So the first aspects I want to say in our roadmap is create an awareness among the industry and the students community. And second aspect, I will say after awareness, I think IBM is rightly doing, and so many of the Indian universities are doing on education part. So NPTEL is offering a course, and there are plenty of universities offering free courses, and also we are creating an opportunity for the students to learn that. As I am glad to see to this, some of the universities are putting quantum as a main and elective courses, but still there is a gap. So when we come to the industry, a small sector other than R&D institute, so how to reskill those employees or upskill those employees? So there we have to see to this a huge partnership between academia and industry and create this kind of a bridge program or some courses where not only the students but also the employees also can reskill them. So here, I think we have plenty of opportunities and students are already, as IBM, Dr. Kargi pointed, within that launch of course, within 2 or 3 days, 15,000 registrations are made. But still, we have to go for that. If it is some of the technology like cloud or security, there are some standard certifications available. Something similar to this, we have to draw a better certification roadmap for quantum. So you not only educate them, but also certify them. So these are the skills required for how to go with this. So we need to work on awareness, and then we have to work on education. And as I already mentioned, we have to prioritize the use cases. So these are all the use cases have a huge potential, are badly needing a quantum power to solve those things. For example, other use case I can say portfolio. In real time, huge stocks you wanted to invest. So today's Monte Carlos or classical ways will take little time. But in a hot market, every second is a money. So quantum power can utilize that and leverage and give a better solutions. There are plenty of algorithms available like amplitude estimate or something still IBM partnering with JP Morgan or some of the R&D institute and universities exploring and coming up with this new algorithm. So we have to prioritize those use cases and also focus on building those right algorithm for those things. And apart from this, I guess I have seen in a global, there are better communities exist for quantum. I can see every fortnight I am part of those community. I'm getting those updates, invites, and all those things. So in India, it's slowly picking up. We are formulating community. We are doing a panel discussion or conducting a conferences. But still, we need to shift the gear and see to this. Actively, we will formulate the community and engage a collaboration between community members or academia or industries, where we can see to this what kind of priority to be taken or what kind of focus has to be done or how to create this awareness and education better. So we have to actively involve this community setup and engage a partnership between the industry and academia. And other aspects in our roadmap is, I think everyone spoke quantum hardware support. It is a very limited. So hardware providers, I can say platform providers like IBM or Bracket or Azure Quantum or Microsoft Azure Quantum or Intel. Some of the hardware providers, even universities are having their own QSIM quantum simulator and some hardware supports available. So we need to see to this. So what kind of real hardware support we can provide for a student community, or apart from simulators, how they can see to this, what is the real power of or hands-on experience of real hardware. So that has to be made. Infra support, we have to put it. And other important thing, I think I missed to say about while prioritizing this. So we have to see to this, the quantum applications. That is a near term, midterm, and long term. I think someone already touched about the point. So near term applications, we have to see to this. It's some of the university support or some of the startup supports, how we can bring it to them. Some of that quantum randomness, already some use cases are built or some POCs are done on those fronts. So kind of some of the financial applications has been already seen the limelight. So we have to prioritize this what is the near-term application? And then what's the midterm application? Midterm application, some of the R&D industries and university can partner and work on this. So what is the priority? How to make it as fast as possible? Is it a universal quantum, or is it an annealer, or is it a hybrid approach? So what can we make it? So we have to draw in line with that. And long-term research, I think rightly pointed, we have to seek for a government help and support funding and prioritize some of the climate change. So kind of those problems, how to solve it long-term, we have to do this. So these are the things, it's in my opinion, we have to draw a roadmap for quantum in India, that is awareness, creation, education, and prioritizing the use cases, and building and expanding the community, and making this infra availability. So apart from this, one more aspect, there is a little hesitant among that industry or corporate sector. As this hardware support is centralized or over a cloud, we have to rely on or share about our data. So what is the privacy of the data? So there comes the government or regulatory body has to come up with some compliance or some policy to be defined. How to share those data, how to protect the privacy of the data. Maybe if we have a time, I would love to hear from this SMEs, what is the take on privacy protection. So these are the points I wanted to say about our roadmap on quantum. So with this, I wanted to say what we are doing. I will just take one more minute. So Infosys has formulated Quantum Center of Excellence. As part of this Center of Excellence, we are engaging with our client interaction. For example, any of our clients, while we are giving a proposal or RFP, we are saying to this, what is the potential or possibilities of pitching into quantum into this. So this is the problem we are solving tomorrow, after a few years. So this is how quantum can come into handy, just creating an awareness or putting into them. So consulting kind of a stream. So we are involving, actively engaging those clients. That is one way we are doing it. And other than that, so we are also engaging with some startups. Already we have onboarded a startup from Australia in quantum security, and plenty of startups from Bangalore and Pune and Calcutta. We are in talks with them and leveraging that. So how to leverage them and take it to our clients or work together in R&D sectors, as well as building some of the use cases we are working. And other than the startup and interacting with the clients, we are also in talks with global universities and Indian IITs and IICs and some top class universities. So with university collaboration, we are just putting in a two-way approach. One, we are identifying the problem statements, what we believe quantum potential or what our client wants us to work. So we are jointly trying to solve these problems, how to take it up, how to jointly define the quantum problem, or how to jointly solve those problems, putting in front of the client. So this is one approach with universities we are doing. And second approach, as I mentioned, reskilling and upskilling. So with the help of this, IIT and NPTEL is providing course. Apart from this, we are in collaboration with or in talks with few universities on reskilling our employees. And also we are just looking how to reskill our clients or what is the interest on those trends. So this is the more we are engaging with universities. So not only global universities, but also we are in talk with few Indian universities. And then the next angle we are looking is exploratory projects. So as I mentioned, fiber rollout, one of the exploratory projects, and protein folding, drug simulation. So kind of we are doing our research. So what is this quantum potential? How quantum can solve into those things? Or what kind of optimal algorithm we can use? Or what is the hybrid model work in case of QML? So kind of something we are exploring. Apart from this, we are trying to partner with few platform providers or industries. Already we are in talk with IBM as well. We have signed and done a press release with Amazon Bracket. So where we are saying not only as a platform providers, but also we are working together to solve some of the interesting problems. Apart from this, we have a dedicated thought leadership page in Infosys.com. So where we are, our quantum experts are writing a blogs or whatever. The latest what we are doing are happening in quantum and what's our point of view on finance industry, telco industry, or aerospace industry, kind of that we are working, and regularly we are publishing so that we will just create an awareness and also internal employees can leverage this, what's happening into quantum. And apart from this, we are enabling the talent, we are providing this, channeling that what kind of certification can be made available for quantum talents, and we are upskilling or reskilling our internal employees as well, our clients. And then we have building few prototypes or POCs. So those are all still in the early stage, or live version of that we are doing it. So we have a demo ready for fleet management and portfolio optimization and workforce allocation, job scheduling problem. So some of these demos we have already built, and we are putting it into our experience centers called as a living labs, so that any of our clients visiting to Infosys or publicly who wanted to know that what's happening in the emerging spaces can look into those things. So these are all kind of activities as part of Quantum Center of Excellence. We are doing that. So with this, I will pass. So these are all my recommendation for roadmap of quantum and what we are doing as part of Infosys.
Thank you very much, Dr. Varadarajan. Yeah. So I think we are overshoot our scheduled time, and there is another talk which is at 7:30. So now I'd like to request Professor Arvind to, with his vast experience and also whatever listened, we heard it from the various industry colleagues, suggest some of the thoughts at the end of this discussion.
Yeah. Well, I think we had a very good discussion, and more important is to have such discussions, more of them. And as I said in the second round, let's get very specific. And it is not just question of industry funding projects in academia, because it is not even very clear today what exact projects need to be funded. I think we need to do specific theme-based brainstormings. That's what I see as the important point coming out of today's discussion, that we should, take up one area, say quantum communication, or we should take up an area of quantum sensors, or we should take up a specific area of quantum computing, or we take up, AI, ML, and networks, or whatever. And in that, we try to thresh out where such collaborations can work. That is one lesson I would like to draw. Second thing is we must learn from our failures. In this country, we have not managed to build industry-academia partnership to the level that we should have done. I would say that some of the new IITs, like the IIT Jodhpur, should take initiatives in this direction, because over the decades, we have in some sense failed, and we should not shy away from recognizing that. Whether it is automobile industry or it is computer industry, our share in producing and putting technologies in those industries is very little. And therefore, for quantum technologies, let's learn from all that experience and see that we have our due share. And for that, government, academia, and industry, all three have to come together. Why government? Because when things are small and cannot get going on their own, it is the role of the government and the policy makers to encourage, and that is what is being done. I also want to use this occasion to specifically say, because I have been involved with all this, right, as I told you, right from year 98, 99, and initial attempts at discussing whether the things could take off. The way Dr. Murli Mohan has provided leadership to these programs. First time there was a brainstorming in Bangalore, in which we all met even before the Quest program went forward, and how consistently and persistently he has seen through these programs to develop. We need that kind of what is called consistent input at the highest level to get these things going. So if one or two of the new IITs take this up in the mission mode, and I think IITs are the right place to get these things going, because they are technology institutions. And of course, all of us will contribute and participate and so on. So again, if these are the last remarks, then I would say that we have a long way to go before we can think of actual technologies coming out and getting translated into industrial products. But that should be our aim, and we should become very specific in this context. So this would be my take-home lesson from today's panel discussion.
Thank you very much, Professor Arvind. I think we are close to, because the next session will start in another 10-15 minutes. So we had a wonderful session. I would like to thank Professor Arvind, our director, Professor Shantanu Chaudhary, Dr. Murli Mohan from industry colleagues, Jay Kumar, Varadarajan, Dr. Shantanu Sardar from Young Scientist Lab, from Mumbai, the Dr. Sarkar from Warwick University, Dr. Gargi from Gargi Das Gupta from IBM. So all gave a wonderful thought for this, and I think with this inputs we received and the suggestions, I think we take it, and as rightly pointed out, with the focused direction and challenges, it will be quite challenging for the further advancement in the direction of quantum technology. So I thank everyone who participated in the panel discussion, and also all the panelists and also all the attendees. So I once again thank, and we conclude this session. Yeah, thank you very much.
Thank you, sir.
Thank you. Bye-bye.
Thank you, sir.
Thank you.
Yeah, thank you.
Thank you.
Yeah, thank you. Thank you.
Hi all. Shibashish, I heard that you will be chairing the next session. Can I just try my slides if they work?
Yeah, please.
Thanks.
Hi, Tomek.
Hey. Okay, do you see it? Or maybe I should actually play this, huh? This will be better. How is it? Do you see this? My slides?
Yeah, full screen, good. Yeah.
Super. Okay. Then I'm turning off my mic and so on, and see you in a couple of minutes.
Yeah, sure.
If I knew how to do that. Here. Okay.
Hello, Dr. Subhashish Ghosh. Dr. Ghosh. Hello.
Hello, can you hear me?
Yes, sir. I was just asking
Hello.
to just check. Yes, sir. Yes, sir. You're audible.
Can you hear me?
Yes, sir. Yes, sir.
Hello.
Hello. Yes, you are audible, sir.
Okay, fine. Shall we start now?
Sure.
Shall we start now?
Yes, sir. We can start now. The final session. Hello, sir. We can start now.
Well, you mean me or Shibashish or who?
No, Dr. Ghosh will introduce you and then you can start.
I thought so. Thanks.
Okay. So good evening, everybody. It's a pleasure to yes, yes. Okay. Just a minute, huh? Tomek, just wait a minute, huh?
No problem, no problem. I'm here and I'm having lots of time. So yeah, I don't want you maybe to stay till midnight.
Sorry.
I have many slides.
Yeah, what, Tomek?
I think I can hear you actually.
Can you recognize me?
Of course. Come on. I think you have some network problems. Sometimes you appear and
Okay,
you
okay.
disappear.
So let me say something about you because that is what I have been asked to tell you. Okay. So how are you?
Yeah, thanks a lot. In Poland, and it's a nice autumn time actually.
Yeah. Okay. Yeah. So, so
how are things
yeah.
there?
So let me tell something about you as usual. So good evening, everybody. So it's a pleasure to have with us Professor Thomas Patrick, whom I know people call as Tomek. Yes.
Correct.
So Tomek did his master's from Institute of Physics at Marie Curie University, and did his PhD from Theoretical Physics and Astrophysics in 2007 from University of Gdansk. Interestingly, he was awarded the Ig Nobel Prize in Biology in 2019, which he shared with Ling-Jun Kong, Herbert Tripez, Agnieszka Boreska, and then Alexandra Urbanek, Reina Dumke, for discovering that dead magnetized cockroaches behave differently than living magnetized cockroaches. So his research activity lies in the interface between quantum physics and other disciplines, most notably quantum foundations, information, and biology. So without further ado, let me invite Tomek to give his talk.
Well, thank you very much, Professor Shibashish. And I wasn't not expecting you really well prepared. I was not expecting that. I'm actually going to give a usual boring talk. So no magnetized cockroaches, like this, just some kind of basic physics. I am sorry, this is maybe disappointing. So also many thanks to Professor Shubashish for organizing this event, for inviting me, giving me this opportunity to say a few words. And I realized I actually didn't participate in many of these online conferences. And I think it's actually my first time I'm giving a talk on a conference, like a bigger kind of gathering of people. And then I realized there's one good thing about it. I can say, good evening, India, good afternoon, Europe, good morning, America. That would be impossible in any offline meeting. So yeah, I guess I'm done with this chit chat. I can show you my slides. Thanks again for the invitation. I'm going to say a few words, actually kind of a summary about our works on mediated dynamics. And I realized we've been working on this for years, like at least 10. So some of the things I stopped when I had I think 40 slides, and I still didn't manage to put in two things that I thought I will also be telling you. I might be slightly, too long. So Shibashish, please feel free to just cut me off right when I'm totally over time. Okay, so what is this mediated dynamics? So to make a connection to the theme of this conference, I also called it a little subtitle, Foundations and Applications. And of course, you can email me here. So this is everything. Thanks again for the introduction. Everything was said by Professor Bosch. So when you think about this mediated dynamics, probably the first thing that comes to your mind, at least when you're kind of this foundations person, is this, that when you have a charge, let's say, and it starts moving, hey, I assume you also can see my cursor. So could you please confirm? Can you see my cursor or only the slides? Anyone?
You can see the cursor.
Cursor, like, no, I'm waving it over here. Can you see it? Yes? So I assume you can. So if you can't, just please shout, and we'll think about some of the solution, right? So what you see in this slide is thanks a lot, is an electric charge that is moving to the right, and this is the electromagnetic wave that it generates. It goes, so as it propagates and changes the electric field around this charge. So imagine you have a different charge, say somewhere here, then even though you have moved the charge, the green charge, this one that I'm just waving with my cursor will feel it later. And these retardation effects are usually explained, that's exactly kind of how we explain them today, that there is a field that mediates this interaction, and it has to take some time for the wave to propagate from one charge to the other charge. So that's one kind of mediators that come to mind. But of course, you don't have to be that fundamental, and this is the same story we have for all the other elementary interactions. But there are also, it's also interesting, this mediated dynamics, that you can also engineer interesting situations. And here's one example, I'll give many more later, where you have two fields taken from some recent paper, where you have two fields that got correlated because they were, so actually they don't interact with each other, so because they have different colors, but nevertheless, they got correlated because they interacted with a single atom. It's a cool experiment where you have a single atom that mediates interactions between the two electromagnetic fields. So these two slides were really just to show you, what in general this mediated dynamics is about. It has this foundational flavor where you can think about fields that mediate interactions, and also this more applied flavor. For example, here there's some engineered situation where two fields interact via an atom. And in general, when you think about this stuff, there is really, it comes in two flavors, I think, the very essence of it. It either has this structure where you had some object A, let's say one charge, and another object B, another charge, and then there was something that was kind of propagating in between them, like maybe a wave or a particle that goes from one party to another. Or you could also think in terms of quantum communication, that's why I wrote it here, that it's essentially just a quantum communication. Imagine you have kind of one lab and another lab, and some particle that flows from one lab to another. That's the basic scheme of quantum communication. But it also essentially, especially the second experiment, interesting, I cannot go back, I can. About this guy, when you think about this sorts of experiments, two fields interacting via an atom, then it's more like the guy below, where you have now object A, one field mode, object B, another field mode, object C, an atom, and all of this stuff interacts continuously in time. So these are just my labels. So I'm gonna call this scenario discrete in time, and I'm gonna call this scenario continuous in time. And this is just so basic that you probably may think that there's nothing really to be learned about this. We probably know this stuff from like hundreds of years. And so no, it actually, especially from quantum info perspective, this is more modern, and you'll see that it's actually really interesting and unexpected stuff comes here. I'm going to go through these two cases one by one. Let me first talk about this communication discrete in time. So here's the simple thing that is essentially really, you should all agree that this is really correct, right? And no one will question this, I hope. Or if you question this, then you probably are questioning the very basic definitions of what information is, because this really looks like almost a defining feature of information. So imagine you have two laboratories, the one on the left and the one on the right. And there is a particle that flows between them, could be classical, could be quantum, whatever. Then it's not hard to prove, And you can see in our paper, and generally speaking, I'm not going to give any proofs. So you feel free to ask me later or just look into those papers. But I'm just gonna talk, what are the results. So here's an inequality that quantifies information gain caused by communication, but which here means caused by this transmission of C from one lab to another. So A versus CB is the situation where C has already been communicated. So A is in one lab and B and C are together in another lab, minus this information between A, C, and B. So now it's the initial information. So this stuff on the left is really the gain. So it's the final information between the laboratories minus initial information between the laboratories. It's not hard to prove that it's always bounded by how much information the particle C carries, right? The one that you communicate. So really you could just say it's kind of every day, everybody sees this in every day. Information gain is bounded by how much information is actually stored in the carriers. So no questions about that. So really, then we were asking, but what actually happens in the quantum regime? So take exactly the same situation and ask exactly the same question, but for quantum entanglement, for example. Take entanglement when the C has already been communicated to the lab on the right. So there is A versus CB, minus the initial entanglement with C is on the lab on the left. And given the previous inequality, you would probably think that it's bounded by how much entanglement this particle carries. And it's not. It's actually bounded by something completely different. That I think is really a surprise number one, that when you try to extrapolate from this information inequality to entanglement inequality, you get a different quantity. Then this is the surprise that I mean here. The entanglement gain is not bounded by how much entanglement particle C carries, but how much discord it carries. So let me now just maybe recall for those, or introduce for those who don't know, and recall for those who already know, what are these two quantities. So entangled states are those which you cannot write as these convex combinations or some sort of coin tosses, and then you just have product states for the parties. Whereas discorded states is a different class of states where you don't really care. So discorded states, to here, this kind of states would be called discorded AB versus C. And what discord demands is that there exists a decomposition. Discorded states are those which cannot be written in such a way where pi C are orthogonal projectors. So here you also, for the entangled states, you also would have some states of C, and they could be non-orthogonal in different, when you mix them in different, for different probabilities, whereas here you demand that they are orthogonal. So that's mathematics, and really what this means, I think, is that actually those states without discord, so those which you can write like this, are really good models of classical communication. Because look, these states pi C, they are orthogonal. So you could dephase or measure the system C in this very basis, and if you don't know the result, you would not disturb the state. So that's kind of really the notion of classicality, that you can measure we can measure an object without disturbing it. And you could also copy this states pi C, right? If you know the basis, that's also not an issue, also something that you could do with classical states. So it's kind of really natural. And let me just step back to this inequality, right? So C is really this discorded state. They encode classical, I think it's good to think that they encode classical communication. And in such a case, this whole expression is just a generalization of this fact that entanglement doesn't grow under local operations and classical communication to the case of quantum communication. So now if this C is a quantum particle that you communicate, it could be discorded, and then you can entangle the two laboratories. And if it's not, then you don't. So this is how it generalizes this so-called LOCC monotonicity. And it also brings the following question, right? So since these discorded states of this form, they have this property that they have orthogonal projectors on C, whereas in general entangled states or separable states don't have this property. So this discorded states, they are a subset of states which are not entangled, a subset of separable states. And now this is the bound on entanglement gain. So it naturally, once you see this kind of quantities, you ask yourself, could it be possible that two laboratories get entangled by exchange of a particle that is actually not entangled? And especially from this quantum communication perspectives, and perhaps even maybe technologies, is that there are plenty of protocols that utilize entanglement. It would be funny if you could actually generate entanglement without communicate it in advance, right? And it turns out it is possible. And what's the trick here is that, look, there exist states, necessarily mixed states, which have different entanglement properties in different bipartitions. So you can design states. I won't go into this design here, but you look in our papers, for example, you can design states which are separable when you look at them in this partition AB versus C or AC versus B. So, which in our communication perspective means that AC versus B was the initial situation where particle C was still in the lab on the left. So you could have states when the particle C is with Alice's lab, there's no entanglement between the labs. So AC versus B is 0. You actually don't communicate any entanglement because you can also design it in such a way that C is not entangled with AB. But yet, there exists entanglement A versus BC. So after communicating C to the other lab, the laboratories would become entangled. So this is on a piece of paper, but people have done also experiments on this back in 2013. And oh, I forgot, there's also one paper that somehow got forgotten, I think in 2005 or so, in Chinese physics letters, that demonstrates also this kind of stuff. Maybe not, I think it's in NMR. So there's always these questions in NMR, is there really entanglement there or not? So in this sense, maybe it's not, but yeah, actually go ahead and ask questions in between.
Thanks, Tomek. This must be a stupid question, but can I just go back in your slide? I'm wondering, I mean, see, in this case, yeah, let's say the one before this, or the one before this. It doesn't matter. So my question is that, the picture with the charges which you showed, the initial and final states are actually different in some sense. I mean, you have a communication which is happening, whereas here it seems to be that you have one state and I mean, the state is not changing. You're just looking at it as different partitions.
Precisely. So thank you very much. This was so really my initial slide was just to introduce basically this whole mediator dynamics or dynamics with mediators, and now I'm focusing on a single time instance. I'll go to really proper dynamics later. That's super important. Thank you very much. So we should have said that 10 minutes beforehand. So at the moment, all of these inequalities that I'm presenting are for a given quantum state. So if you think about dynamics at a given time, they don't apply to this, at least I think not immediately, right? To this, for example, moving charge.
Yeah. Okay, thanks.
Yeah, a single state, and you just look at the state at different bipartitions. Essentially, that's what it boils down to. Operationally, this would mean the transmission of C. Thanks. So this is, people have looked at this, have observed this in the lab. It's kind of interesting that you can distribute entanglement without having it in a particle that is actually communicated between the labs. But it was first time noted maybe in 2003 in really a seminal paper in this field by Two Cubits and others. And this is Alessandro Fedrizzi. I was contributing to one of his experiments that he was leading, and it's with photons. But really, it's just a demonstration of a certain optimized protocol to see a lot of this entanglement distributed in such a way that you don't communicate entanglement. And exactly now I move to the situation where actually something happens in time, but I'll focus. Really, I think you should, for maybe even the whole of this talk, forget about the example with the charge, or almost until the end. So now I will focus on the situations where you have two objects A and B that are coupled and continuously in time with some Hamiltonian, so some Hamiltonian dynamics interact with the mediator C. Now, when you look at this and you recall what most of the courses about entanglement and quantum information tell you, the following expectation might occur, which I think is actually quite intuitive. So it's good to put it forward and try to see where it goes wrong. So usually we're told that quantum entanglement cannot grow via local operations and classical communication. And that's, of course, the very definition. So it must somehow be correct. But then, therefore, when you think about this situation, you see that A locally interacts with C, B locally interacts with C. There is no Hamiltonian that couples H, so Hamiltonian HAB. This is my basic assumption here. No such Hamiltonian. The Hamiltonian is just the sum, the total Hamiltonian is just the sum of HAC plus HBC. And therefore, it is tempting to say that whenever you see that entanglement between AB grows, because these are local interactions, and then you think that once entanglement grows, therefore the C could not be the classical communication. So it somehow must have some non-classical features. And I already argued that it's good to think about states without discord as models of classical communication. So you would think that it should somehow be possible that entanglement gain between these two green objects would imply that you have discord as measured on this C. And that's incorrect. And what we're missing here is the information about initial conditions. So it's really important, what is the initial state of this tripartite dynamics? Here's a simple counterexample. I think the simplest we were able to find, perhaps there is something simpler, but this is just what we thought, is imagine that you have this tripartite 3 parties, and for simplicity, these are now 3 qubits, 3 two-level systems, and they are prepared in a mixed state like this, that you get maximally entangled state between AB, coupled, so tensor product, say some plus state for C, plus another maximally entangled state for A and B, tensor a minus state for C. So it has this property that when you trace out C, you of course end up in an even mixture of two-Bell states. And it's well known that such even mixtures of two-Bell states are not entangled. So essentially at time, so this is my initial state. So at time 0, AB is not entangled. And now imagine that this whole system evolves under this Hamiltonian, which is like X, and so sigma X and the Pauli operator sigma X on Alice plus sigma X on Bob, tensor sigma X for C, or Bob for B and sigma X for C. I have chosen it in such a way that the states of the mediator are eigenstates of this interaction Hamiltonian. So they are stationary. They will never, ever evolve. This system, if you start with this state and you evolve this system according to this Hamiltonian, you always at any time have this particular form that there will be some state for AB, tensor plus, it will never, this plus never evolves, it's stationary. Then some other state of AB, tensor minus. So this is, since plus and minus are orthogonal, you could think about this as some sort of a classicality. It's because they are orthogonal. So you could measure in this basis without disturbing. You could copy this plus and minus and all the stuff that I said before. And yet, when you actually run this evolution on starting with the state, you find that AB become entangled, and they can even become maximally entangled. And you know why? It's just because there actually is, in fact, a lot of entanglement initially. This is not against this entanglement. What is it? Entanglement cannot grow under local operations and classical communication. It's still here that cannot grow. You just realize that you actually have a lot of entanglement, but in different bipartition, A versus BC. Actually, entanglement A versus BC is 1 at all times in this dynamics. This is this dashed line in my plot here. So what happens here, which is still kind of funny, also I call this a surprise, is that you have this entanglement in A versus BC, and you can actually bring it to the subsystems A and B only while keeping C classical at all times. So somehow it's possible to localize entanglement through a classical mediator. So that is still funny, I think. And this has been demonstrated recently in collaboration with Professor Mahesh from Pune, and these guys did experiment where they kind of really run that dynamics in this NMR setup. Oh, but look, by the way, this is also a nice illustration. Look, this is the molecule they were using. Some dibromofluoromethane. I think I even learned what's the name of this. And this is its bond structure. And you see how nicely it actually realizes this mediated dynamics, because this is like qubit 1 or A, this is qubit B, and the bonds, which is most of interactions happen via bonds. And the mediator here is the nucleus of carbon, and the bonds are here. So it's really this H Hamiltonian, here plus Hamiltonian here. In fact, there is a little bit of coupling between A, B, and this is why they actually had to correct for certain things in this experiment. But that's really, I think this is very nice kind of illustration of yet another example how this mediated dynamics, where you can find it right in the lab. And the cool stuff is in this experiment that they just evolved this system that I talked about in the previous slide, but they also dephased it in the basis. So they kept on measuring this mediator at certain times. So here, here, here. Oh, actually, I think 3 times. And you still see that entanglement grows, which is, I think, this yellow line, yellow data points. And really, many thanks to the organizers of QIPA or QIPA in 2018. By the way, this is really something that I think we will never accomplish with our online meetings, because we just met there, went for a talk, grabbed some tea, chatted about this stuff. It's so much harder to do this kind of interactions online. And at the end of the day, there is really a proper collaboration. Yeah, so what I told you is that you actually have to be careful about the statements of how entanglement between A and B, in which situations it can grow. What are really the properties of mediator that will allow mediated dynamics to create entanglement between A and B is still an open problem, because at the moment in my presentation, I just showed you that this can even happen through classical mediator. But we managed to prove that, oh, sorry, one more thing. There's also a theory part in that paper, and we managed to prove that it turns out that the bound on how much entanglement can grow in this situation is not bounded by any discord or entanglement. It's actually bounded by just simply correlations, could be even classical in the initial state, correlations to the mediator. Actually, it probably makes sense to summarize. In this discrete scenario, entanglement can grow even though you don't communicate it. It can grow via separable states or via states which have discord. And in this continuous case, entanglement between A and B, now, previous entanglement was between A and BC. The inequality that I showed you, A versus BC minus AC versus B. Now, here is a bit different because I'm just talking about entanglement AB. And it turns out that this one can even grow without any discord. It's really just the bound is provided by classical correlations. Kind of interesting. And yeah, but now as you see that in this discrete case, the entanglement in partition A versus BC minus AC versus B, but you see that it's somehow, when you take all the system into account, was bounded by the discord. So one could try to see if a similar property could be found for this continuous case. And indeed, we managed to prove this. So it's just an implication. This time I don't have any inequality. Actually, if any one of you has any ideas how would the corresponding inequality look like, I would be very curious to know, like really curious. I think it's probably one of the weakest points in this whole research program. The only thing that we managed to prove up to now is that if throughout your dynamics, so from time 0 to time t, there was no discord, AB versus C, then entanglement A versus BC or B versus AC, but in fixed bipartition, cannot grow. And yeah, this one is a bit more complicated, so you really have to look into the paper if you want to see how this kind of stuff is proven. But that's the statement. And now, in the next step, it will lead us to a nice method that only talks that still, because look, in many situations, you really don't know what this mediator is. So I would like to eliminate it. And I do it in the following way. That this is the inequality in the previous slide. If the dynamics was such that you had no discord on the mediator, then entanglement in A versus BC bipartition cannot grow. But at time t, this entanglement is definitely greater than just entanglement between A and B. And it is also possible to prove that entanglement A versus BC for a classical state is always bounded by the sum of the entropies of A and B. And here it's something really cool, I think, now. Because now I have a quantity, that only talks about A and B, namely entanglement. It talks about entanglement between A and B and entropies of A and B, entanglement at time t, entropies at time 0. But I can conclude something about the mediator, which I have never ever touched. I'm really just talking about A and B here. So here's this inequality provides a method of accessing non-classicality of an inaccessible mediator. So it's inaccessible in this sense that you don't have to know its Hilbert space dimension. Of course, I'm assuming quantum mechanics, right? So there is a Hilbert space for each one of these three systems. But other than that, you don't have to know what's the Hilbert space dimension for this mediator. You don't have to know this interaction, the Hamiltonians, HAC and HBC explicitly. You don't have to know the initial state. I mean, there is the entropy that enters here, but you don't have to really know what's rho, right? This you can measure in the lab at time 0. The method is for NS state. And it turns out that you can also open each one of these systems to a local environment. This inequality still remains, and this implication still remains. So it turns out that if entanglement between systems A and B grows grows above the sum of their initial entropies, then, and of course, sorry, this should be not zero, right? Then discord, then you had some non-zero discord throughout this dynamics, somewhere between times 0 and t. So I think I'm ready. So essentially, I will now show you a bunch of applications, yet another classes of mediators where this applies. So once we realize that this is so general, we just try to apply it in different fields of science, see what this does, right? And the first thing where we applied this was optomechanics, because you have those interesting situations there which are just like look like made for this theorem. So people often talk about cavities which have a membrane in the middle, and then you have a field on the left and the field on the right, and this membrane is actually modeled as a quantum harmonic oscillator. So the interaction Hamiltonian between these objects are exactly as we want. So there is a term which is AC. So actually for optomechanics, it is the number of photons that couples to position of this mirror, and the same on the right. But it has this structure that there is AC plus BC, and there is nothing that couples A and B directly. So we could. So by the way, the first thing that you conclude from the theorem that I have just given is that once you see that entanglement grows AB, so entanglement between the fields only, so you could just close this cavity, look at the fields only. You kind of put these lasers into the cavity, but you don't have to look in, right? Just look at the fields that are then reflected or somehow interacted inside and then got outside. And that alone will allow you to tell that there has to be some quantum correlations of discord with respect to this membrane. But now in this particular model, because now we know this Hamiltonian explicitly, we probably should be able to conclude something more. And indeed, you can actually show that you can compute this entanglement between the fields A and B in the cavities. And it turns out there is actually a lot of entanglement here. So these experiments will likely succeed. And there is a considerable steady state entanglement. And interestingly, because our theorem only tells you that the discord should be there, but since now you know more, you know explicitly the form of your Hamiltonians, it turns out that this AB entanglement also implies entanglement with the membrane. And and also look that this entanglement is only at some time, right? It vanishes later in time, but it doesn't matter. I stress again that in our theorem, it only tells you that there had to be discord at some time during the evolution. It doesn't tell you at which time. So yeah, here you could conclude that membrane is entangled in the process. My second, well, so how much time do I have? Actually, start like 3 minutes, huh? Okay, I'll be quick. Professor Gosh, do you confirm that I have 3 minutes?
No, you have about this is now what about
13 minutes.
Yeah, I have about 5 minutes. Yeah.
About 13-14 minutes. Yeah.
Okay, great. I'm good. So here's another funny experiment. So at the end will lead us to quantum biology. So in 2017, a group of Lindsay, I think. So the first author is Coles. They have put a bunch of bacteria, living bacteria, these bacteria that live somewhere down in some lakes, and they are very light sensitive. So they have antennas that can capture single photons and really try to use each single photon because it's super dark there when they live. So they put them into the cavity, and they observed strong coupling between light and these bacteria just by looking at how much light is transmitted from. But then some referees actually pointed out that this experiment admits a classical model. You can somehow imagine that the light is like oscillator, and in these bacteria, something that couples to light, if you model it also as an oscillator, there is some proper coupling between two classical oscillators that gives these results that these guys have measured. And then I heard it in the talk that Vlatko Vedral was giving. He's one of the authors there. And of course, given that what I have told you by now, you probably already see what I proposed these guys, because this is very natural. Of course, if you really want to conclude that something quantum is going on, just put this bacteria and let it interact with two light modes, which don't interact with each other. Because then when you see that entanglement, when you see that these two light modes become entangled through the bacteria, it has to be that there was some discord. So really, in a sense, a quantum correlation with something in this bacteria that couples to light. Well, actually, in the actual calculations, it's slightly more complicated than that. It actually turns out that if you just look into so this is the scenario that we were looking at. Just take two mirrors, like a cavity with some reflectivities, put these bacteria inside and model them as a bunch of harmonic oscillators. Sorry, this is as a harmonic oscillator. I think at some later version we also had few modes for these bacteria. These are the different modes, different frequency modes that this cavity supports. This is supposed to be harmonic oscillator of this bacteria. Now we take, because they were observed to strongly couple, so you have to take the whole dipole-dipole coupling, and there is some driving here. So if you take this model and actually include more frequency modes than just two, it turns out that you do get a steady state entanglement, but you have to have 4 light modes. And it actually turns out that there is quite some entanglement between these light modes and bacteria, but as soon as you trace out bacteria, there's only tiny amount left. So it's a tough experiment. You would have to look into many modes of your cavity, and there's really not much entanglement in the steady state that actually accumulates between the lights. So we talked to these experimentalists, but this was like they were not interesting. This is too complicated. And my last one, on which I'd like to spend a bit more time, is quantum gravity. So this slide is just to kind of introduce the problem, right, or where we are in this this detection of quantum features of gravity. So of course we have seen a lot of experiments where you have quantum particles interacting with gravity, and this is, just these are the ones that I mentioned here. And in essence, they all use gravity of the Earth. It's always, you either have some neutron that falls or some atom that falls, or maybe you look at some motion of photons in gravity, in Earth's gravity field and all that. It's always gravity. And because of that, you always have microscopic quantum particles that move in the gravity of the Earth, and there's practically no back action from these particles on gravity. You could think it's actually throughout these experiments, it's in one and fixed the same state, on one fixed the same space-time. Nothing really is modified there. So in this sense, you could just think classically about it. These experiments do not prove that that gravity has some non-classical features. It's kind of a background in which things happen. So naturally, right, in this setting, you think about this kind of experiment, right? So if you have two masses that are comparable, so now not a huge Earth and a little particle, right, but two masses that are of comparable sizes, you could think about entangling them via gravity in this sense that there is some degree of freedom of mass A and degree of freedom of mass B, like position. And you embed this experiment into the quantum formalism. And this is probably what quantum gravity people would say, come on, like this is not how we should do it. But I think it's, as a first approximation, it's probably not so bad, because you definitely could embed these experiments into this kind of formalism where you have some Hilbert space for your gravity, and in this Hilbert space there is just one state that you need in order, because it doesn't change the gravity in these experiments. So you could think there is a Hilbert space but you just use one state out of this Hilbert space. It would be consistent with those experiments. So now this is exactly what I want to disqualify, that no, now I want an experiment which shows that during the dynamics, in this Hilbert space of the mediator, so describing gravity, you really would have to have more than one state, and it would have to have discord. So they would have to be somehow non-orthogonal states. If you recall the definition of discord, zero states were the ones for which it was possible to write the tripartite state using only orthogonal states for C. So now I disqualify that. So again, here should be not equal to 0. So this means that there should be some non-orthogonality or coherence. So essentially, a theoretical proposal would be look at two masses coupled gravitationally, see if these masses can develop entanglement which is higher than their sum of their initial entropies. And I guess we had this kind of comment already here, but you probably have heard about this famous BMV experiments by Professor Shugato Bose and all the others, and by Chiara Marletto, Professor Pedral, which is the same idea, but a different setup, right? So they had this superposed masses that were interacting gravitationally and got entangled. So at some point we decided that, okay, so we'll just compute. We wanted to compute how much entanglement you can actually develop due to gravity. And the first setup that came to our mind that seemed to be kind of experimentally friendly is when you have two masses in optomechanics again, and these two masses are like oscillators or trapped in harmonic traps, or maybe really just vibrating oscillators like cantilevers. So one thing to note, if you have these two masses and you think about the gravitational coupling between them, so that's my notation. L is the distance between the centers of mass, and XA and XB are the displacements from each center of mass. So then this guy is the gravitational energy between them. So it's GM squared over the distance between them, which is L plus XB minus XA. And so you can rewrite it like this. And I rewrote it like this because, of course, in these experiments, you have to cool these masses close to the ground state. Otherwise, just thermal fluctuations will kill your entanglement. So that's a prerequisite. Once you cool them into the ground state or near the ground state, the displacements from equilibrium are tiny. So this thing here is tiny compared to L. And it makes sense, it is very reasonable to expand in the powers of this quantity. So when you do it, you just get some rigid energy shift, uninteresting, not observable. Then the first order term is still uninteresting in a sense because it doesn't lead to entanglement. There is no coupling. Each one, so you could add this term to your Hamiltonian for particle A, and you could add this term to the Hamiltonian for particle B. It doesn't produce any entanglement, it's just local terms. So Entanglement is the second order effect. It only starts from this quadratic term. It immediately shows you that it probably will be time consuming to see those effects from the second order term. They have to accumulate. So once you have it, there is certain, so we'll just give you an intuition that I think I really liked about this work. So intuitively, what do you want? You want this second order term, the one that can lead to entanglement. You want it to be comparable to the energy of each oscillator, because then you won't have to wait that long. Otherwise, the free evolution will be dominating, and the second order term will only, you could only see it later in the evolution. So it is a very reasonable quantity. Some reasonable quantity will be achieved when you compare the second order term to the energy of each oscillator. So I'm just taking the second order term, I'm dividing by h bar omega. And then in the next step, if you think that these guys are really on the order of the ground state of harmonic oscillator, you get this quantity. And that's, so it's actually Gm divided by omega squared L cubed. And it turns out you can actually prove even analytically that this is exactly the maximum amount of entanglement one can get in this setup. So I arrived at it through this kind of hand waving, comparing the second order term, energy term, to the energy of each oscillator. But the quantity that you get here precisely gives you the maximum amount of entanglement that you can get in this setup. So this is the relevant quantity for this kind of experiments. I was even afraid because I thought is important. And the person who managed to prove these things is Tanjung Krisnanda on this slide. I won't go into these details because I think I'm slowly really running out of time. And it turns out that when you put the densities that are, for typical materials, this experiment would be super slow. It requires omega on the order of 0.01 hertz. Super slow. And to my surprise, and maybe some of you, if you haven't heard about it, there actually are such experiments done by the LIGO collaboration. They managed to cool almost to the ground state objects as big as in the range of kilograms, and the frequencies there are just one order of magnitude bigger. This is really incredible. This experimental work. But anyway, I think it's too demanding, too high mass, too low temperatures, too slow. We need a different idea, and this different idea we thought is we should release the masses. You know what's the problem here? So look at my hands. If you probably have me very small, but it's where do you get the entanglement in this kind of experiments? It's because if you start with a Gaussian state for particle A and the Gaussian state for particle B, the parts of the wave function that are closer are attracting more than the ones that are further apart. So at a later time, these parts that were closer move faster. They have bigger momentum than the ones that were further apart. And this momentum position correlations, we were thinking this is really where this entanglement comes from. So if we release the masses, we remove those harmonic traps, the particles expand freely, and because of that, there will be much more interactions, and the entanglement should appear faster. And that's exactly what actually one observes here. So now I will just hurry a bit because I run out of my time. That's what you observe. That you can get entanglement much faster within 1 second. Observable entanglement, which observable means comparable to the numbers that people have already observed in optomechanical systems and microwaves. So there is a famous paper where you have some microwaves and optomechanics, and this is 0.01 or something like this, logarithmic negativity. Back to concepts. So the theory was actually done for this kind of scenario, but the calculations I have done for this kind of scenario. So, of course, the question is which one of these is actually good, and I think the answer is both. It's on one hand, we already know from the experiments like even these black hole mergers that gravity is giving rise to retardation effects, just like electromagnetism. So it really, you should think that there is some space-time or whatever, something like this that mediates gravity. But on the other hand, since these objects are so nearby, these retardation effects are negligible. And the Newtonian approximation probably is just good for this. I would argue it's really good for such experimental setup. And in any case, if you might not like it, right? Because fundamentally it really should be mediated. But even if you're kind of an extreme Newtonian physicist and you really think, okay, the gravity is at some sort of a direct coupling, these experiments would still be interesting because it would show you that in the expansion of the gravitational potential that I wrote there in a few slides back as powers of xa minus xb over L, you have to have the coupling term, the second order term. That's the only one that can actually, that has to be there. Otherwise, you won't be able to see entanglement because the previous term was just local. So this is interesting. And it's actually simple. So Ankit Kumar, he's a PhD student at IIT Roorkee. He worked out the situation where you could actually test for the third order term. And it's really very simple and experimentally friendly. It turns out that if you just truncate this expansion of gravitational potential to the second order term, there is no dependence of entanglement on initial momentum. So if in your lab you see that when you push these masses and there is some initial momentum for them, you vary initial momentum, and when you vary it, correspondingly the entanglement varies, it only can happen due to the third order term. So that's yet another kind of precision test of this coupling. And I'll skip this. So here are my conclusions. Mediators are everywhere and they behave surprisingly. Thank you very much. I should thank these people who pay me. So I thank very much Polish National Agency for Academic Exchange. So many thanks. And I'm sorry, I think I ran slightly over time. Any questions? Comments? So thank you very much for the one about the time dependence. The first part was just for a fixed quantum state.
Questions?
May I ask a question?
Yes, of course.
So I want to ask you, when you said discard is non-zero, only then you do see this kind of counterintuitive kind of features, that is entanglement increases between A and B. So is there a situation where entanglement is zero, but discard is only non-zero? That is, when you showed the inequality of entanglement gain earlier, so there is a discard which bounds it.
Yes. Mm-hmm.
Okay.
And
so
now what you want, that discard is zero?
Is it to the situation where you have entanglement is zero, but discard is non-zero? Or you're only restricting to discard non-zero, but I don't care about entanglement?
Oh gosh, this was complicated. Hold on. Let me step back to that inequality, and let's see on that one where we are. Okay, this one you mean, right? Do you see my slides? Yeah.
Yes.
Okay, so and now this holds for any quantum state. Okay, and now
but then if you have restricted to no entanglement between AB with C, that is, if you take AB on one side and C on other side, no entanglement, but discard is non-zero. Only discard is non-zero.
Yes, exactly. So these are exactly the interesting cases, right? And because this is this slide. So it turns out there really are such states where where these two entanglements are zero, but you still have discord AB versus C, and that's precisely what leads to also this entanglement. And at the end of the day, this strange possibility of entangling labs via not entangled states but discorded states.
Yeah. Okay. Thank you.
Yeah, it's strange, but that's how it is. I think the simplest kind of understanding of where this comes from, you could gain from, there is this theorem of Vidal and Tarrach where they show if and only if conditions for a state to be entangled if it's a mixture of a pure state and I think some white noise. And so imagine that now for this pure state, you choose a state, now it's a tripartite state, but it has different Schmidt coefficients across different cuts. You can then prove that from that Vidal-Perrech theorem that in such a way you could design this kind of states by proper mixing of white noise. It will be different at mixtures of white noise, which makes it separable across different cuts. And this is how you could arrive at this. Yeah. Yes, thanks for the question. That was really deep. Yeah.
Any other question?
Yeah, Arul here, Tomek. If I'm to ask, maybe it's got two parts to it. Is there some special case? I mean, the special case when ABC is a pure state, does it lead to any further simplifications? Number one. Number two is I would imagine naively that the relative dimensionality of, let's say, C with respect to A and B may matter in the sense that suppose C is a very small subsystem compared to A and B. Maybe its effects are going to be smaller. Is there anything like that in the details?
Mm-hmm. Yeah. Okay. So the first statement that when the state is pure, it's yes. So actually, you can when the state is pure, then all of these quantities boil down to just entropies of subsystems. And then you can, in this way, you can actually show, you can give a meaning to negative entropy, this negative conditional entropy. So in quantum mechanics, entangled states have this property that they can have negative conditional entropy. And for example, here, look what's on the left, right? In the case of pure states, you could write it like this, that it's the entropy of A minus the entropy of AC. And therefore, so you see that you arrive at the meaning for this negative entropy in a sense that this is how much entanglement between the labs can increase if you move particle C from one lab to another. So that's kind of so there has been this work of Horodecki's, of Renato Renner, people try giving different meanings to this quantity, and this provides you a really simple one, right? Immediately for pure states. The second one about the dimensionality, we actually have one nice application where dimensionality of C matters, but it's in a bit different spirit. It's still think about this scenario where you have them coupled continuously in time. And it turns out that one can prove that if these Hamiltonians commute, then the gain of correlations, for example, entanglement and actually many other correlations, mutual information, and just under some very minimalistic assumptions about these correlation quantifiers, one can prove that there is a bound on how much correlations you can create given by the dimension of this DC. So now, if you violate this bound, this could be your experimental proof that these Hamiltonians don't commute. And indeed, there are such examples. We worked them out in one of the papers with Tanjung Krisnanda and Ray Gennardi and others. So definitely, I think there is much more to it. So once you know the dimension of C, you can do this interesting kind of witnesses of non-classicality, but now not of states, but of dynamics of processes. So it would tell you whether these Hamiltonians commute or not.
Thanks, interesting.
Yeah, thanks. It's PRA 2018 if you're interested in this.
Any other question? Okay. So Tommy, can I ask you one question?
Yes, of course.
Yeah. So regarding your this application in the gravity, in a quantum nature of gravity. So I remember this work of Shogato Bose and also this work of Vedran. They had to get rid of the other degrees of freedom, like internal degrees of freedom of the masses, right? Like spins and others.
True. They also have spins. Yes. So we don't have that. Yeah.
So you have not taken that into account, right?
And yeah, you don't need that actually. So somehow, at the end of the day, people worked out, Shugato and others, they worked out the experimental conditions for their experiment and our experiment that I just described, and they are similar, to my surprise, right? Because they seem, so I think in their case, the one that is now on the picture in this slide. So if what you want to ensure here is that the Casimir effect that between these two objects on the left and the object on the left and object on the right is much smaller than gravitational effect. So you don't get into this electromagnetism. And I think, as if I understood correctly their paper, this happens when the separation between these two arms of superposition is about 1/4 of a millimeter. No, that's demanding. And so in this sense, somehow, so this was one of the things that were absent in our approach, right? Is that you really cool down those masses to the ground state and you don't have this macroscopic superposition. But nevertheless, actually, the time required to entangle these two objects in both approaches is similar.
I see. Okay.
Yeah.
So can one say that then this approach that you have described here in your case, is it comparatively easier to implement?
I think so. Oh no, wait. Okay, so tricky question. So it is. I think there are complementary difficult points. In their case, a difficult point is this initial state where you have to prepare the superposition of 1/4 of a millimeter. That's a tricky business for a quantum coherence, over such a distance. In our case, the initial state is easy in a sense that you just cool down the oscillators and essentially that's it. And this has been demonstrated for various oscillators already. However, in their case, the final state, I think the final entanglement detection is very well described in these papers and a clear procedure. But in our case, you somehow have to reconstruct the covariance matrix, which I think I don't know how to do that really in practice. Right? This step, I think, is a difficult one. So the difficulties are on different stages, but they are there in both scenarios.
I see.
Yeah, it would be really interesting to work out exactly how do you read out entanglement in this setup that I described here. We stopped there and we said, this is the entanglement, right? And how do you read it is your business.
Okay.
Just one little
Any
comment.
more questions?
One comment. I'm very tempted to ask this to Tomek. So you have this, I'm again going back, this is bothering me. If you have A, B, and C, local unitary operation or local operations will be between A and C, let us say A and C, and only B. So, but you are doing AB, AC, and BC, HAB, AC, and HBC. So then how do I expect entanglement not to increase or decrease? Local would be AC and only B, kind of.
It is like this.
So this is something.
Yeah, here I don't have those states, I think. Yeah, here it's not representative. You actually, so the answer is you actually do really local operations, you AC, let's say, then you transmit the C.
Yeah.
So no, like this. So you prepare a suitable separable state between AC and B, let's say. So AC is in one lab, B is in the other lab.
Yeah.
It is not entangled.
Yeah.
Then you do some entangling operation, let's say, on A and C locally in this lab, but it's entangling, but yet such that because the whole state is necessarily mixed, this thing doesn't work for pure states. It's necessarily mixed. So, and this mixedness causes C to still be disentangled from AB.
Right.
Then you move C to the other lab, and you get entanglement. There are no further operations on BC. Or actually, I think you could actually do something, but you don't have to, right? You prepare first separable state between the labs, AC versus B. Then you do something on A and C, and that is entangling indeed, but in a specific way, because the state is mixed, C still remains separable. You move the C to the other lab.
Then you do a operation there. No, I'm not asking about the way in which we do it. I'm only saying what I would have thought of as a local operation when I take A, B, and C. And when do I expect entanglement not to increase? So that would have been on 2 parts once and 1 single part. But I'm doing it twice here. That is like shifting it there and then again do an experiment. So this is a little
You don't have to do it on the other side. Yeah, you don't have to do it on the other side. As soon as the particle C emerges on the other side, you will already have entanglement between the labs.
Okay. Yeah, I will check it. Thank you.
I think this one I didn't explain clearly, so sorry. Yeah.
No, I will check it. Thank you.
Yeah, maybe it's. I will email you. Thanks.
Okay. So yeah, if there is no more question, let us thank the speaker for this wonderful talk and interesting talk, of course. And that's it. So Tomek,
Thanks again.
You after a long time.
Yes, exactly. Nice to see you.
Yeah.
And so many people, I know it's great. Greetings to everyone. Yeah, I'll be joining you on other sessions. Yep.
Okay.
Thank you very much. And
bye-bye.
Yeah, thank you.
And a happy supper. It's really late in your place. Thank you very much.
Yeah, thank you. Bye-bye.
Bye-bye. Thanks.
Okay, thank you, Dr. Tomek. That was very nice. So with that,